Good morning, everyone. I think in the paucity of time, we will start. Those who join us later can take the seats which are empty. So, Susan, are we good to go? Yeah? Are we good to go? Okay. So, good morning, everyone. Welcome to this 121st edition of the Zak World of Façades conference series. My name is Ahmed. I'm part of the organizing team here. I quickly want to introduce the Zak World of Façades conference series to you. So, we've been organizing this event since 2012, finished around 120 editions, with the last one being in Vancouver, Canada last week. So as you see, the event spread all across the globe. We've had some great experiences in organizing these events in different parts of the world. Facades are constructed, designed very differently in different regions. They have different rules, regulations. So for us, it's been a roller coaster of a ride in terms of getting people to come and talk and share their experiences on how facades are designed in different parts of the world. We are here in North America since 2018. This is our third city in the US, but it's our seventh event. We've got a couple of events also completed in Canada and South America also. So slowly but steadily, we are trying to increase our presence in North America with our events. This is the calendar for 2023. A week, event almost once in 2 weeks all across the globe. And as I mentioned, every event is different. Every region has its own challenges. And we hope to present different stories from domain experts at the respective event. I'd quickly like to thank our event partners without whom this event wouldn't have been possible. Starting off with our associate partner, first one is AGC Interpane. AGC Interpane is a value-added glass fabricator out of Germany. They have a reference portfolio of some of the most iconic projects in the world. Agro-Bichtal, another German manufacturer of terracotta products for cladding. Arconic Architectural Products, aluminum cladding solutions. Boston Wary Terracotta, another American-bred specialty terracotta manufacturer. Cosentino, Spanish manufacturer of an interesting sintered stone product called Decton. Envilon, another German manufacturer, they have BIPV, Building Integrated Photovoltaic Solutions, in a form of colored glass. Guardian Glass needs no introduction, one of the world's leading coated glass manufacturer. Komaling Chemi, now part of the HB Fuller Group, into sealing solutions. Neolith, another Spanish manufacturer, sintered stone non-combustible solution. Northern Facades, one of the leading North American manufacturers of rain screen systems. Sherwin-Williams, coil coatings, PVDF, liquid coatings. And then our final partner is HALIO, along with their fabrication partner Viracon. They have a dynamic tinted smart glass product. For those who are applying for the AIA credits, 8 AIA LUHSW credits have been assigned to the event. While signing out at the end of the day, please drop in your AIA membership number and sign out. Our next event is in my hometown of Chennai in India, followed by Cairo in Egypt, Milan. We've got another event in North America and Washington, D.C. a month from now. We've got Hyderabad in India, we've got Hong Kong, we've got Shanghai, New York, that's the biggest one in the region here and the second largest for us after London across the globe. Montreal, and then yes, so we've collaborated with the Society of Facade Engineering. Society of Facade Engineering is the, I think one of the leading bodies for facade engineers around the globe. They have these awards called the Facade Awards, which they've been doing from the last 10, 12 years. Last year we collaborated with them, and post the completion of the London edition, we have this black tie event in the heart of central London, where people from all across the globe nominate their projects, which are then judged by a jury, and then they are awarded at the event. These are the 6 categories which have been shortlisted, which have been announced for this year. These are not only entries from the UK, but all across the globe are welcomed over here. So we've collaborated with them. SFE is part of SIPSI. SIPSI is the ASHRAE equivalent in the UK, in Europe. They're pretty popular over there. And very soon we'll get these awards to North America also. But as of now, the event is in London on the 8th of November upon the completion of the Zak World of Façades conference. Those who are interested to be a part of the awards by getting yourself nominated, please follow the link over here or scan the QR code. It's a very interesting, high-profile event which happens in central London with 500, 600 people attending. And it's a very different experience wearing a bow tie and attending the event. So this is something which we have collaborated with the SFE, the Society of Facade Engineering, and would welcome everyone to participate in this. That's it from me. My role ends here. Just a quick brief. We've recorded today's event, so we'll share the YouTube link from today's recording a week from now. Those who have the delegate badges, you'll see a USB stick hanging out over there. The USB stick has the PDFs of all the partner companies over here. Their product brochures are no more in a hard copy, but in a soft copy. So that USB stick has their PDFs. And the event recording will be shared via an email, via a YouTube link next week. That's it from me. My role ends here. I'd like to call upon today's event host and convener, Edlyn Garcia La Torre. She's the principal and facade consultant at Morrison Hershfield. So she's going to be your host for today, and she's going to be taking the day forward from here. Thank you all.
Good, it's working. Good morning, everyone. Thank you, Ahmed. So yes, my name is Edlyn Garcia La Torre. I'm a principal of facade consultant at Morrison Hershfield. And to relate to so many of you, I'm an architect. But I also work in the facade engineering field mostly. It's my passion. That's why I'm really happy to be here hosting for the Zak World of Façades conference here today. So today we'll be hearing from a great diversity of groups of speakers that will focus on different topics that range from thermal performance, daylighting, just overall envelope performance, current case studies, structural resiliency, materiality, just overall innovation and fabrication. And I think that what it's important to take away from all of this is how to document the current time in place. So given the accelerated way that time progresses, I want us all to just today take a pause from our day-to-day lives and being able to absorb the knowledge that these speakers are going to be bringing forward from their, just lessons learned from their case studies and current projects that they're presenting. As a San Francisco hub here, the majority of the projects will be local, but also how it impacts other projects in other places. So, sorry about that. So like I said, day to day, it's important to document these informations, and that's what's the highlight of everything, is how we can document real time for it to be of high quality, and that's what we're going to be seeing today. So please, if we're going to welcome the first presenter, Felix Weber, on stage. Felix Weber is the principal and facade structural specialist for RDH. And he will be sharing with us some interesting insight on case studies and from thermal performance. And please take it away.
Thank you. Oh, works now. Yeah, I start with a slide which shows how pretty this city is. And I called it Solutions for Energy Efficient Buildings. I wanted to start with some positive image. But originally I was considering whether I mix in the resilience as well. And this can be San Francisco too. This was about 5 years ago, 5 years ago. And you see that the city can dramatically change And so in order to prevent this or reduce the effects of these effects that we see more, our buildings have to be both resilient and sustainable. So the way that that's kind of approached is through adaptation. So you know, California has the climate adaptation strategy, so which is just adapting to the change. And the other one is the mitigation, which is probably what everyone talks also more about, is to reduce the carbon footprint of what we're doing, and to reduce the effects of climate change. So if we're talking about how these can be done, in the facade world, this is really more about the demand reduction, right? So mechanical engineers will discuss their systems, and yes, there's some energy substitution, and you see building integrated photovoltaics, but their impact is still, it's kind of a smaller kind of scale. The big bang, what we typically see is the demand reduction and trying to address the building needs on the facade itself. So that's what we as facade engineers and people who are interested in facade can do. This is a slide that honestly is not very scientific. This is basically some of our senior engineers across the region, basically through darts, and identified, and that's no wonder because RDH started in the Pacific Northwest, and one of the issues that grew them is the leaky condo crisis. And so they, is this working here? Sorry. Oh, yeah. They obviously focused a lot on the air tightness as one of the biggest performance players in the building envelope, and then they identified, shading related aspects, like the glazing, solar Hickman coefficient or divisional shading, but also like U-value related aspects. So we were, there's obviously northern climate specific, and in order to see what we think this could look like in California, we ran a couple of small studies with our energy team to kind of see what the impact is if you have a typical building, and this is all like a trend, right? And to see what happens if you change those parameters. And so you see here that if you like play around with the air tightness the problem is in California, we don't necessarily know what we're building because though Title 24 prescribes an air leakage rate that our envelopes have to achieve, we might be better or worse than that. We don't know because in California we don't measure. In Seattle, right, the 2018 energy code there from Washington, you see that they have to measure, and they have a lot more aggressive targets. What we believe is realistically what we build is probably around the 0.6 CFM per square foot, but 0.4 is the code. That's why we normalized it to the 0.6. And you see that we can get better from there to some extent. When we look at what's being built, this is where in regions where you have to test your air tightness. So Washington and British Columbia, we have this kind of data of what is actually the performance of new buildings or new construction. And you see that over the last years, this like 0.1 to 0.5, depending on, and this is probably because we're doing a lot of testing on passive house. We have those really low values, but the numbers kind of like hone into that area that we feel are getting us some benefit. But it would be good to have similar data for California as well. Next is the thermal performance. It's still, what we try to do here to normalize is on an overall curtain wall, and then see what the benefits are of doing better and very extreme measures. And you see that the benefits are kind of equal, right? Around 5% to where we think we can get reasonably without overdoing it on a curtain wall or on a building envelope. Anything other will require quite intensive kind of measures that we don't really see in California. The shading solar heat gain coefficient. So this is just looking at the glass. And we also here normalize to what we typically see built. And that's because, not because of us, but the energy consultant who typically on the buildings we're involved with run building specific energy models and shift the needle a little bit for the envelope in favor of typically the architectural design intent, away to what typically Title 24 would ask for. And you see that there's also quite some range. It's probably one of the biggest influences for the energy demand. So if you look at glazing products and if you think about window-to-wall ratios and how typically the offset happens between, you get your prescriptive reference as for the facade design, which is a 40% window-to-wall ratio and a 0.25 solar heat gain coefficient, and then you start tweaking your energy model, or you start, like trying to increase your window-to-wall ratio. We kind of get a little bit into backing ourselves into a corner where we can't really progress further with the solar heat gain coefficient, because after this point here of something like a 0.22, 0.23, we're getting into a product range that is very dark. Unless we go and use dynamic glass with static products, there's a little bit of a limit to what we physically can get to with products at the moment. And yes, there's a way of trying to tweak the efficiency of the mechanical system, which is basically addressing the effect, right? But in a case of power outage or so, you don't get much resilience that way. So what this would then typically lead you to is to go darker and darker with your glazing, but you are sacrificing comfort and your quality of your space and your daylight autonomy. So what you really want to do is thinking about shading, right? That helps you, some form of shading that helps you to maintain your clarity of the glass and the performance of the glass, but increase your shading performance. Now there are dozens of ways to create shading. I'm just going to talk about two examples with static, but there's obviously a huge amount of products on the market with different price tags and different visual effects and a lot of room to play with for designers. But for all of these, it's somewhat important that you start bringing them into the design and discussing those very early, because if you want to have that as part of your element of your building, it needs to be early in the considerations for pricing of your energy use, thinking about payback scenarios and so on. So the time when typically the energy models are run, right, at a late stage of the project, is a little late to actually prove or address these. You need to have early stage proof of concept in a way to confirm that these measures are useful and will get your building to perform as you intend. So there are several ways of how to do this. This is the simplest probably. And I'm putting a building that's a circle there as a reference, and that has a very high overhang, because Title 24 allows you to get a guess, right? So if you want to do it prescriptively, you use this projection factor, which is basically the extent of your overhang and the height, and then you can look at what that ratio is, and then you have your azimuth angle, and then you can see that, say, this is kind of close to, say, the 1-to-1, you're getting a reduction of, around somewhere between 55 and over 60%. So this is the factor you can multiply your glazing SHGC with. So 0.25 glazing would, with a factor of 0.4, go to like a 0.1, which is kind of a useful tool to get very early, like, indication of where you might want to sit. It's typically, though, not really addressing when's your peak load, and that's important for the mechanical engineers, or the time dependence on when do you have the sun or when not, right? So trying to maybe utilize solar gains in winter and shading the sun in summer, those games you cannot do with just this kind of simplified table. So people often use shoebox models and just use parameters, and then you see these graphs being produced. It's one way to kind of address it, but they're often very simplified, and they don't really reflect what the real design is on your building. There are ways to do it through the energy model, and I kind of, am a fan in a way of these graphic tools that come out of it. But they are for design use often a little bit sturdy, because you basically have to predetermine what you want to investigate, and then you kind of investigate, and then you figure out it doesn't work, and then you can go all these loops, or you use these parametric tools, but you're only going to get the results that you've all added, right? So the more you put in here in the beginning, the more options you will have later coming out, and you see that you can get lost a little bit. You might. Typically, I see that you need some guidance. I'm a fan of those tools, though, but it is a little complex, because you're trying to address many different topics at once. So what we were trying to do, or looking at, in order to do this a bit more in a playful manner and not as kind of like rigid and linked to the energy model, something we can control more, is to try to utilize Rhino and Grasshopper to model shading. And the idea is that this is not done yet, it's work in progress, but the idea is that we create this little tool, and you see up there on the right, like an early kind of concept play, that allows us to basically review the efficiency of a shading device on the building. So that image on the top right is probably a bit simple, because you see basically just the shades projected from a single spot in the glass onto the sky dome. In reality, you have to consider the full glazing area. But the idea is to have this early stage tool. You can modify your shade design, and you'll get direct feedback of what your solar gains are. So I'm going to show us some projects we've been working on, and I'm with RDH a little over 2 years, so apologies that I can't present any photos from finished projects since that time. But this is a kind of exciting project in a way, because it addresses these kind of aspects I was talking about in the beginning, and I also honestly enjoyed working with EHDD. It was a really good collaboration. And this started with this EHDD, like designed and they probably have their own talks about it, so I don't want to go too much into the history. We started when the concept of using these exterior photovoltaic cells on the building to kind of increase the shading around the perimeter and address thermal comfort issues. And it started with these goals, as you see there. I was putting Den Hart, I don't know where he's really sitting in there, but I just put him a seat. The building where the AIA sits in has this really distinctive south and a west-facing facade. So south is obviously, as we know, typically really good for overhang shadings. West is a little bit more tricky, so it will need some level of operable shades, at least for comfort. And at the time, you know, when we were designing and like considering how effective is it, we were waiting for energy model results and wanted to have content for presentation. So I came up with this really old school way that I could quickly, in like half an hour, produce to show how efficient like our new shading would be. But now we, like in hindsight, we've also tried out our tool. So this shows basically what's there, right? The shading of the projection of the precast concrete. It's nice and brutalism, but it doesn't really do much. You see that the overhang is typically mostly not efficient. And to then show what I was then doing in very poor PowerPoint skills. So you see the impact of the overhang, right? On the south, you see, oops, there's my, ooh. You see how, you know, we are kind of in summer really shading out most of the sun, and it's kind of conveniently what, you know, without running the energy model and having all the results, but it shows what kind of corresponds pretty well to the cooling season that you would get out of an ASHRAE chart. The same for the west-facing facade. And you see that though, yes, you still have sun hitting your perimeter or your envelope in the afternoon, right? The really high solar exposure times are kind of covered by the shading. So the shades have basically a different angle depending on whether they're west-facing or south-facing, and that's depending on the optimum angle we need for the PV cells need for energy production. It's been forward and back, and you sometimes say architects shouldn't build their own house with AIA, but it's kind of honing in on a very efficient kind of minimalist, but I kind of like it, structure that uses tubular steel and nodes that are really hidden through, you know, at the moment considering casting. And then the PV is on subframes and gets attached to the existing structure. So this project at the moment finished CDs, and here's some image from our engineering and drawings. Another project I wanted to show, and I'm not sure, I'm trying to show not too much, but also something, is the new hospital on Parnassus Heights. It's a 16-story tower, and it's integrated project delivery with the target value design method. And Herzog de Romoran are the design architects, HDR, the architect of record. It's been a very intense and interesting process. We're working since the beginning closely with our GC, which is a joint venture formed by Herrero, Bolt, and Webcore. And one of the things that defines this building, at least the upper part, and I'm going to just focus on that, is the patient room bits, which are like the upper floors. And they have a double function in a way of breaking down the scale of this building, also through the ramping to the back, and also providing shade to the patient rooms. And our energy targets there are pretty aggressive. So the shading coefficient we can have is a lot less than Title 24, and this is just not even assuming the scale of the overhang. And we have, beside that, but this is not so much about the performance to deal with Oshport 1. So it's a seismically challenging project, and have to convince Oshport of wood and terracotta cladding. And the site is very restricted. We evaluated the shades, and this is a slide that Arup produced as and Mazzetti as the mechanical engineers, but the facade is basically driven by the cooling energy use and the mechanical system size. And we're trying to get additional benefits for the patients because we can use the interior blinds for preventing glare, but in the end, like on the site where we are, and with the concept of the healing habitat, we really want to maximize the time that the patients have as a view out of the building. And you see here the effect the shades are, because the building is staggered and the shades are staggered, we just picked one room, but you see that they're very efficient, and we cover a lot of this is west facing, a lot of the peak solar loads. And this is the south. And still, because of the energy targets being that grave, we have to consider interior shades to, and now my time is running out, but I think I have some extra, right? But so we're still considering interior shades, which we know Title 24 wouldn't allow us, but for reducing the peak loads on the mechanical system, they are effective. And so we're trying to utilize the interior blinds that are automated in the first place because of the patient comfort to help us with the very low angle sun conditions. We've been going through many studies of how to build this facade. These are just some kind of design concepts. These were the kind of 3 options that came out of 15 different options we scanned for feasibility, and the process is ongoing. But it's a very, it's been a very interesting and very nice working relationship with the team. And we're aiming to be completed by 2030 with this hospital. And until then, this is just my final slide, and not my slide, but we have the design, the overall massing, the overall facade outline established, and this very early design helped us to very early design studies. In this case, they were run by the sustainability teams at Arup and Mazzetti. Allowed us to prove the efficiency of this facade concept, and now we're working on realizing it and optimizing it, and obviously primarily for cost, but cost and carbon has some relation, and that's the ongoing work at the moment to make this a successful project. Thank you.
All right, thank you, Felix. That was certainly entertaining with all the interruptions and all. Not old school, definitely. It's really refreshing to see how you're really incorporating, data and understanding those sun paths within the tool, and not just like letting the software do it for you. So that was really appreciative in that case. So now we're going to welcome Mark Schwettmann. He's a design principal and residential practice leader at SOM. And I'm excited to learn a little bit more about 1515 Mission, which is a bit of a newest, tallest high-rise here in San Francisco. So I'm eager to understand a little bit better about that facade as well. So without further ado, welcome, Mark.
Thank you. Thanks, everybody. I'm going to talk today about 1550 Mission Street, which is a residential tower recently completed, not too far from where we are here, about 7 blocks to the west. And the interesting thing about the site is that there's an emerging cluster of tall buildings planned and in process, basically at the intersection of Market and Van Ness streets, which are two of the city's most important streets, well outside the traditional financial district, just to the south of the Civic Center, and just to the east of a neighborhood called Hayes Valley. So the site is incredibly prominent for anybody entering the city from the west. It's a large site that formerly housed a motor plant back in the day and then a Goodwill processing facility. It has kind of an acute Flatiron corner at that southwest tip where everybody kind of gets off the freeway driving right towards it. The zoning of the site was kind of nonsensical. It required it allowed three tiny little residential towers, less than 8,000 square feet per floor. It only allowed office on the first 4 floors, but the city wanted to build a new office building. So the first thing we did was rezone the site, moved the office to one side, the residential to the other, which really put this residential tower right at that most prominent corner. So it's the first thing you see coming into the city from the Central Skyway in that direction. So we wanted to find a way that a residential building could have a civic presence, which often they don't. So we started with a series of open spaces at the base, but then wrapped the tower in this curving sculptural precast concrete facade. That's really the signature element of the facade. It is a unitized precast system that curves at 2 corners and spreads apart at that prominent southwest corner to reveal a terraced window wall. So some views of the completed building looking up at that facade. And how it meets the ground, the precast stops 2 stories above the street, switches to stone cladding, as well as a very large self-supporting aluminum wind canopy. So when people think about San Francisco, and particularly living in San Francisco, they don't really think about towers. They usually imagine Victorians on the hills, this sort of Mediterranean quality of white and beige and pastel-colored buildings. And we've been working on residential towers in San Francisco for a long time. This is a series of 4 that we've done, of which 1550 is the one on the left, the most recent. And they all speak to how we can express this sense of light, material, color, and scale in very tall, repetitive buildings. The other thing that this building deals with is we also designed the city office building on the same site. So this image shows the city office building in the foreground on the right, the residential tower beyond there. And the city office building has a electrochromic glass facade that really simply expresses what the office building is, which is a 30-foot steel grid with a 5-foot planning module. So the residential building sits against this grid, but has its own rhythm and repetition. And it starts with expressing the columns. So the precast covers all the columns, which works very nicely from the inside. We express the floor lines. And then there's a secondary finer grain that stacks up that roughly expresses the room module. The additional pieces that bounce back and forth between there are flexible, and they form intermediate mullions and windows within the rooms. So these are some design renderings from about 5 or 6 years ago. Study models, elevations, and then the design details. So the precast system is around 8 inches deep at its thickest. It's around 5 inches deep at its shallowest. That delta of 3 inches is super important. That really is what gives you light and texture and scale. And as that gets bigger, the whole building gets heavier. So we try to really optimize that. And then the vertical pilasters are in 1-foot increments. So these 2 curving facades shown unrolled here have hundreds and hundreds of panels. And in order to make the thing cost effective, we developed a system of relatively few panels that are slightly varied and repeated. So although it doesn't look like there's much repetition, there are a lot of panels that are actually exactly the same. And there's even more panels that are just slightly different. So Willis Precast fabricated it. They did a fantastic job. They're really great to work with. And what you can see in the formwork is that the fixed elements are steel. The bed is steel, the rails are steel. And then within the steel elements, there are steel window frames that are fixed sizes But those move around, and there are wood pieces that kind of make up the difference as you shift the pattern in there. So this is panels being constructed, panels out at the yard, hundreds and hundreds of these things lined up. It was really exciting to go and see them accumulating before getting lifted onto the building, some of their details. Some of the unique conditions where that curving screen sort of slides past the building, it thickens a little bit, has a sculptural edge. We worked really hard to incorporate reveals and details so that the panel joints were sort of lost in the field of the detailing. And these are lifted onto the building, pre-glazed generally. So the punch windows were made by Torre. They were set in Willis's facility in San Juan Bautista, brought up here, lifted onto the building. We utilized the ability of these very large precast panels to cantilever. So you can see that roughly 20-foot backspan, then about a 10-foot piece that actually extends past the structure of the building. And of course, the idea had this one opened corner, but then it had two curving corners. And so precast is a great material for that because, you know, concrete can be made into almost any shape that you want. But we pretty quickly realized we couldn't afford to curve the glass. So the precast is curved, which makes the outer line that you see at that spandrel curved, makes the vertical elements curved. We did have to thicken the panels a little bit because as you go around the curve and you draw a straight line, obviously the window kind of jumps behind the inside of the sill there. So here's that finished product going around the two corners. They have the same radius. It doesn't look like it because one of them turns 90 degrees and the other only turns about 60 degrees. But that way they can reuse this big curved bed that they made. So again, steel bed, steel rails, and then a mix of steel and wood infill elements. The real challenge that we find with precast is to make it cost effective, you have to do donut panels because you can't lift 1,000 picks on one of these buildings. You know, you have to lift big chunks of the facade at a time. When you make a donut panel, it needs to have a top and a bottom. And the combination of the top and the bottom here usually ends up in a dimension that's like often close to 2'6", and it's really thick, and it kind of ruins the vertical fine-grained character that we were trying to achieve. So we spent a lot of time working with everybody about this. We came up with 4 or 5 different ways that we thought would resolve this problem. We begged our client to build mock-ups of all of them. They only let us make 2 of them, but nonetheless we did. And the difference here, at first it appears subtle. It's actually really important. The one on the left is the darkest precast that Willis could really make reliably. The one on the right is the same but polished. So we convinced them to try this to polish just that darker square. And what happens because it's polished is it reflects the light in the same way the metal does. And most of the time, not always, but most of the time, this band of the precast sort of merges into the recessed reading of the window frame. So really what you see is the lighter precast. It kind of jumps forward. And sometimes it's more effective than others, but in general it really works. And you see the kind of lightness of these light precast elements. The proportions work great from the inside. The building has a window wall section, which is in the middle, and then the precast sections on the left and the right. Again, very carefully coordinating the fixed verticals with the walls, and then that one in the middle moves around depending on the room. The other great thing about precast is you can almost make it any color and texture you want. So we worked really hard with Willis, hundreds of iterations of exactly how much of different types of sand and aggregate and how much sandblast is there on it for the 2 different colors. The one on the left was actually what we approved, and then somewhere towards the beginning of the construction process, they said, well, we have a better idea. We can get this other aggregate. It's closer, less shipping, more sustainable, cheaper. Can we switch it out? It actually had a lot too much yellow in it, and so we worked with them to actually change the mix of the aggregate a little bit to get it a little bit closer to the one on the left. So the nice thing about it is in the kind of strong raking light you get here often in the afternoon and the morning, sort of before the fog rolls in. The kind of crystalline quality of that white precast really highlights the 3 inches of depth that you get between the window and the outer face. Creates just a nice, relatively subtle tapestry of light. It looks different at different times of day, of course. Here you can see the way in this photo, this dark piece, I mean, it pretty much looks just like the metal. We got the color pretty close, and the sort of similar degree of reflectivity really helps. Lots of little details go into these things, and one important one was the client very quickly came to us, and they were an amazing client. They said, we don't really need glass in the part that sticks out, do we? Because it's not enclosing anything, it's just a waste. We said, well, you know, the overall reading is intended to be kind of a sloping, single diagonal line, not a stair step. And if you take the glass out, you kind of start to read the stair step. So we convinced them that it was the right thing to do, but we did really optimize this condition. The 5 panels that are making that up, the top 5, repeat exactly every time. So the angle is obviously closely related to the floor-to-floor heights. There are different floor-to-floor heights. The J3 one you can see there is much higher. The maximum slope was actually set based on how far the precast could cantilever, because we didn't want to have a bunch of steel out there behind it that would have to be painted and waterproofed and all that. So it goes from 9'7" to 0, basically. And it really is a signature element of the building. One image I didn't include is there's a company that makes recycled water systems that are in this building. So they're using all the building's gray water as recycled water. And one of the things they did with it is they made beer out of the recycled water. And they have a beautiful drawing of the building on the can. It's pretty much from that angle. So I was joking, as an architect, there's like a few things you want, and having your building on a beer can, I think, is one of them. And then the top of the building, you know, the way these things meet the sky is really important. The original concept had an extra layer behind the glass, and that was like a metal mesh or something to screen the mechanical equipment. But as all of you know, 2 layers, you always end up getting rid of one of them. So the back layer got removed, and then we're like, oh man, we're gonna see right through this thing, see all the junk that's back there. So we worked really hard with the glass supplier to come up with a pretty interesting glass type for the top of this building. It's laminated glass. It actually has the same low E coating as the typical glass, even though it's not enclosing anything. And then in addition to that, we added a dark gray film to the laminate. And we had about 10 or 20 different ones made up. I looked at them inside. It was like, this doesn't mean anything. We went and had them placed on the building at different angles and different positions. You know, we're kind of holding it up to the sun, like, how much can you see through this thing? And then finally got this poor guy on the construction team to go up there and hold it like at just the right angle off to the side of the building. So what we're trying to do there is match the color of the clear glass with the sky reflection to a piece of glass that doesn't have anything behind it. It doesn't have a dark room inside it. It's super effective. You wouldn't believe it, but that top is almost completely opaque. So you can see on the right, that mechanical penthouse, it just like disappears behind there. There's all kinds of crap up there, as everyone knows. We worked really hard to get the steel pulled away from the corners, so all you really see is this precast fin. There's a teeny little piece of it poking out up there. And it, you know, in an aerial view, of course, you can see how much junk there is on that roof. I will say they never park the BMU, so it's always sticking up there. But the effect is really convincing for just a single layer of glass, basically. So then, where the building meets the ground, precast is great. Really happy with how it turned out, but it's not the nicest material to walk up to at the street level. So we used Napoleon gray limestone from Missouri, in the Ozarks, at the base of the building. There it is being quarried. Here it is at a fabricator down in LA, laying out the pieces, testing them. Nice big vertical dimension pieces, really nice soft grain on this material. There's a wall of it on the left, and you can see the column and entry cladding on the right. And then the last element I'll talk about is there's a sort of, see that little metal piece that's wrapping around the top there? That piece sort of disappears at this end of the building, but it actually cantilevers out about 30 feet at the southwest corner. San Francisco is super windy at times, and there's an ordinance that basically requires that you not make it any windier. And this west-facing building, the wind comes in over the hills, hits it, and obviously gets directed straight down at the sidewalk. So one of the things that we found mitigated it was a big canopy. The original design of the canopy had steel trusses and then aluminum panels. It was very expensive. It was very clunky. So we came up with an idea working with Boak Modern. It's an aluminum fabricator here in San Francisco. To start with big sheets of aluminum, cut them into triangles, fold up the triangles, bolt the triangles together in 2 layers, which basically makes a 3-dimensional aluminum truss in all 3 axes, really. And then those are bolted onto the building. So this is a rendering of it, looking up through it. It behaves a lot like a tree in that it moves a little bit, and the 2 layers deflect the wind kind of in different directions, but they don't completely stop it. It's not like a single sheet of glass. Here it is being built on the left, and you can see the corner part gradually making its way out there. Very nerve-wracking, but it did go together. And then a final image of the building. This is on the sidewalk of South Van Ness, under that canopy, the stone and the precast cladding there on the right, and the city office building in the distance. So I realized I went too fast because there's 8 minutes left, but I think I started late, so I will end with that.
All right, thank you, Mark. Definitely, I think we all appreciate that story about just how glass was chosen and just that, reality check of how to choose it properly. That gray tint is a great solution. Thank you for sharing that anecdote. So now we're gonna be talking about terracotta with, sorry about that. So right now, about terracotta, just overall, it's, I think, one of the most sustainable materials we can use. And we're going to have on board now John Krouse, which is not only president and CEO of Boston Valley Terracotta, he's also a ceramics engineer, right? Yeah. That's really interesting. So, yeah, take it away. Show us what you got.
Thank you, Edlyn. Great job. Thank you for introducing me. Hi, everybody. My name is John Krouse. I'm the president and CEO of Boston Valley. And you guys are the guys that design the buildings. I just make the material for you. So we're going to learn a little bit about some of the research that we do. This particular job that I'm going to talk about and was just completed, OCMA with Morphosis, and Edlyn was involved. She was the engineer behind the scenes making this attachment system happen, so it was quite a collaborative experience. So when you decide to choose terracotta for your envelope or facade, there's certain properties that are inherent with the material that are really important to understand. Number one, it's been around for like 3,000 years easily, if not longer. It's been used all over the globe. It's a proven building material. It's very stable. It behaves like granite, but it's a lot lighter. It's hollow. It's very plastic. As you can see in the picture on the left, there's an artist working with a wood tool to manipulate the clay. So in its soft form, it can be manipulated. And on the right is an image of where a technical piece of ceramics can be manipulated the same way, where you can fold it and bend it. And a lot of that experimentation is done at our ACAW event, and out on our tabletop, I brought a bunch of research books with me, and you're welcome to take one if you want. But in essence, what ACAW does is it kind of pulls together a consortium of manufacturing and architects that are interested in learning a little bit more on how to design and build with the material, some of the constraints and stuff like that. So we hosted up at the University of Buffalo, which has an architecture and planning program, and it keeps it very research oriented. We also invite a lot of academic schools to participate. It happens every August, the second week of August. It's open to the public and it'll stream live, but in essence, what we're doing is we're really trying to move the material to the forefront of how we can exploit this awesome building material for today's energy issues, how to make the building behave and perform better. And what you'll see here is there's 8 teams on the floor from various areas of the world. We have FX Collaborative on the right, and we have WJE, which is a facade engineering group that does a lot of historic work that we worked with, and they had some great ideas. So one of the projects that was brought to the table was Jain does a lot of preservation on historic terracotta buildings across North America, and I've been pushing one of the principals to get involved in this program to start exploiting that we can put cornices back on buildings a lot lighter and faster than the conventional method of these heavy structural blocks that are up there. So this was an exercise to leverage our rain screen principle, do lightweight extrusions, and then mimic a very large cornice on a building or some type of band course or stuff like that. It was a very successful project. Everybody's engaged. They're all working with tools. They're actually rolling up their sleeves and problem solving on the fly. We spent a lot of time in the early part of the ACA event. January, February, and March are SDs, DDs, and then CDs are in March. Then we tell them to stop, put the pencil down. Now we got to build all this stuff for them. And then when they come into Buffalo in August, all the material is sitting there waiting for their team to put it together. So it's a really fun exercise. And you can see the focus with the younger associates that are, totally hands-on. Everybody's into it. And at the end of the day, we want a successful project and outcome so this can be taken to market. So this type of exercise allows that to happen. And then at the end, we make everybody present their research, and we put everything on a certain size calibration to get it inside Hayes Hall, where the actual fun happens, where we present. We have a little cocktail party. But at the end of the day, everybody gets to know everybody a little bit better, and we're trying to understand how we can work with this material in a different way. And you can see how thin the cross-section is on this cornice, but if you were standing on the ground looking up at it, you'd have no idea that these aren't gigantic, heavy terracotta blocks. And since we're involved in rain screen facades, we know how to extrude this material at a very long length and keep the weight down and keep it thin. So it makes sense to explore this option. They built a second one for the testing facility. So this is a serious project where they really want to get it spec'd and start using this in applications across North America. So one of the things that WJE did is they invested in a really nice lab, and they'll be able to perform all the necessary testing on this to get this qualified. Next, we worked with Cook Fox in New York a couple years ago on a really interesting project. There's a little mistake there with the architect. They had that mixed up, so I apologize for that. Anyway, we worked with Burrow Happold and Cook Fox on this one. And they were really interested in a screen. And one of the principal architects that works there is actually a beekeeper. So his interest is actually getting nature to get involved in the ceramics through a screen system. A lot of thought was put into this project, but at the end of the day, it's all about trying to work with the architect to understand simplicity of the design. You don't want too many molds. This entire design work started out with 6 different configurations. We were able to convince them to keep it into one rotating piece, so if they ever do want to build this, it would be cost effective, so you're only building one machine die to stamp this stuff out instead of 6 different shapes. But it's really about the design and pushing yourself to really have fun with the material, but also how it's going to behave, how it's going to fasten together, how the insects and the bees and the plants are going to interact with it. So what they developed was different pod shapes that accept the housing of the bees when they want to set up a nest. So we came up with a separate strategy. Actually, Cook Fox came up with the strategy. We helped them kind of design engineer different size modules that actually bolt into the back of the ceramic module that were made out of the same material, but they're fired at a lower temperature. So we chose a lightweight red, your classic red terracotta that acts like a flower pot, basically. And there's also all these properties that have to do with controlling humidity, temperature, moisture, all kinds of fun things that actually work when you do projects like this. So this is an experimental project to see if we can get bees to set up in here and birds to nest inside these modules. They can also be changed out if there's ever a failure. You can come in from behind the carcass and actually remove the module and put a clean one in or a new one or a different shape. So we had a lot of fun working with them on that. And then we get into the nitty-gritty details of right down to the fasteners and all that fun stuff that make these very collaborative exercises. And these guys are focused. They show up ready to go. I mean, we supplied the tools. This was during COVID, so we actually had to pull off this event one at a time at our factory. We weren't able to go up to the University of Buffalo. We had a lot of extra students helping us, but we were able to get it done. We didn't shut the project down, and we learned a lot with working with the team. And at the end of the day, the thing went together really well. It was well thought out, well planned, and the plants are still living inside the modules. And it really, it was a fantastic job just being involved with the team and their design that they developed. Now we're going to get into a little bit of performative value of what architectural ceramics can provide. Our facility is really a custom sculpture house. We don't do like a commodity product. We love getting involved in unique projects like this or research where we can explore and understand what the next shape could look like for an architect. So we teamed up with Woods Bagot. They accepted the offer to come to ACA, and we got a powerhouse group of people. They brought together all their knowledge, and their focus was on photovoltaic cells and how to integrate it into the ceramic panel that can be modularly assembled on our existing rain screen attachment system. So when we open up the box and pull out all the pieces, we lay everything out, we start the organization. It can be a little overwhelming when they first show up. They're not used to really doing this type of work, but we kind of walk them through the organization of it and then just leave it there for them. We don't want to start jumping in and doing their job for them. But one of the things that we do during the ACA event is we really have a lot of fun exploring glaze finishes that are available for this type of work. So we have a separate artist that we work with out of Kansas City. His name is Andy Brayman with the Matter Factory. He does about 70% of the ACA work for us. We try to keep a lot of the research out of the main production facility, and it allows us to focus really on the ACA event, personalize it, and really deliver a unique product and finish for the architect. Here we're trying to explore what the glaze is going to do on a vertical surface to see if it runs, reflectance, things like that. That's the end, the vision of the model, the final model from the architect. We did not get into the corner variants. We just ran out of time. But as you can see, we had a lot of trouble finding somebody that wanted to build a photovoltaic and donate it to this cause. So we mimicked it with just the glass. So you got to kind of visualize what the rest of it would look like, but it's all commercially available. The Americans are a little nervous about doing stuff like this. I think the Spanish are really eager to get involved, but for the most part, this will happen eventually. So we're looking ahead in the future of what could be. And at the end of the day, when you model that whole thing out on a building it facing the right elevation, I think these guys are onto something. So I think this is the direction that the material can move into to help facilitate photovoltaic activity on a building and actually reduce the energy consumption. Next, we'll talk about how to control light. This was a very interesting research project. Gustav, who is the head designer, it's his brainchild. I'm friends with the structural engineer, Ralph Forrest, and they brought a couple technical guys with them, but this was a really difficult shape, but they pulled it off. But before I get into that, I think that slide was out of order. This was the job that started from ACA, where the folks from Morphosis about 4 years ago they wanted to put a ceramic skin on the project, but they were a little nervous about how to bend the panels and whether it would work or not. And it's a huge risk. So we urged them to participate in the ACA event to see if we could actually do something and control the tolerances on it. So this was the finished product, but the early days, we were just taking the ceramic elements and cutting them and trying to twist them and bend them and working out some early ideas with Morphosis. Eventually, they gained confidence in the fact that we could actually pull this thing off, so we invited them back a second year to like really start to nail it. And then when we really trusted the 3D technology working with Rhino, which all you guys work with in your firm, I would imagine, or some type of 3D modeling, we actually work with the same software. So we could take your model and then we can actually start working with it. So we helped Morphosis rationalize the number of curved panels, jigs that were required to bend all this stuff. So it came in way over budget, and we were scrambling for a few months on how to, manipulate the joint lines, which was done by Morphosis, and then we would just collaborate back and forth with them. What if we did this? What if we did that? So we were able to actually shave well over $1 million out of this just through a couple months exercise of exploring how to chase the joint lines on the building and reduce the curvature. So at the end of the second exercise, we agreed to actually mock it up and say, I think we can do this. And with collaboration from industry, Morris Hershfield was key to this. Also some other players, SFS and a few others. We were able to come up and build a team that could actually assemble this thing and figure it out. And then it speaks for itself. We went to the Edlyn met us over there in LA last year, and we were so excited to see the unveiling and walk through the actual gallery, and it was like a huge piece of sculpture that you're standing inside of. It's incredible. So if you haven't been down there, I urge you to go look at it, but it really turned out nice. That's another finished shot. That was the simpler planter box. Clark Construction wanted us to get right into the atrium first, and we urged them to start on the simple area, get the guys in the field comfortable just working with the system, and then take it to the challenging area. That's how it ended up going at the end of the day anyway. And that was a great experience. So getting back to FX Collaborative, most of the architects like to 3D print their model or machine a model and bring it with them to ACOS so they can actually not only have the computer rendering, but the physical model to kind of make sure they're realizing the assembly properly. This was designed to control light and focus a beam of light into an interior space. So I think it's going to act as a screen wall as well. Not really sure, but this was their focus, to be able to direct a beam of light, and it worked. What made it really challenging is working out the details on how we were going to hang it. Now, these are ideas that don't really have a finalized attachment system, but in working with them and bringing in partners, on this particular partner that we had was Tri-Pyramid out of the Boston area. They're also a resource that we bring in if we want to design some custom attachment clips. So we did some one-off clips, and there's the detailing that was done on the clip. A lot of thought is put into this. There's a lot of engineering calculations that are done behind the scenes with the facade engineering teams that are part of it. So at the end of the day, we're really delivering what we would consider a module that all it requires is some final testing, and then it's ready for market. And then you can see it was all hands on deck, and we were really cranking it out. We're studying the light, how it came through, and then the finished product going up to the gallery. So that's the presentation, and hope you enjoyed it. Thank you.
All right, thank you so much, John. Definitely sign me up for the next year's workshop, if possible. And yes, it was pretty challenging to engineer and problem solve all those joints between the double curve. Great design by Morphosis. It was really fun, so thank you. Great teamwork overall. So our next presenter is she is a fellow facade specialist as well. And please welcome to the, sorry, I can't see with the light, a little bright. Hi, Karen. Come on over, Karen Burns. She's a senior principal and has the West Coast office in Heintges. So happy to have you on board, and your topic is right on the idea of talking about the current and the present time. So let's thank you for coming, and we'll learn from you. Thank you.
Great, thank you. And this is what I used to advance? Okay, great. It's great to be here. It's great to see everyone. Again, my name is Brandt. I'm a senior principal at Heintges in San Francisco, and I manage all of our firm's West Coast projects and operations. For those of you who might not know Heintges, our firm, we are a specialist consulting firm focusing exclusively on the building envelope, facades, and roofing and waterproofing. So what I wanted to talk about today is really thinking about specifically basically embodied carbon, but also responsible energy use, responsible material use, but specifically in the framework of facades, and thinking about maybe some questions that maybe not gone unasked, but ones we can focus on, particularly as we are within the facades community, bringing the resources and intelligence that we have to bear towards forthcoming policy and regulation, which I think is super important. And this is some framework for some of what I'm talking about today. Probably most of you are familiar with this, but as operational carbon is reduced, the relative importance of embodied carbon to total carbon increases. And this is, in the context of reducing operational carbon. And if we look at the statistics of what's happened in 2021, the emissions from buildings has actually increased compared to 2020 and 2019, so moving in the opposite direction. And some estimates calculate that embodied carbon will be 50% of total carbon emissions of new construction from now to 2050. And of course, there's a lot of assumptions that are embedded in this, the rate of renewables coming onto the grid, et cetera. But I think it underscores the importance of focusing both on operational carbon, but also embodied carbon. And I think the last is this aspiration that many, maybe all of us, are aligned toward a goal of having emissions of the building and construction sector by 2030 with zero carbon by 2050. This is an important goal, but also one that is a huge reach. And so how do we really get there? But maybe to take a step back for a moment, when I was first approached even to talk to you today about this, talking about sustainability, talking about operational carbon, really wasn't what I had first thought of as a topic to talk about today. And really what kind of changed my thinking was we're working on 2 projects at the University of California, and we were preparing the specification, as we typically do, writing the performance criteria, and we were given a sheet to slip sheet at the back of our section, which is talking about curtain wall and mega panels and things like that. And it had global warming potential targets for some specific materials. And this was, the first I had really encountered the Buy Clean California Act on an actual project. And the Buy Clean California Act affects projects that are managed by the state of California, but that are above a certain financial threshold, but it sets global warming potential targets for specific materials, specifically structural steel, steel reinforcing and concrete, insulation, and flat glass. Not processed glass, so not coated glass, not tempered glass, not laminated glass. But it really struck me because this was the first time, at least in my working career, that I had seen regulation on embodied carbon be a requirement, not a potential credit such as through LEED, not the aspirations of an enlightened client that was trying to do the right thing, but actual regulation and requirements. And if you look into the Buy Clean California Act requirements, they're not so stringent. They're in some ways at the discretion of the procurement agent for the project. And again, this is just for projects that are run by California, but it is the beginning of requirements and regulation that are going to be talking about embodied carbon. And it made me think of, well, what do we actually know from a data perspective on the percentage of embodied carbon that's actually in the facade, and ways that we can actually optimize that. In many ways, I kind of focused on doing the most with the least. And with this kind of regulation that's coming, how do we make sure that good policy doesn't inadvertently result in maybe bad regulation? So that was some of the context of wanting to talk about this today. So early phases of material production and manufacture, currently, they create a spike of embedded emissions up front. And this is often referred to as upfront carbon. Probably not telling you anything you don't already know. But this is heightened in importance because of the goals of trying to avoid global climate warming of more than 1.5 degrees Celsius in the coming years. And I think this spike of embodied carbon in the early phases of a project, sometimes that time is called cradle to gate, or maybe it's cradle to end of construction. But I like to think about it as like in the ground mining the materials all the way to basically getting your certificate of occupancy. All of the embodied carbon that's in that phase can be 75%. There's a range depending on the type of project location, but it can be 75% of the embodied carbon in a particular project, and that's huge. So trying to minimize that at the outset is important if we are going to make some headway towards our climate goals. And industry is actually making a lot of progress towards looking at ways to minimize the embodied carbon in some of the materials that are considered to be maybe the worst offenders: concrete, steel, aluminum, et cetera, a little bit of glass. And I think you can see that different companies are looking at increasing recycled content in aluminum and in steel, also increasing color in glass. And I think Eduardo, Rosa will be talking about this later today. Improving process technology to use better furnaces, maybe to use renewables, et cetera, looking at new fuel sources. Looking at ways to decrease the cement content in concrete products that we specifically use for facades, architectural precast, GFRC, et cetera, and reducing the cement content goes a long way towards reducing the embodied carbon. And even in materials like the silicone that we use, Dow is looking at ways not only to decrease the embodied carbon in their own products, but also looking at trade-offs, et cetera, and offsets. So I think it's important to watch the space and understand what industry is doing to reduce embodied carbon, but also not to let this, in some ways, bifurcate into two paths where there's a thin slice of material that's very low carbon, there's a price that we, to pay for it, and the majority of material is business as usual. So I think as architects, as engineers, in terms of using our voice to kind of push for better materials and faster decarbonization of materials, it's all important for us to participate in that effort. And I think agencies and alliances, national, international, are cooperating in ways that are really fascinating and important to watch in terms of coming to an agreed upon set of standards and requirements. Of course, there's still a long way to go, but establishing a framework that we all share internationally for what life cycle analysis is, and also how we begin to measure carbon in products, for example, through EPDs. But all of this information kind of brought me back to a question of, well, what proportion of a building's embodied carbon emissions is the facade responsible for? And of course, this is going to be different for different project typology, different locations. Is it a project with a huge basement, in which case there's a lot of concrete and steel compared to a project that doesn't have a basement at all? But 10 to 20% seems to be a figure that some of the statistics are kind of focusing in on. So 10 to 15% of the embodied carbon of an overall project. And I think with that mindset, it is the 10 to 20% is a significant contribution, but it's probably maybe half of what the building structure provides. And I think the facade, and I think some of the earlier presentations you've seen today have spoken to this, the facade and the building enclosure has a really unique potential, not only to reduce the embodied carbon in the materials of the facade itself, but also to contribute and really hit above its weight relative to reducing operational carbon. And on top of that, the lifespan of a facade, in the way typical, there's some guidance on life cycle analysis that really posits that a facade's typical lifespan maybe is half of that for the building structure. So increasing the facade's lifespan or service life is another huge opportunity and area for development for facades. So what I wanted to look at is in the typical guidance for life cycle analysis, how is, or where is service life considered in this framework? And it's really in this section from when the building is constructed until the point at which the facade or the envelope would need to be replaced. And what's the guidance on how long a facade lasts? So I looked to the Carbon Leadership Forum. For those of you who aren't familiar, they are a tremendous resource for anything related to this sphere of sustainability, but specifically embodied carbon. And their guidance for the typical lifespan of a facade is between 30 to 35 years. Another statistic or number that gets thrown out a lot is the a theoretical 25-year lifespan for an insulating glass unit. That really is the limiter of how long a facade can be in place before it needs to be replaced. And I think that's kind of interesting because replacing glass is actually one of the few materials for replacement that we really design for currently in the design process. We think about, can that piece of glass be removed? How do you get to it? How would it be lifted in place? So I don't think that the lifespan of an IGU is necessarily the right endpoint for the lifespan of a facade. And this kind of led me to maybe a larger question, or another question, is what is the real, if our goal is to not build if we don't have to build less, to build more intelligently with less material, what are the other factors that lead to the demolition of a facade or of a building more than just technical performance? The facade leaks, the IGUs are fogging. There's also the question of obsolescence. And this maybe is a larger question of the quality of design, how much or how does that contribute to the lifespan of the facade? And these are two totally different examples that I have on the screen. On the right is the recladding of the Javits Center. It's a project that our firm worked on. The Javits Center was built in 1986, and we got involved with replacing the glass and the armature for supporting that glass in 2006. And that project was, I think, a really successful example of a reclad bringing new life to an existing building, existing structure. I think the other example, and maybe it's a polemical one, this is the Hotel Okura in Tokyo, which maybe many of you may know. It was a very famous and beloved architectural project. The south wing was demolished to be replaced with a new wing of the hotel, much to the, there was a huge outcry in the architectural community of wanting to preserve this beautiful building. And in the end, market forces and the desire to make a more modern hotel really led to the demolition of this still usable facade. So how in the end, does facade quality maybe factor into this proposition to increase longevity? Another question is, could embodied carbon, again, embodied carbon in a facade that's used to reduce operational carbon, could that accrue credit the longer a building remains in place with service life? And this is really thinking from a really different perspective at the regulatory framework that we may be walking into or developing if we're participating in it, that it seems to be focused around penalties, sticks. You've got to meet this global warming potential or else there's some kind of penalty. But what kind of incentives could there be? If whole life cycle analysis ends up being the framework where we're really measuring embodied carbon, could there be a credit if the facade is anticipated to last for 25 years, but actually it lasts for 50 without replacement? I mean, this is a more longer term question, but really it's how could credits be thought about in the future? Another question is in the framework for thinking about embodied carbon, and if one of the goals is to use less, And the strategy for doing that is optimizing through engineering everything to be its thinnest, its smallest, et cetera. Could there be a potential downside to doing that? In kind of doing some background reading before presenting here today, I had come across an article that had some, I don't want to say tips and tricks, but it was quick things that you can do to reduce the embodied carbon in your facade. And some of them were really credible and sensible, like thinking about the form factor of your building, the area of skin that's enclosing volume. Makes sense. But there was one in particular that kind of jumped out to me. I thought it was very provocative. It was this thought to relax criteria for visual distortion in glass and say, well, if we're using a lot of thicker glass than what we need to resist wind loads for optical flatness, for aesthetic reasons, is that something that we should give up as architects because it's wasting embodied carbon? And I had a very strong knee-jerk reaction to that. I'm like, no, but it's interesting and it's provocative. But I think the flip side of it might be the additional material, a few millimeters of glass, additional millimeters of glass on a facade, contributes a very small amount to the embodied carbon of a facade, but also is a reservoir for resilience. And so maybe those additional millimeters of glass, in addition to providing a huge aesthetic benefit in terms of resisting pillowing and minimizing flatness, but maybe with more erratic climate changes, maybe having that additional thickness of glass as a kind of reserve counts towards resilience. I don't know, but I think these are the kinds of questions and discussions that we want to be having as we're kind of rethinking maybe rules of thumb that we have grown used to using. Similarly, with rigorous quality control, and higher rejection rates, is this something that we maybe should have a lighter hand with? Should we be so fussy? But maybe not, because maybe the quality control standards that we have, yes, they result in waste, but long-term over the course of the building, they increase longevity. Again, these are trade-offs, but I think we're all starting to think about them with another layer, or slightly from an inflected point of view, once we're bringing embodied carbon into the picture. And I think I've already touched on this, but quality, beauty, cultural relevance, they all contribute to longevity when we cherish a building and preserve it and take more care of it. Is this something that has a way to be included in life cycle analysis? It doesn't in the current models, but maybe as we're becoming more sophisticated in how we think about that, it's something that gets added in. Another question is, what's too big to fail, and what's the right time frame? This is a slide of the Whitney Museum in New York project that we had worked on under construction, and that project has steel panels of 5/16 thick mild steel cladding as a rain screen on top of unitized curtain wall units with an aluminum outer skin and a galvanized steel inner layer. A lot of embodied carbon in this facade. And I will say at the time, this was built, more than 10 years ago, really, the planning for it, embodied carbon wasn't in the thinking, but resilience and sustainability was. Because during this project, Superstorm Sandy hit New York City, so there was a lot of thinking about at the ground level of sea level rise, et cetera. And this very heavy carbon-intensive facade is a rain screen. It can be replaced. The punch windows that you see can be reglazed from the interior. So there was a lot of thinking about the overall lifespan of this building. Could this be a 100-year facade, et cetera? But embodied carbon, I think, adds another layer onto it as to what is too big to fail when ultimately, eventually, it will need to be replaced and whether or not it can be recycled and reused. Another question, how should investments in materials extending facade lifespan and resilience be considered relative to embodied carbon? Something like laminated glass. Being able to recycle laminated glass, we still have a really long way to go, but clearly and its recyclability is starting to be understood, really driven by the automotive industry, where sizes are much smaller than our large glass sizes. But the advantages of laminated glass for resilience, particularly for guardrails and handrails, is really important and necessary, and even in some jurisdictions, we've gotten to the point of not allowing fully tempered glass to be used in guardrails because of the risk of falling glass. So how are we trading off maybe challenges to circularity, the circular economy with laminated, with resilience, added performance, life safety? What about trade-offs between lifespan and toxicity? Some of the processes that we know really expand lifespan for aluminum products and coatings, like chrome pretreatments, or even resins like Hylar and Kynar and FEV. How do we kind of measure, and maybe this is outside of the embodied carbon discussion, but their benefit relative to resilience and longevity compared to their toxicity? And I think what's interesting is some of these very same materials that are in some of the long-term paints that we use, these long-term forever chemicals are in things like basically like batteries that we're using for for electric cars and other things. So it's a really complicated discussion about toxicity and benefits, and also renewable energy. How and where should new technology be incorporated in facades when the long-term performance is untested? This is an image of some of the very large operables at Uber. How does that factor that R&D into embodied carbon and life cycle analysis? Is it considered to be a total negative because it might be years of working on a prototype or multiple prototypes? There might be a lot of physical material that's discarded, but still the investigation, that long-term R&D, has longer benefits that we don't want to give up. All of those amazing studies that John just showed with terracotta, all of that R&D, it's not waste. It shouldn't be considered as a negative relative to embodied carbon, even though it does take energy. How do we effectively not penalize ourselves in forthcoming regulation that somehow R&D actually has I don't say a budget, but is still allowed for and not seen as waste? Because it's not. It's absolutely essential and critical to everything that we do. I wanted to come back to this question I had touched on earlier. Really, what is the percentage of embodied carbon in a facade as a kind of data or reference point? And different organizations kind of capture, summarize it differently, but I wanted to share a couple of them. So the International Energy Agency looked at global energy emissions, and in 2021 estimated that cement, steel, and aluminum for buildings and infrastructure, so that's got infrastructure in there, which is a huge component, 6.4% of global emissions. The World Green Building Council was calculating it as 11% for materials and construction. And Architecture 2030 calculated that in the United States, CO2 equivalent emissions from building materials and construction are 5.9% of total US emissions. So of all of the emissions and embodied carbon for the building construction sector in general, think of facades as maybe being 10 to 15% of that. But where I wanted to end is thinking that, and kind of remembering that the embodied carbon in a facade is very different than the embodied carbon in a building structure, I think, because building structures typically don't also have this other opportunity of reducing operational carbon. So in the forthcoming regulatory environment that we're going to be going into, how do we make sure that devices like physical sunshades are still, we're able to take advantage of the operational carbon that they're saving without getting too much of a negative penalty on embodied carbon? I think the second opportunity for facades that's particularly unique is this lifespan question. So if in the current framework for thinking about embodied carbon, we're estimating the lifespan of facades to be 30 to 35 years, why not set that as 50? What would that mean? Maybe it's replacing certain components, maybe it's building in a slightly different way. I think that is worth investigating as well. And where I'd like to end is that as kind of new requirements and regulation are being developed, one of them, probably most of you know, is Administrative Bulletin 2446. which Gavin Newsom had signed, I think, late last year, which is really looking at setting caps on global warming potential embodied carbon specifically for the building industry. That those requirements and exactly how it unfolds is still being developed. I think that potentially is a sphere where all of us with the facade expertise that we have can bring to bear on making that legislation and those requirements more intelligent and really more specific to facades. I think the other thing that is coming right around the corner is the interim code cycle for CalGreen, which has some whole building life cycle analysis requirements coming as well. So I think maybe what I like to say at the end is let's all pay attention to what's coming and contribute to that to make sure that good policy doesn't actually results in the best possible regulation. Thanks.
Thank you. Thank you so much, Karen, for that information. It's definitely refreshing to see the focus on quality for the longevity of the facade, so thank you for that. So we're just gonna wanna say that we are going for a coffee break. Please, take your time to get to talk to the sponsors, each other, networking, and we'll chime in when it's time to come back. And please, all of the speakers, if you can come for this session, if you can come to the stage for a photo, I'd appreciate that. Thank you. So have fun, everyone. Hello, everyone. Yes, please come in, get seated, get comfortable. Hope everybody got a nice coffee break or tea break or just a break. All right, so to keep with the schedule, we will be hearing from 4:15 Natoma, another great San Francisco giant, I want to say. So we're going to be talking about form, facade, contact, and the urban fabric with our Trent Tesch. He's a design principal at KPF. So if you can please come on board. Thank you.
Hi. Oh, very loud. Sorry. My name is Trent Tesch. I'm a design principal at Cohn Pedersen Fox. And my presentation is not going to be exceedingly technical. And I really wanted to kind of start by talking a little bit about 5M. So there's sort of two sections to this presentation. One is about the 5M kind of master plan process that we embarked on over a decade ago, September 2012, which was pretty remarkable. And really, I'm flagging the key words here that came across in a meeting that we had with Forest City at the time, create an authentic urban realm. The city was really interested in not doing kind of glass boxes, and we were happy to hear that. They wanted a building that had some texture, some character, and then really like make a contextual building. The ask for this project was pretty big, right? Everybody can see the density and the scale of the ask. And so, we really thought hard about the context and the adjacent relationships. And it's something that I'm very part of my architectural practice, personal practice is really about making those connections, those social connections, physical connections, all the different ways that we can leverage architecture to make these connections. So you can see on the site, Mission, Fifth, Howard, Natoma is very important. It sort of became the front door of the building. And then we had these view corridors that the city was really interested in maintaining. I just want to show you a little bit about the adjacent sort of immediate context. Cameline building is right in front of the building. Chieftain is sort of embedded in the corner of the building. We had a lot of discussions with those people. The Tempest Bar, you can see on the corner, there's sort of an interesting kind of urban gathering place for the community there. The Dempster building, I always called it the Let's Go Giants building, but it's the Dempster building. Chronicle, and then the Mint. I think all these buildings kind of added up to give us a sense of the character, the flavor of what we were trying to achieve on this site. And then this was a really interesting diagram for us that spoke to this idea of an office building kind of in South of Market, having these two conflicting scales, the sort of smaller scale of west south of Market, and the larger scale. Obviously, our building is sort of a large office building, and how these two came together. That was really the story for us. That was really sort of the important part of what we were trying to do here. And then I just, as part of any project, architects love to research, and we love to kind of dig up interesting thoughts or discoveries that other people have done in the region. And Janet Delaney produced this book of photographs that she took in South of Market in the 70s and 80s, and that book kind of gave us some hints or some clues about the history, the character. This idea of a place that was light industrial created a lot of there was a lot of makers in the site, and a lot of artists, a lot of crafts people that created that made a lot of things or fixed a lot of things, and so it was this industrial character that we were really interested in. And then obviously, big part of our process here was really analyzing the site, finding the fabric, really understanding, trying to figure out what the fabric of the site is. And that was something that we explored a lot around the neighborhood. Specifically, we were kind of like asked by the city to kind of really look at the Caesar Pelli building, the J.P. Morgan headquarters on Mission Street, as an example of a building with a lot of texture, a lot of character. They seemed to really like that precedent. We were enamored by the Pacific Telephone and Telegraph building and the kind of elegance of that historic texture. And then the Snohetta building was under construction when we started, but this dialogue between one building with two kind of components that kind of came together to create this sort of idea of a museum. And then these are really, I just wanted to show you a little bit, kind of show you behind the scenes a little bit of our process, and thought this would make it sort of the presentation a little bit more interesting. We produced an array of options, slab buildings that had a dramatic cantilever. Sort of the one in the middle was sort of a two-part kind of tower that had a plan juxtaposition and a section juxtaposition, and then tapered form. But they were all sort of like trying. Our goal was to make something that felt like it was would be well received in South of Market as a large kind of commercial office building. And so, they said, think outside of the box, really come up with some dramatic ideas. So we thought about color, pattern, texture, all of these things that kind of make a building feel more human scale. And after all, that's really what we're trying to achieve, is to take something that is quite large and reduce the bulk, reduce the scale of it. So some examples. These are things that I thought were kind of interesting, thinking about South of Market, thinking about, could we make a building that could it reflect the South of Market? Could it somehow respond, the different edges of the building, could it respond to different parts of the site? And so this imagery was really important, and I think it felt like the right kind of character to try to achieve. And then, we created these diagrams early on about, originally this kind of asked to do a big, beautiful box. We thought about, the typical footprint of an office building in San Francisco is about 15 to 20,000 square feet, something like that, very delicate. And our building was trying to achieve much larger floor plates. And so we thought about this idea of taking two buildings and kind of butting them together. And this was sort of the process on how we did that. And really, like, what is the character? Like this idea, these two forms that are coming together and making a singular piece of architecture. We weren't trying to fool anybody with the scale, but we were just trying to break it down so that it felt more comfortable on the site. And so this was sort of what we produced. And I think, to the building in the foreground was something that I think got removed through several community meetings. And really you can kind of see a little bit of the two-tower concept in the back. We created a document that was, we didn't think we were going to, we didn't know we were going to design the building at this point, but we created this sort of guidebook that allowed whoever was going to pick up on the work. We were just engaged in the master plan at this point, and we created a sort of a document that was sort of a guideline of all of the design elements that we worked through with the city and the client. And so really, 6 years later, we were asked, and through kind of a negotiation, we won the commission to actually do the office building. And so we started to think about what that was. We dusted off our diagrams. I think there was a sensibility about color and craft that we were still really interested in exploring. You can start to see a little bit of the fabric that is emerging in the diagram of the building. We originally thought about terracotta on the sort of the smaller of the towers, painted aluminum, sort of a white, delicate figure on the tall building, and then we introduced a secondary or a third element that was an interstitial fabric for the podium. And the podium was something that we felt it was really important for us to create a podium that had a lot of scale change, and that had to do with the existing fabric that I spoke about earlier. The goal of this project, and I was just talking to Ron Klemenchek, who was the structural engineer of this project, was to really make this building as lightweight as possible, and that was part of our sustainable agenda for this project. I think he just gave me a metric. He says volumetrically it's lighter than balsa wood. It's about 50% lighter than a traditional concrete core office building. So it's a steel externally braced building, but that was really our goal, was to make this as lightweight and as delicate on the site as we could. And obviously, this building was built during COVID. So these are photos. Enclose was our consultant for the facade, built in China. And then really just sort of give you a sense of what were the fabrics that we employed and around the site, around the base of the building. There was Mary Street was a really important street. So we employed this idea of a very kind of industrial brick. But as it turns on Howard and Fifth, we kind of thought about interpreting that in sort of a fritted glass idea. Again, that goes along with the notion of the two parts of the project. And then here, I think the key, the urban move for us was really this idea of locating the services core off of Natoma, which we located the front door. Instead of being on the major grid, we kind of made the building feel more intimate by connecting to the minor grid of the site, and this is the entry on Natoma. We wanted to kind of, indoor-outdoor was really important to us, and so this idea that we could take the front door and kind of open it up and really allow the community to filter through, again, that idea of social connection. The lobby is not a traditional lobby. It's a very social lobby. There's a restaurant being planned for the lobby. And if you've walked through it, you can kind of get that sense. It's a different kind of office product. And then, so looking back, you can see the Tempest on the right-hand side, and we collaborated with Iamoto Scott to do the fit out of the lobby, the character of the lobby. And then going back to that, earlier, industrial kind of image that I shared, this is what we were trying to achieve. We were trying to make something that felt like it was, you know, part of the history, part of the fabric of the market. These are more kind of close-up views of the corner, really playing up that idea of the industrial aesthetic. Really wanted it to be responsive to, it was sort of like our dream was to kind of make this building feel like it was responding to various different sides, various different elements of the site. So that's where we came up with this idea of this horizontal brick. We thought about the Boda building, the MoMA, and thought about that horizontal texture. Thought we'd pick up on that, but in sort of an industrial kind of way. And then this is a view along Fifth and the Chieftain, and the amount of effort that we put into kind of relating to the various cornice elements that happened. It was something that the city was very interested in us doing, so we kind of try to maintain that kind of scalar relationship. But again, you can kind of see the goal was to make something that felt very distinct. It didn't feel like a traditional sort of singular gesture, but really it was sort of a form and a fabric that responded to a lot of different scales and characters. And there's two big kind of amenity decks in the project, one on the 10th floor, which is the plan here, and then the one on the top of the building. You can kind of see how that's laid out. In the plan, you can see here, the thing that makes the building so light is this braced frame that goes around the perimeter of the building. And because the core was offset to one side to maximize the flexibility of the floor plate and the views to the bay, we needed to find that core is not absorbing any of the lateral loads of the building, but it's the steel braced frame that is managing all of the lateral and the seismic loads. So it really is a very lightweight building. And then you can kind of see we were really interested in the climate and how we can make sure that people have access to the outside world. That notion of when you breach the perimeter of an office building, how that reduces stress and keeps your it makes you actually feel better if as opposed to being stuck in an enclosed building all day long. And at the top, we only have some renderings here, but you can kind of see how that space has been imagined. And then looking again, the bay view is really important to the planning of the building, the logic, the intimacy at Mary Court, and then this sort of expansive view on the other side. And then just other views that you can kind of see in the facade. We were really interested in this idea of maximizing the difference between the two forms. And so you can kind of see, even in the glass technology, the white tower has a different, it's got a glass that is a little bit more transparent, a little darker, that contrasts more with the white fabric. And then the shorter tower form has sort of what we called an aluminum baguette. It was kind of trying to mimic a terracotta shape, but that it was, again, it's sort of idea of lightness around the building. You can see here, one of the things that I was really excited about was trying not to have a 5 foot module or 5 foot mullion across the floor plate. So we came up with this idea of doing a sort of a 7 and 3, which is the 10-foot, the typical office building 10-foot module. 3 feet was a good dimension that we could actually insulate that panel behind it. You know, if you go tighter than 2 feet 6, you can't really insulate the facade. So that 7 and 3 gave us this idea of kind of clearing out, making an expression that has no kind of mullions. And we get this bigger piece of glass. So it's a bigger than a typical module, And so that's something that we were really interested in exploring. We didn't want to do this. We wanted to create sort of kind of a window frame in this building from the inside out. Again, you can see the technical details of that other wall. They're all basically the same form. Each unit is roughly the same form, a 7 and 3. The horizontal has a little bit deeper spandrel, but again, it's 7-3. This has more glass. The horizontal has more glass because it's only clad at the column. You know, and again, I want to reiterate that this idea of how we tried to make a building that it was sort of a very large ask, but to try to make it feel as human scale and connected to the district as possible. So this is my last slide. I think we tried to craft a building that spoke to South of Market, but still felt like it was a very interesting form and a shape that would fit in with San Francisco's you know, important district. So, thank you.
Thank you so much, Trent. Certainly, I agree that it's a very well thought solution to really pick up from the current fabric, the current aesthetic, and just overall scale, and just bring it up a notch. That's very, very well thought. Thank you so much for explaining that detail. And just next up, we will be talking about, we'll be bringing up John Picard, sustainability expert with HALIO. And it's interesting to just listen about electrochromic glass and smart glass. And I think that what a better way to really just let time pass by and adjust itself, right? So take it away. Thank you.
Hi, you guys. They told me I can't walk out here in front of you. So for the next 20 minutes, I am your personal disruptor. I love the buildings. I love the design. I love the engineering, the materials. I'm here today because I wanted to be. And I never thought I'd be in front of a room that just had to deal with something this specific. And I've spent the last 30 years in the Valley and building and working in the sustainability space, looking for the 10 things that could impact climate and the 10 biggest climate solution technologies. And facades is number 3 on my list. Number 1 is generative AI, meeting biomimicry. Number 2 is the battery physics and chemistry that we don't have today that will unlock wind and solar. They're telling me to get back on the stage. I just wanted to be close. So, and this cover shot, that wave, when I asked my team, I said, put a big wave on there. So I'm a surfer, not the greatest surfer. My kids are way better. My kids are ripping. I suck, but I go out and sit outside and I wait for the wave of the day, the biggest waves. I surf big waves. And what that taught me about my work in climate and sustainability is when you ride something like that, and when you are paddling, you are going all at it and you don't hesitate. And we're in a climate situation right now where we can hesitate. And I'm here today to say to you guys as a group, as an industry, that the skin of buildings, whether it's glass or terracotta, or it's electrochromic, or it's solar, or it's paint, the future for you guys is unbelievable. And if we can deal with the radiant gain and the impact and the heat and all of the things that are coming at our buildings at that skin, at that nano level, and if we can digitize that, and if we can geospatial that, we can change things dramatically on the energy profile on the planet. So we got to go after big waves. My wife says, why don't you pick an angrier picture? You know, I'm in the construction business. Everything's a low bid. Nothing. We're sitting in a pile of low bids, and that's got to change. So I've been a builder for quite a while. I built some of the most expensive homes in the world, The last house I built, the electrical bill was $75,000 a month, and they weren't home. And their water bill was the #1 water bill. So I built $150, $200 million homes that looked like this hotel, had the operating costs of a hotel. My client dispatched me out to try to find things to lower that cost. On the way back, the pilot said, "You're the only one on the plane. We got to test the engines on the jet, so go service it in Atlanta tomorrow. We're going to go to the ceiling limit of the airplane." And we went to 54,000 feet. They rolled over. I got to see the curvature of the earth. And when I landed, I severanced my company completely for a year. Traveled the world to see where we're at our best and where we're at our worst. And I came back to building. And I've been focused. I think you, as an industry, the whole built industry, designers, architects, engineers, you're at that crossroads. And I hope I can help you with some direction. So the valley is, you are 50 miles from the biggest exponential solution set of tech in the world. The facade industry needs to race to meet NVIDIA. You need to race to meet OpenAI. You need to race to meet all these new software engines and all these new sensing nanomaterials, because this is the next generation of compute. And now let me threaten you. The things that you're about to see with AI and chat, they shouldn't have come out with it this quickly. It's going to run over everything. Back office, call centers, most lawyers will be gone. Maybe not all, but most. There's a lot coming. Buildings, we've just come out of COVID, and now we're running into this situation where the workplace is going to be completely undefined. So what do we do? And the tipping point of climate is bearing down us. We are not hitting our numbers at all. And so I decided to be an innovation catalyst. You should be an innovation catalyst within your space. I decided I was going to be a climate solution architect. You can be that as well in your space. And so here we are. And if I had the 45 minutes that I normally get, this is the slide that tells us the doom and gloom. Living systems are in decline. Rainforests are depleted. Oceans are changing. Right here, when the ocean temperature changes 2 to 3 degrees, the pumping cycle stops, weather systems change, it's over. It's done. For your kids, their kids, and the next kids. And this generation, you, us, now. This is the tipping point. This is where we have to get traction on this. And I don't think there's anybody in my space, if I said, "Oh, I'm going to go speak to the facade industry today," they're like, "Really? What about?" About your damn importance. You're one of the most important technologies in the planet, and you have so much potential to change the physics and the chemistry. Think about every surface as a solar gain. Think about every surface as being able to store energy. There's so much that can happen in the labs. So species are going extinct. The food chain, planetary boundaries have been pushed. The Earth's warming, and most importantly, we exceeded the carrying capacity of the planet when we were at 1 billion people, because the Earth could reclaim its waste, but it can't today. And so we need all hands on deck, heading to 10 billion people. And the last 3 or 4 speakers were speaking about embodied carbon and life cycle. We need to build buildings that last 1,000 years. We need to build buildings that the recyclability of materials was designed in, not sort of wandering around at the edges of all this. There's so many things that we can do if we dedicate ourselves to this. So the other slide is the reverse of this, how amazing it's going to be. And I wish I could show you that, maybe next year. So nature is weaponizing. You're going to see ladder effect fires start in the landfill in Tijuana and end in Washington. Everything will become fuel. You're going to see superstorms like we've never seen before. You know what it's going to do? It's going to change the risk profile of this planet. Things will be, you won't be able to insure 1/3 of the real estate in the world in 30 years. So what do? We have to rethink and reimagine everything. Your future is either happening to you or for you in your industry. And the way to have it happen for you is to get really creative right now. Really creative. So rethinking cities, rethinking airports, rethinking data centers, rethinking offices. This space is where I get my cheat sheet. There is more going on in data center design and engineering than anything else, than those three combined. That's the edge. That's where I mine these big cycle ideas. Even white paint was reinvented this year. How white can white be? It can be white and whiter. 3D printing. I'm 3D printing my house in Maui next year with a KUKA robot 6-axis arm printer with two materials, water, the #1 moved material in the world, and #2, cement, with graphene mixed in. And I am using a design engine, it's a generative AI engine, speaking to a biomimic code, looking at the natural landscape of where my house will be, and says, this is what your house should be based on that, as if nature were to do it. We don't know what that's going to look like yet. We'll see. Mass timber, net zero buildings. That was my first project here in the valley in Sunnyvale. The air conditioning hasn't come on in 7 years. The 2 times that it did, it was a mistake. We can do this. This was a racquetball court. This is energy positive now. This thing clicks pretty slow. So this is where I see you guys. Sensing the skin of buildings, being able to tell the weather at the nano edge, like what's the temperature, how's it changing, what's it moving. Just look around and just imagine if all the skins of the buildings could communicate. And I've been working in the electrochromic glass for a long time. I worked at Sage when it was a mom and pop. I went on to View and rode that wave for 9 years. It was hard. And I could have quit any time. I didn't, because I believe that dynamic glass, things that can phase change and can block radiant gain at a nanomaterial, is where we need to fight the fight. Facades are incredible. You guys are positioned to be a solution, a big climate solution. And I love HALIO because of one reason. It switches quickly. It switches in seconds. And I'm thinking, what do I do now? If the glass switches in seconds, can I get it to talk to the light? Because the lights are all IP addressable. Everything's in the cloud. There's artificial intelligence is going to drive all that connectivity. That goes back to the utility. And now I've got this big communication at the grid, and I can control the city. And when you pull that back, and when you see where the most impact's going to happen from, it's on the skin of the building. That's what could drive the connection of a city. So we've got to reimagine batteries and battery chemistry and wind and solar, transportation, planes flying on batteries, planes flying on hydrogen. The digital twin of everything is what's going to unlock the transparency and the truth of real engineering. And AI is going to come along and they'll say, I want a 20-story building on the corner of 2nd and Main. I want a homeless shelter. I want a low-income house. And those designs are going to be unbelievable. And why wouldn't we say today, generative AI, design me a building with a facade that's a climate solution product for the next 20, 50, 100 years? What would that look like? Conductive cooling is a really good example of an industry that's just a major energy intense situation, but they've been able to remove 70% of the energy cycle from cooling in data centers today, and it's driving change in the cooling industry. The Omniverse and the Metaverse, when you get a chance, go to NVIDIA, look up the Omniverse E2 engine. It's the beginning of an AI engine that looks at the climate weather pattern in real time. But Omniverse is going to see every cubic inch, every cycle of energy, every cycle of operation performance of everything that is on this planet. It's just a matter of a few years to see that. And follow NVIDIA as a company that will be a $1 trillion player. Their stock went up 26% this week. And this is a company 10 years ago that was almost bankrupt. And if you guys don't think you can go from zero to like unicorn space, you're mistaken. It is an absolute moment for you to be that. So rethinking and reimagining facades. It's way more than aesthetic. It's a critical building component. The energy efficiency at the edge is a major plus. The significant climate solution aspect of you will drive big investment dollars. The money that's coming into this space is extraordinary. So one of my slides shows these little cubes. First one in the corner is a white cube, 1 by 1. It's a $1 trillion company called Amazon. The next one is 80 cubes. It's the GDP of the US. The next one's like 140. It's the GDP of the world. And the rest of the screen is 270 blue cubes, representing $270 trillion that's got to get aimed at solving for the fact we exceeded the carrying capacity at 1 billion people. That's what you should be aiming for. You should be designing for your importance. You should be designing for how powerful a solution you are with buildings. It's not just the buildings. It's this symphony of connectivity of all the materials energized and that intelligence. That is going to change the portfolio value. I'll give you a prime example. Brookfield's one of my biggest clients. They gave the keys back to 2 office towers this week. They also called me and said, we have a $17 billion fund, and we're going to clean up manufacturing around the world. Where do we start? I am telling you, this is going on now, and it's an exciting time. So sensing and connecting is where you start. Call Esri, talk to any sensing company you can get your hands on, and start looking at the possibilities of pulling data, digitizing these skins, and starting to see what that is, and starting to collaborate and experiment. Go to MIT, go to Georgia Tech, figure it out, but do it as a group. Not all you guys separate in the hall, all you guys working together. That's how it's going to happen. That's what will accelerate this. IoT and digital twins and Omniverse are not going to go away. They're going to accelerate and expand. And generative AI and machine learning, it's in its infancy, and it's a new form of compute. You don't need to understand it. It is 1,000 times what the internet is. You guys remember when the internet hit? Remember? This is 1,000x of that. Am I going over time? Am I okay? Got one, what? Oh, I got 11 seconds to tell you guys how it's going to go. So here, HALIO. And again, I told you why I'm with HALIO and Viracon. Viracon is going to help this company, HALIO, that's not at scale and accelerate this important technology. And you all should be collaborating with them because they already have a product that switches, that connects, that's at the edge. And their nanomaterial that they print, it's activated, it's incredible. You guys could cooperate with these things. So the high-speed switching, the rapid phase change, and the building systems connection, all of this is a huge climate change catalyst. And I'm funding stuff. I just started a big Applied Frontier Fund with X and some other founders, and we're only looking at alpha technologies. And the reason I would invest in HALIO today is here, here, and here. And this is what your client wants, right? So how do you go to a developer today and say, I want to take your whole portfolio and I'm going to increase the value and I'm going to help you meet your carbon equivalent, and you're going to be there. 2 years ago, I got asked to green the Rolls-Royce. An impossible job. They put me in Chatsworth at some house. They shot a De Niro movie by the pool with really good-looking people spraying Evian water on me while I looked at 2 Rolls-Royces. And I got done, and Ian Robertson, the CEO, called and said, how's it going? I go, it's a shit show. I have no idea. It's a disaster. You got a boat with wheels. There's more chrome on the front bumper than 10 any other cars. It's not going to happen. 6 months later, I get asked by Ralph Lauren to green Ralph Lauren. I'm in the elevator. I'm wearing his belt. I'm wearing his jeans. I've had the jeans for 15 years. I've had the belt for 10. I get off the elevator. He says, how's it going? I said, I can't do the job. I go, why? He goes, why? I go, your sustainability is already in the quality of your product. I'm not going to tell you how fat you are and what you have to do. And I woke up the next day and I called BMW and I said, spend $50 million in the supply chain and make the car the trophy, the monument of that change in the supply chain. And that's what they did. They didn't touch this luxury brand at a time when Prius was driving Julia Roberts to the Oscars, right? And the Wilshire Hotel canceled their orders. And now the Rolls-Royce became the driver of change in the supply chain. So look at your supply chain and drive into it, fund it, incentivize them, inspire them. Go and ask them if they can make the metal at night off peak. Go and ask them, can we use electric arc ovens? Go and ask them, can we model for our next generation materials? It's about being creative, guys. It's about taking risks. It's about realizing that you as an industry, and I'm predicting all the time. I'm always telling people what I think is going to happen in 4 or 5 years. When you Google me, you're going to see that. And I'm telling you now, you're a very important trend. I wish you all the best. We need to work together. Thank you.
Thank you. Yeah.
Sorry, I went over.
Yeah. Thank you, John. Thank you for that inspiring talk. Took me a little by surprise. I definitely agree with you. Nature is definitely a way to go to really hone in for innovation. You must be geeking out in cephalopods, right? The immediate adaptive nature of them. And just to add a little bit to that, yes, just looking outside of these 4 walls, current, like what we can look to for inspiration is just outside there with nature. And we're just tapping into the surface. So excited about the future based on what's present in time. And that evolution of genius is what we have to look into. And speaking of evolution, the next talk will be, it's a amazing design firm that has evolved their ways into a very interesting geometry. And I'm excited to hear about Kerenza Harris. She's Associate Principal and Director of Design Technology of Morphosis. So she'll be presenting an interesting talk on how that evolutionary technology and design in architecture. Thank you.
Hi. Yes, thank you very much for your introduction. I am Kerenza Harris, and I do work for Morphosis. My specialization has always been towards bringing technology in kind of the supporting of a certain vision of how we make architecture and also how we deliver and make buildings. That has always been my focus throughout my careers. I'm also teaching at SciArc in Los Angeles as well. Very important to kind of bring these two things together. So today, what I wanted to kind of go over a little bit is the way we work, how we have evolved in the last few years, and the type of work that we do together. So our main offices are in the Culver City area. We built this. It's a net zero facility. It was the largest actually office in the LA area to have a net zero capabilities, and we have about 60 to 80 employees depending on the year. And what's really characterized the type of work that we do in the last, I would say, 5 to 7 years is an evolution towards kind of diverse types of projects that we work on. So as you can see, we're kind of spread out internationally. We have some kind of permanent offices, but we also have a lot of satellite offices that support locally each project where we want to have a presence or a physical presence there. And again, some of the kind of variation of work right now, the range has really grown, right? So we work on regional planning, city planning, master planning. We also work on large complex of architecture, like with several buildings on site or singular building. And then we've also kind of broadened our interest in variation in typography of buildings and also programmatic requirements. We always have kind of this environmental condition that we're trying to respond to, and again, because we operate very much around the world. Now, we do have an interior team of experts that kind of do the same job that I do on the exteriors. And so we're kind of bringing the architecture both from these two kind of major kind of component, interior and exteriors, to kind of bring it together as a performative composition. And so I think part of the reason why we've been able to expand a little bit of our interest in the things that we're testing or getting into is really because we have, number one, an approach that's very systematic to the kind of composition of the architecture, meaning that every input, every condition that we want to kind of bring in is looked at in a very kind of systematic way, and they all come together and interplay within the final composition. And obviously, this type of approach to the making and the fabrication, as well as the use of the architecture, has to be kind of supported by a pretty sturdy infrastructure that is kind of digital-centric in a sense. So we have to somehow find a way to kind of organize internally how the firm operates on the digital front in order to support and allow the kind of the design to evolve, but also to respond in maybe more extreme conditions, environments, and requirements, right? So I'm gonna show you a little bit of like internally how that kind of translates, and then I'll show you a case study, which we've talked about today already from Boston Valley. But again, this methodology is supported by a very kind of strong centralized network of kind of digital and non-digital elements, right? So what we're trying to do is create like an interface between analog and non-analog information, and everything comes into play at the end in this kind of like global element. And it could be results of analysis, it could be data, it could be sketches and everything. Now, in terms of design software, or architecture software, we are quite open, depending on what's needed for what project. And so part of the genius behind this whole thing is that we are really kind of focused on interoperability. So internally, what we're doing is that we're allowing a certain freedom in the tool usage to get to to the final product, but we're providing some kind of interoperability between these elements. The other thing is a more classical approach here is that we look at the architecture as being kind of like driven by kind of an infrastructure of drivers. And the drivers may be the things that rule the lines of the project or the grids or the datum, anything, and then sometimes it's kind of just a database, but that really kind of organizes everything. And the projects themselves start very much in this environment, which is like a mass, right? And the mass evolves, changes, and is morphed depending on the condition that are either external or internal condition. And then on top of that, then we're creating these design surfaces with those solids or these surfaces, and every system, a structural system or a facade system in this case, come in and they get kind of attached to that initial mass model, right? So it's a very much like a kind of a sculpting approach, but the sculpting obviously is based on very kind of rational sets of conditions or requirements depending on what we're looking at. So this is just one example of these interoperability tools. Sometimes it's a plugin that comes in already packaged and we can do that. This particular one goes from Rhino to Grasshopper to CATIA. And what we needed to do here is that we had a designer designing a desk, a very fancy one, in Rhino, and then we're using Grasshopper to rebuild the desk natively in CATIA, because CATIA is going to be used for the more kind of higher level of detail and the construction document phase as well. And so we don't want to lose if there is any intelligence that's kind of embedded in the geometry or the geometry itself. We want to be able to carry that information back and forth. The more we facilitate this movement between the different software allows us to have a very iterative process, which means that very quickly we can study a large amount of solutions, and because we are embedding like the performance criteria within each of these kind of little problems. The iterative process is giving you 1,000 solutions, let's just say, and every solution operates on the same level. They all have the same level of performance. And so we're kind of allowing the designer or the kind of creative process to be released a little bit, because the choice doesn't really matter. It's going to be performing at the same level. And this kind of driver, massing, these types of operations really become the DNA of the architecture. And it's not, I mean, obviously we often show the very complex one, but it applies globally to everything. I wanted to show you this project. It was in 2019. We went to the Milan Design Week and did an exhibit, an installation for Dassault System. And this one was like the perfect little research project where we created a digital twin of the exhibit and did a simulation for everything. So we choreographed the visitors. Inside of there, you have rotating panels that are timed, that have a certain content, digital content in them. There's also a sound component. So the digital twin was giving us instant feedback to all the things that we were testing. And again, we're testing form, experience, sound, and different types of things. So it was really helpful for us to be able to combine all of that in something that gave us feedback immediately. And it was used for not only setting up the exhibit and all the components that are with it, but also the kind of fabrication process and the mock-up for the performance of the projections. So we created our drawings from there as well. And this was really a great opportunity for us to work with in a very short amount of time, but like just putting it all out there and say, okay, we're gonna go 100% with certain types of tools and test these out and see what comes out and how we can reintegrate that into our process. Now, the content of the exhibit was our content, which is our digital waste, in a sense, things that occur during projects and that we never use again, that nobody ever sees again because it's done. And so we were recycling our digital information. Within this, it was a little bit meta in that sense. We also went ahead and created an app for this one that people could just download. It's interactive, so whoever's in the app at the moment could interact with each other. And it allows us to extract from this digital content some of the one-to-one panel on the facade, for example, or physical model one-to-one as well, or some pictures or footage from the actual projects that all of this other content was extracted from. So that was a really interesting kind of applied research, and for us to try to find ways to reintegrate that in the workflow. So the project that I'm going to use as a case study has been mentioned earlier today. It's going to be the Orange County Museum of Art in Costa Mesa, California. And for us, it was a really interesting one. It just opened, so I thought that would be interesting for you to kind of get a quick look at this. It doesn't have a parking, so the kind of urban planning and the kind of pedestrian circulation around the site is very important for us. And the other kind of big move, let's just say, is that you essentially have a large box at the bottom, and on top of the box, we've kind of elevated the site, and so we're giving back about 70% of the footprint to exterior event space and green spaces as well. So there's a little bit of like a bigger picture effect that we're trying to bring in as well. Now, working very closely with our client who really wanted a very expressive type of architecture and really treating it almost as a sculpture as well. And again, these would be the image that you see in magazines. So these are like the atrium and the entrance and the store, highly articulated pieces, and then the actual exhibit spaces are much more performative in the sense of what they need to do. So it is a couple of rogue pictures here, but the front is the pictures of the different exhibit areas that they have, and in the back I'm just showing you a few models. The competition, it was a competition that we won in 2008, and after that there was a few years where the client was doing a lot of fundraising and also settling the program. And in 2018, we actually started the project in earnest from schematic design phase. And so this is kind of where we started a little bit. So you can see there's a big box at the bottom. There's a bar building or a box at the top that ends in a kind of articulated element. Now, again, the majority of the building is very much kind of regular, orthogonal, and repetitive, and then we only kind of dial up certain areas where there's potentially more public interaction and needs for something a little bit more expressive. And again, the relationship here is we have a series of primitive drivers and surfaces that are a design surface, which guide every single architectural assembly inside and outside. The structural system is a steel structure, and then we have a few shear walls and a couple of cores that are concrete. But again, the box on top of a second box is really kind of basic. And then what we do in these particular cases are we scope out the areas where we're going to need a little bit of digital support in excess of like the just typical project. And you can see this red line is actually identifying where that intervention occurs versus where it doesn't, right? So we, in this particular case, kind of separate all the exterior assemblies and use them or put them in kind of this higher level of kind of oversight. The original idea or concept, one of the large concepts from the competition were to have these horizontal lines crossing something, right? So there was a lot of material research and systems research, trying to figure out like what would be the best, the most appropriate for what we were trying to do. And as you heard this morning, we got together with Boston Valley when the choice was made to select the terracotta. And as he mentioned, we did some of the workshop with them. And for us at this point, we're like, tell us what we need to know, right? Like, let's go and let's understand what we're talking about. Let's understand the material, the behavior, the pros and cons. And we came in already with a design that we wanted to do, a super articulated tile. And so at the end, we ended up choosing a tile that was more regular in terms of like flat in a sense, because we already had a really expressive mass, right? So adding more pixelation or articulation on top of that was not necessary. But one of the major component here that we kind of came up with is that because it's an extrusion, we want to have the panels stay rectangular, 90-degree angle, 12 inches tall, and have variation only in the length, right? Which means that it has it has to follow certain sets of rules as it goes around eccentric geometries, for example, right? So once you apply these rules to the behavior of every tile, you are starting to see, like in the areas where the architecture is highly articulated, the tiles automatically start to redirect themselves to kind of maintain their kind of single curvature or no curvature, and we start to have a flowy pattern, which is exactly, I mean, completely linked to the nature of the geometry. So the way we did this, you can see here we have these driver surfaces that define everything. The driver surfaces are smart, so they understand what they are, where they are, and they can be described in a series of control point or wireframes. And they're also very much aware of their different states, right? So what I'm saying here, for example, is that we have a series of three-dimensional surface in space, and then we're telling the surface to unfold themselves. And so all of these surfaces unfold themselves in a very specific way on the ground. And then what we do, we run a second set of script that deploys the wireframe of the tile directly on the ground. And the wireframe is driven by all these rules that we just talked about. How does it hit the cylinder, the size of the tile, and each of these wireframes has a certain relationship to its neighbors and to the geometry that's unfolded. That's like a zoomed in version of that. And then we're telling the surface to please take this wireframes that you have on your unfolded state and please fold that back into your folded state, right? So that whole history now is a real-time process that allows us to kind of connect these two pieces together without having to erase and redo. We're just evolving a model. It's important because obviously if a designer changes one of the geometries of the building just for any reason, it's going to affect the entire pattern everywhere, right? So you can't really afford that. And then it also allows us to kind of optimize and work with again, the fabricators then understand better what what works best or doesn't. And then now these tiles that were wireframed and surfaces now become three-dimensional solids, right? Because obviously material has thickness. So we want to make sure that the kind of architectural assemblies are tracked throughout their kind of the different layers that make up this assembly, so that we are kind of due diligence to really make sure that we understand what we're proposing here. In this particular case, you saw a mock-up this morning. We did PMU's performance mock-up, but we also did visual mock-up for this one. And then the color of the terracotta, the color of the glazing, the texture on the tile, all these things are part of this kind of global design overview. And then when we do exterior facades, we usually in our set have individual sheets that kind of give you a map to the whole system. So here, by just looking at this one sheet, you can understand the pieces of the puzzle, a general idea of like what we are proposing or presenting to you, and then you go through the set to the different details or other types of drawings that you may want to look at. So you can see our waterproof wall, which is black in the background, and then you have the clips in front. The tiles were delivered to the site uncut. They're all obviously the same width, but they have a certain length, and then they get cut on site by a subcontractor was trained for that if there's a corner or an opening and things like that where they have to adjust. And you can see that some of the models, either from the fabricator or from us, are getting really detailed in certain areas. You can see here we have the structural steel, and then we have the infill aluminum studs in between, and the steel is kind of supported by this curb area around the edge of the slab. This is the picture, again, that you saw this morning, a very much kind of a layering effect of all these different pieces of the puzzle. And these gigantic beams here, which are tying the classroom and the rest of the building together, become kind of integrated within the bridges in this case. So I think what, the lessons, again, of kind of where we go through, and it's an evolutionary process for sure, is to really try to kind of leverage certain types of technologies, stay on top of what's going on out there, and really try to make some of the processes faster and more intuitive, because that releases us from the final product, right? Meaning that again, if we're able to kind of create a series of solutions that all have already embedded into them the performance requirement, then at the end of the day, we can deliver a piece of architecture that has all these components integrated into the final composition. Thank you very much for having me here today.
All right. Right, thank you so much, Kerenza. While we set up with the chairs, I should not get close to that. While it's quickly set up, there's any questions? I know there's not like a Q&A, but if anybody had any questions for Kerenza or any others, this is the time, perhaps. If not, it's really interesting presentation overall. Thank you. Certainly, those joints, the way that I laid along with the studs, were definitely a journey to go through. So now we're going to be presenting Dr. Isabel Paparo. She's senior engineer in Arab, and she will be the moderator for our next panel, where building a resiliency to wind and seismic conditions will take place. So take it away. Thank you.
Perfect, thank you. My name is Isabel, I think I was introduced. I work for Arab, I'm a facade engineer, and I'll be moderating the panel today. We are talking about designing for building resilience in wind and seismic conditions. And I have with me on the stage Jeffrey Haller, who is the founding principal at Haller Architects. Then Roy Denon, who is the senior principal and vice president at CPP Wind Engineer Consultant. Ron Klemenchik, who is the chairman and CEO at MKA Structural Engineers. And then last, Vince Polemos, who is the vice president at pre-construction at Waters & Wolf. So thank you for joining me. And we will start with like a couple of slides. Everybody gets a chance to introduce their own work and themselves. I don't want to take that away from the group. So let's start with Jeffrey, and you can go ahead.
Okay, thank you. So we're going to talk quickly about a project we did here in San Francisco, 181 Fremont, and the slides are there, right?
I'm clicking for you.
Oh, I can't see that thing. That's all right. So what's unique about this project is it's a mixed-use development. The bottom two-thirds are office, and the upper third is residential. There's a gap between them, which is an amenity floor, which divides visually the building. Also worked as a unique wind reducer or wind changer around the building. Next one. The exterior of the building, as you can see, is done in a sawtooth. That was done for passive solar reasons. So as the sun moves around the building, it hits the metal mullion first and it gets to the glass later. And ultimately, that passive design created a reduced 6% in the solar load factor on the building. Next one. The building is exoskeletal, so you see the triangular elements. So the facade is done in a way that works with the sawtooth, but also the triangles. So the panels of the glass are in distinct large triangles, and then the design and the structure of the glass is within that triangular element, which is different from most buildings with continuous facades. The next one. Just another shot of that aspect. And you can see the relationship between the facade and the diagonals, and there's a detail between the triangles and the diagonals, which is kind of unique in the facade and isolates these triangles in a specific way. Next. This is a wind tunnel model we did. I threw this in because the split in the building, we tested it with and without this porch, which we did around it, and there was a significant lowering of wind load on the structure because of it. Next one. Just a detail of the facade. It shows how the facade relates to these triangular elements, and there's a detail between the exoskeletal expression and the facade itself, as well as, of course, floor to floor. Next. And I just threw in pieces of the glass being put together, and it was fascinating to watch that happen. Thank you.
Thank you. Roy, if you want to go ahead.
Yeah, thanks. If we can have the next slide, please.
Oh,
Is it
sorry.
yeah, we're moving fast here.
Okay.
Yeah. So if you're designing your facade for wind loads, how are you going to do it? Do you even need to do it? I mean, who's ever seen some broken glass in a building? Never happens, does it? Oh, hang on, San Francisco. Yeah? 14th of March, 21st of March this year. We had close to 2 50-year return period events a week apart. I mean, kind of fluky, yeah, but we saw some damage. I'm surprised there wasn't more, yeah? But if you're going in at design, you can say, well, I'm going to design to the code, the standard, yeah? And that's just ASC 7 sitting there in various versions, getting bigger and bigger and bigger. And wind loading is a bit of a contributor to that. I'm not guilty for any of that up until the 722 version, yeah? And it's not like a normal design standard when it comes to wind, because it's not saying do this, do that, do that. It's designed to envelope most design cases, but it's not going to catch all of them. And it's going to be, for most cases, a bit conservative. So you say, well, actually, I want to be a bit better than that. Let's go to the wind tunnel. And there's little wind tunnel model. That's your 415 Natoma that Trent was showing. So again, not super tall, but there's value in there. So the idea is you can save a bit of money if you're clever with your design and look for, yeah, they're the bits I need to strengthen, and you'll find most bits are a bit below the code. Yeah? So there should be some savings there, but you're also getting that resilience bit by picking the hot spots that the codes miss. And those of you who've been working with the SC 716, you'll notice, oh God, some of the low-rise pressure coefficients have gone up. That was mostly moderated in most places by the wind speeds coming down, so it kind of washed. But we also know that some of the other coefficients in there are still a little bit too low. Yeah? And this really came out in the development of the performance-based wind design pre-standard, which we did over the last few years. That's version 1.1, just freshly out. And this was Ron and the Pankow Foundation went, yeah, we need to get wind up to the stage of seismic in terms of looking at nonlinear effects in the structural response. But probably what it's thrown more light on is trying to get an equivalent resilience in the building envelope to the structure. And it's way behind, if I can have the next slide.
Yes.
This is the numbers, yeah? Because not a lot of people think about this. Most building envelopes are designed to ASD, allowable stress design. So that's basically taken, all right, we'll take our 700-year load of risk category 2 building, our ultimate load, divide it by 1.6 is what you should do. But the code says, well, no, just multiply by 0.6. So that's a rounding down already. Then you're going to test that to 1.5 times the SD load. That's you getting to 90% of the design load. So you never actually get there and prove it's going to work. The bit that a lot of people have no idea about is that the standard is saying we're looking for reliability for each individual cladding piece, not the building as a whole, the building envelope as a whole. So you take that 0.85, which is the directionality factor in the code, put that through. That's designed to say, well, probably the worst wind direction won't be, you know, the worst wind direction for that little bit of cladding, not the building envelope as a whole. So I ran the numbers this morning, yeah, in my hotel room because I'm that kind of boring person, and said, if we have a building in San Francisco, we design it to the code, yeah, using a 700-year mean recurrence interval wind speed. Once you put these together, do you know what the mean recurrence interval for total building envelope reliability is? 100 years. 100 years instead of 700 years. That's a bit scary. So I reinsured, did my life insurance because you're probably all going to kill me. So, and I know the quick way out here, so that's my 2 minutes. Right.
Great, thank you. Ron?
Well, good afternoon, everyone. We were asked to think a little bit and talk a little bit about resiliency with regards to wind and seismic. So I offer up just 3 points for you to think about going into this. First is, for the first time ever in the ASCE 722 code, there are tornado provisions, and particularly impactful to the exterior wall design. So coming soon to a theater near you, you're going to need to think about tornadoes. And there's regions of the country, of course, where it's more important, just like seismicity, but just know that it's in the code, and as soon as local jurisdictions adopt the ASCE 722 code, you'll be faced with responding to tornado requirements. Next. Roy already mentioned the pre-standard. When we set out to write the pre-standard, we were thinking mostly about structural design, but there was a very loud cry for additional provisions related to envelope design. And so this document, if you click through the next couple of slides, maybe it underlines, it's a discretionary thing, it's not a requirement. You can choose to do performance-based design for the main force resisting system, or for the envelope, or for both. And this is something that attempts to set some standards and ground rules for how buildings should perform, not only structurally, but the envelope as well. Next, please. The last thing I want to leave you with is this concept of simple drift versus DDI, or deformation damage index. And let me summarize this by saying the lowest hanging fruit I see between structural engineers and facade designers is learning to communicate better and more clearly. There's a huge, huge gap in terms of how we communicate. And let me give you one example. If you show the next slide. Structural engineers typically report out to you drift. My building drifts X number of inches, or H over 400 is some magic number. But they don't tell you how the building moves. And so in this diagram, what you see on the top is one version of drift, and on the lower image, a different version of drift. And the structural engineer will tell you those two types of drift report out the exact same number. But it's very different in terms of the response of the building. And if you understand this nature, is it racking drift, or is it rotational drift, or is it some combination of the two, you can get at value very quickly. And so dissecting, what are we really talking to each other about? Not just some one number size fits all, but what's behind the number is really important. Thanks.
Thank you. And last, Vince.
Thank you. We can go ahead and go to the next slide here. Want to talk for just a minute on system selection when we're talking about choosing the systems that are in a facade. And we've seen in some of the example projects today, I mean, a variety of projects, some which had more standard off-the-shelf systems, particularly glazing systems, where there can be cost advantages to choosing those systems, but then the downsides of that, we're losing some of that aesthetic flexibility, and we may have a potential loss in resilience with those. On the other side of things, we have entirely custom systems, which can be great. Those are the best for being able to fulfill our aesthetic intent from the architectural community. But there was a quote that struck me earlier during John's presentation when he said, we're sitting on a pile of low bids. That's very true. So from a constructability standpoint, there's very little benefit for anyone to build resilience into the systems themselves. We're going off of the information that Roy and Ron are providing, and oftentimes those custom systems are getting designed to the minimum to achieve that, because there's no incentive from the construction side to go above and beyond that in a competitive bid environment. In the middle between the two, you do have hybrid systems of being able to work with standardized systems and changing some elements of them to be able to achieve that design intent while hopefully not sacrificing any resilience. And then just a little bit on cost and where we stand. These last few years, we've seen unprecedented escalation, more than many of us have seen in our careers. We've seen facades going up 35 to 50% in the last few years. And many projects are over budget on day one. Couple slides or presentations ago, we looked and we saw some pictures of massing studies where there is no information about the facade, just the massing study. I don't know if you'd be surprised or not, but as facade designers, we're often brought in at that point, to provide information on the facades, what the facade on that building is going to cost. On a recent case where we did that, there was no information on the facade, and the architect did not know what they wanted to be, but we'd done work with this architect before, and so we priced it based upon similar work we had done with them. The general contractor, wanting to be as competitive as possible for the owner, took that budget and cut it by 35%, straight out the door. This is why we're over budget on projects from day one, and we're fighting that from that point on as the information's coming in to want to design the best building possible. So when value engineering becomes the first order of business, where do those changes ultimately need to come from?
Perfect, thank you. So we have a quite mixed group on the panel, and I think it's really representative. Everybody on the design team will obviously design for their own interest. So some people want to design for aesthetics, other people are going for resilience, last one will be designing for costs. Jeffrey, how do you approach the discrepancy in design objectives, and how do you bring those together if you have to look into do I want to design for aesthetics, and how do I bring designing for resilience into the same mix?
I'm so glad you asked me that, because you were talking and I was thinking of stories, you know, endless stories. I think, and our firm, we're probably one of the ones that you would throw in a higher factor for. But I was thinking as you were talking about this, and I think one very important piece that is newer in the world, in the conscious of a lot of people, is performance and cost. And performance, I mean, like I was talking about passive solar. So what do you want to achieve with your building in terms of energy reduction by passive means, which means by design, to reduce the energy costs in this world and in the world before. And I have found that there's a direct relationship between design intent and cost and trying to do inventive things like passive solar. And that means that the client has to be convinced that the performance over time and the reduction of energy costs will be of benefit, and therefore you pay a little bit more on the facade. And as you all may know, some developers are there to make money, flip the project, they don't care. And some are there for longer term and have a wider view. So I would say on the cost piece that design is one thing, and that depends on the client. And then the more recent and more important things like passive solar and variables on exposure around the building, dependent on where the sun is, all of these kinds of things lead in very strongly to being able to have a comprehensive dialogue that goes beyond the technical and the dollar.
That makes sense. So passive solar, as a facade engineer, we typically understand it as we're going to have overhangs, we will have fins, we will try to regulate sun exposure by preventing it to get into the building. Now, this is a lot of elements that we're adding to the facades, which are on the exterior, kind of like a jewelry, but what do these facade accessories basically mean when it comes to wind design and wind analysis? How do we actually know that the design is going to be sound, that we're not generating more problems in terms of structural attachment, noise generation, and stuff like that? Roy, if you want to expand on this.
Yeah, I love these things, particularly when they've been built and no one's really thought about them. I've learned so much from these in the last few years. So it comes down to all kinds of things. So some of the sort of the louvered sunshade arrays, we've seen them, and we've seen the individual louvers vibrating and getting into this little harmonic resonance. Sometimes that creates noise, sometimes they just drop out, which have different things going on for them. We see a lot of the use of, say, porous, punched panels. We've had some absolute screamers of those. We've seen them in the field. We've taken them into the wind tunnel. We've had, I think, 120 decibels was a record, just from testing a prototype thing. So a lot of it's just recognizing in advance. I mean, and it's detailing. We'll test it. We'll advise. Can we guarantee? No, not without till the stuff's been up in situ. We've got a pretty good idea. We had one recently on the West Coast a couple of years ago, building that we'd wind tunnel tested, and then they'd added some fins on the outside, architectural fins, vertical in the bottom section. And these fins got delivered to site, and only then did it get to the engineer of record to say, did you sign off on these? Who came up with the loads on these? So we looked at it with them. did some back of the envelopes thing and said, yeah, it's not quite there, but if we take a performance-based approach, yes, it's going to match. And then I said to them, but you've got this little gap in the back there. You've got a cavity running down the back, this channel. I think that thing's going to whistle. And they laughed. The client said, no, no, no chance, no. And I said, really? I think it's going to do it. Took about a couple of weeks to convince them, yeah, you'd actually better send us some, put it in the wind tunnel. 5 minutes, we had these things screaming, yeah, absolutely screaming. Simple solution at that stage was just to gasket up the back of it. So it was cheap, it was easy to do before installation. After installation, I hate to think how much that would have cost.
You're mentioning you're doing wind tunnel tests on certain projects and designs, but sometimes as a facade engineer, I just get code values. Nobody's really wanting to put money into a wind tunnel test. How do you choose which project has to go ahead with a wind tunnel test? Where can I say, no, I'm going to save the money, I'm going to just stick to the code values? And when, like you mentioned beforehand, the performance-based approach, how does the decision-making process on the design team go about that? Like, where do I need to actually call you and say, Roy, can you help?
Yeah, this is going to be the end of my career. And this was pointed out. I was in a workshop last week, funded by NIST over at the SC headquarters in Reston, and it was all about the future of computational wind engineering. And there was a panel discussion, and the moderator is then said, well, and the way that they put it was, so if you don't want to ask me, ask Roy, or ask them, how do you work it out? Yeah? So what I'd say is, right now, you ask me. Yeah. I tell a lot of people, no, it's probably not, there's no real value, but it's that experience. Where I'm going to be out of a job is AI. We're already working in that field. We're training it. We've worked the best models. It's going to become an early design tool. We were talking to computational people last week, and all this. So there's two bits. There's computational fluid dynamics, which is what everyone thinks about computational wind engineer. They're gung-ho and says that will be a standard design tool within 5 years. It's the same as Murakami was saying in 1974. He said 15 years. But it's getting small, but it's getting a lot closer. The AI is the bit that replaces me being able to recognize, I've seen something like that before. That's what I think is going to happen. But we have to train it, and I'm not willing to train it yet on that stuff. No.
No need to. Okay, so basically wind on a facade generates different problems, but then also wind translates into the structure. And typically what I see is we're getting drift values, as you mentioned, for the maximum structural earthquake event, but you also get serviceability movements in the building, but they're very rarely kind of communicated between teams, and I feel often there's a lack of understanding. What does the facade need to accommodate in terms of serviceability movements? How do you suggest to deal with this problem or like go about it?
Really excellent, and it's at the heart of what I mentioned earlier, that the communication between the structural engineers who are controlling the motion of the building through our designs and the facade designers is so critical, and it's so poorly done right now. So I'll give you a few questions that you can just jot down and remember to ask the next project you're on. And that is whether it's wind or seismic, when the structural engineer is reporting out numbers, what's the recurrence interval of the event they're considering? Is it a 10-year wind, a 50-year wind, a 500-year wind, a 1700-year wind? What's the level of wind demand? Or seismic, is it a 50-year earthquake? Is it a 500-year earthquake? Is it a 2,000-year earthquake? Structural engineers are really poor at communicating out just the basis of what their assumptions in their design is. Then secondly, I mentioned in my slide here, the DDI, that's really a better measure of how a structure will interface with the facade or the interior finishes, but it's not really ever, well, let's say not ever, it's rarely reported. Most structural engineers will run their computer analysis, and kind of the simpleton view is the computer poops out a number and we give you the number. but there's no communication about what's the nature behind that number. So understanding and peeling the onion a little bit more, and not just accepting the number that you're given, but understanding, well, what's behind that number? What's the event you're considering, and what is our performance objective at that event? Are we trying to keep the water out of the building? Or are we trying to keep the facade from falling off the building? And under what event are we trying to do that?
Let me jump in on that for a minute. We had this wind event in San Francisco, and some glass came out of some buildings. And one was the Bank of America Tower, done by SOM, and done, I'm an old guy, so it was done not long before my tenure there when I was, just out of school. And the other one, also a SOM building, that has this facade that kind of gently goes in and out in a quilt weave. For the B of A one, the thing I was thinking about was that this was a magnificently designed building, very strong, first quality materials. It has very large panes of glass and a kind of a bronze finish mullion. And the building's now like 55 years old. And so the other question that comes in with that building is, what happens over time? Is the failure that happened at B of A, putting aside whether the wind problem was very unique or not, it was quite windy, but is the failure maybe from age of the gasketing and the way the glass is held? I can't answer about the other building. I'm not at SOM anymore, haven't been there in a long time, but the younger building's very new, so that's like, what happened?
So a unique point of view I'll share with you all on that subject.
Yeah.
I didn't work out either of those buildings either.
Just
Go
to
ahead.
finish, so I'm more intrigued about the B of A thing, what happened,
So what I was going to add to this is that there were these two wind events in San Francisco of recent, and there was some damage and some glass broke and what have you. Those two wind events were, by quantifiable sake, design wind events. Historically, facades have been designed for a 50-year wind, and those were two 50-year wind events. Also, facades are designed from a reliability point of view, meaning one piece of glass out of, and I don't know the number, Roy, do you know the number? It's like 1 million.
Yeah.
Is expected to break in that event. 0 in engineering is not a number, it's all about reliability. And so in the grand scheme of things in San Francisco, yeah, a few pieces of glass broke. In a design wind event, it actually did really well. This wasn't a problem. This was a testament to how good things are, at least one point of view.
Yeah, and I kind of agree with that. But what's also very exciting about this is that the city is funding some forensic investigations, and they're going to be fairly, well, I'm not saying they're going to be, they are fairly coherent, yeah, across a number of buildings. So I'm hoping that we're going to get some sort of publicly shared knowledge that comes out of this that's going to help us learn.
I agree. I mean, I'm looking to see what they find and what happened. And, Ron says design was really good. Only a few pieces of glass came out, except if you're on the street under those, and then you're dead.
Just adding one
sure.
thing to that. I mean, and as they do the forensics, it will be good to see what they find. To me, it also speaks to why design has to have such a large safety factor, because the other factor that comes into this is the workmanship. You oftentimes see when you get into it, there's an issue of workmanship, possibly from the installer. When we're talking about glass and glass breakage, if that glass was installed and it came from the factory with even just a small little scallop on the edge, that significantly decreases the strength of that glass and increases the chance of it breaking. Possibly not to break under a 10-year wind, but it could under a 50 where it shouldn't. And workmanship can be a real issue. We had a project that we were doing a reskin on. We helped with the demolition of the existing facade. It was hard to find two fasteners we took out of that facade that were the same. They literally, every single screw was different. None of them what had been in the original design. So that is also part that has to really be watched.
So I'll share a couple of little fun stories on that. Yeah.
You got 2 minutes.
Yeah, the workmanship bit is Dubai. A few years ago, they had some cladding panels fell off buildings in a windstorm. It was construction defects. Yeah? But their answer to that was the wind speeds are too low, the design wind speeds, we'll put the design wind speeds up. The sustainability and financial cost of doing that rolled all the way through the structure, awful. I mean, it was almost an environmental disaster, that decision on its own. That one is my first experience of having a failure on a building that I'd wind tunnel tested was on the Olympic Stadium in Sydney. I got a call from site when I was down there and said, we've just lost some panels out the roof. I shot down there. I had one of those squeaky pants moments, you know, down like a shot. There were these missing panels on the roof right where we'd predicted the highest pressures. And it's like, we had anemometers on the stadium because we'd installed them to control the Olympic flame and all the ceremonies. And we saw the wind speeds, windiest day in 5 years, from the worst wind direction for those panels. And then I looked and I saw, what are those ropes there? And it turned out these were discolored polycarbonate panels. They'd had workmen up because the new ones had arrived. They'd unbolted the old ones, gone off for their afternoon tea. So we could see there's the self-weight of the panels. That was the wind speed. Therefore, we think the pressure was this. And we could see, and it was the nicest bit of field validation of the wind tunnel results. So it was like, was that in 2 minutes?
Perfect, thank you. I wanted...
One more thing.
Thing.
This one's important. I'll do it really quick. Everybody should go back and look at the history of the John Hancock building in Boston, where the design failure and the movement and racking meant ultimately the replacement of every single glass panel in the building.
That actually is a bit of a better introduction than I was thinking. We're talking a lot about wind, but I think we want to dive a little bit into the seismic issue that we're seeing. Often, when I think about a successful structural engineer or like a successful structural engineering design, everybody wants the least amount of steel, the least amount of concrete. The building wants to move, then you're doing a good job. But then if you go on the other end and you're a facade engineer, I want this to be as stiff as possible. Like, I don't want any joints. I don't want to see anything movement. I don't want my Mollins cups to grow to accommodate movement. So basically, those are two opposing objectives. On one hand, make it flexible, let it move. On the other hand, make it as stiff as possible to not actually impede aesthetics. So how do you go about combining those two objectives and also like satisfying everybody's needs?
So that's the fundamental premise behind why we wrote the pre-standard on performance-based seismic design, well, the pre-standard on wind design, but also the TBI guidelines for seismic design. And that is to have this commonality in language. And again, it's founded in the idea of performance at different demand levels. So if we're talking about seismic, we can say, for example, under a small earthquake, something that happens once every 50 years, we want the exterior wall to perform. We want to keep the water out, we don't want to break the seals, et cetera. We want the building to perform and the inclusive of the exterior wall. At a larger event, a 500-year event, or at the extreme event, the 2,000-year event, if the facade is somehow damaged, okay, fine, we'll accept that, but we don't want it to fall off the building on top of somebody's head. So holding it onto the building is the design objective. We're able to get at all of that directly within this performance-based design framework. We're not able to get at that directly in the prescriptive code language. The prescriptive code approach is like one size fits all, and the idea is if you design to this particular recipe and you detail according to the code, you hope everything works. And in performance-based design, we don't hope anything, we check everything. We calculate it, and we work with the facade engineers to then communicate clearly about the demand levels that we're putting into the model, what are the resulting outputs of the deformation of the building, and what's the nature of those deformations, like my slide. Is it racking? Is it rotation? Is it some combination of the two? And what does that mean to the facade? And in all of that, if we communicate really clearly on that, I believe there's a bunch of value that could be had very, very quickly without any new technology, without any, John Picard was here earlier, and all the whiz-bang AI stuff, that's great. But I'm talking about stuff that's like right in front of your nose today. You can go do this today. You don't need to wait for Silicon Valley to invent some AI stuff. You can go have this conversation today and make it better.
I think one aspect that I came across, sometimes we get values from the structural engineer and then the contractor comes in and says, this is the ultimate value. We are going to design according to that one. It leaves you with a 6-inch seismic joint. Nobody wants that joint. Nobody wants to take responsibility for smaller values because it's not your responsibility to necessarily calculate different modes, but it's also not the contractor's responsibility to go about and calculate the modes of a structure that they don't own. So basically, it's a bit of a gray zone to understand who will take responsibility for values that are actually expressing themselves in the facade. And my experience was, well, nobody. So we will design for the maximum value, which leaves the architect who doesn't want the 6-inch joint be on the losing end, because they're like, that's not what we want in the design. The contractor will not go about and say, we are taking responsibility and only design for 3 inches. The structural engineer doesn't want to say any other mode but the most severe one. And then where does it leave us? And I think, Vince, if you can elaborate, how do you, how can you work towards values that are not owned by you, but make more sense of them?
And I think a lot of it comes down to there is a lack of communication that goes on. I mean, Ron, as you said, so often structural engineers are doing the work and the number is just spit out. And in turn, the contractors are working with that, and we, as a facade designer, are going, and yes, that may mean, and if we're dealing with a custom curtain wall, it's not that big of a deal to have larger stack joints at the units. It's fairly easy to do, but architecturally, no one likes how that reads. But what doesn't happen, or very, very rarely happens, is actually getting everyone in the room to really have those conversations, to understand what is the actual mode going on here. What do we need to do? I mean, I went and looked. In the last 20 years, we've had one project where that conversation actually happened, and it was able to inform the design. So I think just getting people together to be able to talk through and be willing to have those conversations is at least a starting point where we need to be.
I might add, in particular as it relates to wind design, there's no codified values for building displacement under wind loading.
Yeah.
All the code talks about is strength. So the structural engineers can decide whatever hecta number they want, because there's no standard, there's no code. Folklore is that we typically shoot for something like the story height, H, divided by 400. It's a folklore number because it's worked in the past. But think about that. If you're doing a resi tower and the floor-to-floor height's 10 feet, that's one number, H over 400. If you're doing an office building and the story height's 14 feet, well, that's a different number. And if you're doing a life sciences building and the floor-to-floor height's 18 feet, well, that's still yet another number in terms of absolute magnitude, but the structural engineer is just thinking about H over 400, H over 400, H over 400, because that's the folklore number. And there's no conversation with anybody about, well, on a resi tower, that's a 1/4 of an inch. On an office building, it's a 1/2 inch. On a life sciences building, it's 3/4 of an inch. It makes a big difference to the exterior wall design and detailing at a serviceability level. That's what I'm talking about when we talk about communicating more clearly and asking the questions. Don't just accept the number, say, well, what's behind this number? And tell me more.
Yeah.
There's one number that's come up in recent times, and by the way, I love collaborative meetings, conversations about buildings. I don't know another way to do it, but there's a very interesting number that's come up in recent times with very tall residential buildings. And when we did 181, we came up against this number. And that is that for comfort, if you're living in a tower way up, that the number that has been kind of universally seen around the globe is to not have more acceleration than 0.1017 of a G in any wind event. And so designing to that kind of thing is a way greater demand than to some seismic or wind calculation and structure. And in ours, through a iterative process and also working on that one with Arup on seismic shock absorbers in the structure, we got down to 0.015. But above that, lawsuits happen. and in New York, you can read about some of those.
Perfect, thank you. I think I want to close off going back to events. Often, I think the design team comes together, gets a great design, is super ambitious, motivated, and then we get a contractor on board, and the first process is we have value engineering. And nobody likes it. It brings down the mood. It's like everything we thought about, we need to cut off. What is the trade-off between designing for resilience and basically cutting out for cost?
Yeah, and I actually just taking a step back, you said right now, all the design is done, and then the contractor's on board. What we see so often, even if they're not formally on board, it's the opposite of that. And it's the fact, like I said, we're getting asked to provide facade pricing on massing studies that don't even show a facade. We're giving costs before SDs are even done. And one of the challenges that we see so often is the fact that all of that is taking place, and then design consultants are being brought on, and then the decisions being done to do the wind tunnel study, that all those things are happening later. And I think it was Felix this morning had a slide about making the right decisions early. Mm-hmm. So the advice that I give to owners when I have the opportunity is the fact that, if possible, decide who the entire team should be on a project, even if it's not for sure that a contractor is selected yet, but to start those conversations early so that they can have informed decisions and being open to that communication. Because otherwise, again, like I said earlier, with the way costs have gone, we're just seeing the facades get more expensive, and we're over budget from day one, and we're fighting it. I would much rather be able to have informed information so that we can be pricing that project properly from the very beginning.
That, I think, makes the most sense. And I think this is sometimes when you have design build and you have the contractor on board to inform the design process, but also we are like consultants. We want to do our thing. We want to contribute to the design. We want to support the architect's idea. So basically is getting on board, communicating at a very early stages to avoid price and design discrepancies at the further down the road. We are running out of time, 30 seconds left. Anybody a last comment they really want to share? No? Well, I appreciate your input. We do not have a question round.
No, sorry.
Yeah, no, I'm just informing the group. Thank you very much for listening, and I hope this was informative. And for any questions, I think anybody is available for networking later on in the group, in the hall. Thank you.
Thank you.
It was good timing.
All right. If the speakers can still stay, and the rest of the speakers that were presented in this session can come for photos, the rest of you, please enjoy lunch. chill, take your time, and again, we'll notify you when you have to come back. Thank you. All right. Is everybody settling down? Everybody ate? That was a delicious lunch, by the way. Top notch. Thank you. So a little bit for everyone. Dessert included. Okay, so while everybody's sitting down and getting comfortable, I think we're ready to bring over Christopher Payne. He's the senior associate at Gensler. He's going to be talking to us about 200 Parc. So it's another exciting new building that just came up, and we're going to learn more about the performance of the envelope. And please welcome Christopher Payne.
Thank you. Thank you so much. Again, my name is Chris Payne. I'm the San Francisco office of Gensler here, our hometown. So really pleased to be able to participate in this event with Zak. So thanks for the opportunity. I want to talk about 200 Parc, about an hour south down in San Jose. Want to first definitely mention the owner and our client, J. Paul Company, regional developer based here in San Francisco. We're also working with Level 10 Construction as our general contractor, Eckersley O'Callahan as our facade engineer partners throughout the design process, and also Permis de Lisa, who ended up building the facade. So a really quick orientation to the project and its location in the heart of San Jose, the unofficial capital of Silicon Valley. The project's sitting along a very important east to west green corridor that connects San Jose State University on the far right through Plaza de Cesar Chavez, one of the oldest public spaces in the entire state of California, all the way over to the Guadalupe River Park and the San Jose Center for the Performing Arts. So really interesting site along this important corridor. Zooming in a little bit, the project's well served by public transit, and actually in its construction introduces a mid-block paseo, which is something that the city of San Jose really values in their development in the downtown core. So that's a very neat, kind of intimate, pedestrian-focused corridor that connects Broadway, the green kind of east to west corridor, down to the main public transit east to west line, the light rail in red there. So talking about the design of the project, and when we first got the brief and the commission, at the outset we immediately sought to, of course, maximize the buildable envelope in San Jose. The airport is directly north of the city, and so the downtown core is very much hemmed in by the FAA height limits as the airplanes approach the airport. And so the height is definitely capped. And so when you max out your buildable envelope and the FAR that's allowable, we ended up with a very boxy cubic volume that needed to be broken down significantly to be functional. And so what we did, we thought about the inside experience first primarily, and we started carving out volumes in the envelope to hopefully allow daylight to penetrate deeper into that cubic floor plate. And so then we located amenities, the lobby, certain amenities in the middle of the building, a gym, a lounge space, a bike room, that then helped to shape those canyons. And so it took them from being kind of schematic slices to being a little bit more shaped and have some slope and character to them to respond to that program. So geometrically, resolving those canyons was one of the major challenges of the project, with those slopes and angles, playing within the overall cube of the building. And so what we tried to do was create repetitive shapes that could be either mirrored or rotated on different orientations of the building to try to be as efficient as possible, knowing down the road we were going to be looking at unitized wall just based on the scale of the project, creating something that was going to be very efficient and buildable. In terms of the program stacking, there are 4 floors of subgrade parking. The ground floor is obviously anchored by the lobby and other leasable tenant spaces, as well as a kind of grand bike room that really celebrates the alternative transportation that we're hoping to really encourage, as well as a couple of retail opportunities. Floors 2 through 5 are above grade parking behind our typical curtain wall, which is a little bit atypical. Those floors were intentionally designed to be higher than a usual parking floor so that in the future they could be converted to creative office space if and when hopefully the demand for parking goes down. And so we're using parking stackers given that extra floor-to-floor height to maximize the day one parking, but then it also allows it to be convertible in the future should the parking demand decrease. So that was a really key kind of long-term flexibility, almost future-proofing measure that went into the project. Floor 5 is the amenity level. It has a fully built-out gym, a lounge, office management, property management, and then the upper floors are all very flexible, creative office space, rooftop mechanical. The typical floor plan, like I mentioned, is very large. It's about 50,000 square feet, so that is a lot of space, but also very, very desirable for tech and creative office tenants that really want those big connected floor plates. And so those solar canyons that we introduced to not only break down the mass, they help to really appropriately size what we called the workplace neighborhoods on the inside. We really looked at this carefully to make sure the scale felt good and it was functional. And so those spaces between the canyons became the workplace neighborhoods that encourage, individual work as well as collaborative zones centered around those solar canyons. And so there was a lot of kind of push and pull inside and out of what should these canyons, look like, how should they be sized, and then what's the resulting workplace experience. Each floor has 3 different actually bridges that go within these solar canyon carvings. I call them bridges in lieu of terraces because there's actually guardrails on 2 sides, open air with a kind of cavity on the innermost wall. So it's kind of an interesting feature to extend the workplace to the outdoors in those canyons. Very ambitious performance targets really from the outset. A number of strategies were used. One of the largest moves to really push the performance was going with an all-electric design. That's something very much the Bay Area is leading the nation on, knowing that the energy grid is one of the cleanest in the country here, and with the opportunity with more renewables coming online in the future, having an all-electric design really allows the building to be completely 100% run on clean energy in the future. So that's a great thing to set the project up for future success. Also, much more than code minimum electric vehicle charging stations, and obviously a high-performance facade that I'll get into here. A couple of key highlights. The project will be LEED Gold certified, has already achieved Fitwel 2-star rating, which if you aren't familiar is really focused on internal occupant health and wellness. Interesting timing of this project, going through design during COVID and the pandemic and construction kind of happening all during this, crazy time that we've all lived through. We went through a whole process at the outset of the pandemic of, oh my gosh, do we have to rethink this? Are people going to be coming to office buildings? Does anybody want to touch anything, right? Like that was the knee-jerk reaction at the very beginning of the pandemic. And after several months of study, we realized that a lot of the original design ideas still very much held true. And sound planning, touchless water fixtures, these things have been standard in Class A office design for a long time, but it was just kind of good validation that even after a deep dive analysis, we were not doing wholesale changes. The EUI on the project is 31, and so that is actually quite a low number for a project of this size. So we're really pleased with that, and a lot of this comes from not only the high-performance facade, but then the decision to go all-electric, which then reduces the project's greenhouse gas emissions by 73% over your kind of standard baseline with gas boilers. So now getting into the meat of the facade, from the outset, we really wanted a very performative facade, but we wanted to take an approach where, our first reaction is to do something very specific to each facade as it receives different amounts of solar orientation. Climate in San Jose is a little bit different from where we are here in the city, where it's much more driven by controlling solar heat gain, less heating in the winter as well. And so we closely analyzed how much each building face would take in terms of solar radiation, and then we mapped our facade grid onto the elevations, and we had the idea of varying the window wall ratio per elevation to be specific to the orientation, but give not a completely different facade expression on each side. And so we came up with this idea of varying spandrel, the varying element is the vertical piece. So we had about a 30-inch horizontal spandrel, but then we varied the vertical piece per elevation, and so you get a little bit more transparency on the north, a little bit more solar control on the south where you need it. And diving in a little bit more closely, what does that look like? So we came up with this matrix of curtain wall panel units with the solid element in the color. And so you can kind of see how on the north we biased it to thinner solid pieces, more glass, going then to the south with whiter solid pieces, a little bit less glass. And so we came up with this family of units, and each building orientation has a slightly different bent to the size of and types of those units. And then to make it work within the overall massing, we decided to work within the solar canyons and have the areas in the middle of the canyons be a little bit more solid, and at the edges where you're approaching the corners of the canyons where the glass wraps in, we wanted, and also for those corner experiences, a little bit more transparency. And so you can see on the elevation diagram there on the left how the blue being a little bit more solid happens in the middle of those areas between the solar canyons. In terms of system design, that's all happening at one scale, right? So this is zooming in a whole nother scale, right? We wanted something that would be highly textured, highly articulated. We decided to push the windows into a thin frame to again give a little bit of passive shading, not dissimilar from the 181 Fremont project that we were looking at earlier. And then we actually angled the glass in plan so that on one side you have a little bit more of a kind of shading fin than the other side. And then what that looks like in section, this condition where the angled glass in plan, it's out further towards the edge of the window frame, and then as it kind of cants back, you get a little bit of a deeper expression there. And then looking up, that gives you a kind of glimpse of what that angled glass actually does to shade and shadow and giving the feeling of a highly textured facade. I want to zoom in a little bit to the solar canyons and the bridges that kind of fill those gaps, because they're a very interesting and kind of in a way, like their own unique project. We wanted them to feel delicate. They go every other floor, and so each floor has a slightly different type of size with the angled walls of the canyons. We also wanted the edges, or the two ends of the bridges to feel very light and delicate and fit within the thin spandrel zones. And so the beams are tapered at the ends to allow that to happen. And then a lot of systems coordination between sprinklers and window washing, making sure we have hands-on access for all of the glass, and future unscheduled maintenance for there's not much caulk because there's mostly gasketry on the window units themselves, but anything that would need to happen in the future, we have anchors to allow BMU units to slide within that slot between the bridges and the back wall of the canyons, as well as on the outboard side to allow hands-on access to all these different surfaces. A lot of work there. And then, really getting into the details of how the bridges meet the building, on both sides of the canyon, how the waterproofing laps up underneath the starter sill, kind of that was the key condition to solve, because it was obviously a repetitive condition everywhere. a couple of quick, progress shots of what that looks like, how we sequence the fireproofing of those beams as the sidewall of the canyon comes up underneath them, and then we have to make sure the air and vapor barriers terminated and coped around all those beams. So a lot of pre-coordination there to make sure that we were going to have something that was buildable and very repeatable. The cladding of the bridges themselves going on, and then we wanted a material, a warm material on the underside to kind of contrast the sleek outer skin of the building, almost hearkening back to a clay tile roof that you see on some of the buildings in San Jose, but a very different kind of contemporary take on that. And again, just the idea of expanding the workplace experience outdoors with the wonderful climate that San Jose enjoys. And so getting into the facade itself, we all the angles and the thin window frames were a very, very consciously tailored, crisp aesthetic. We wanted a material expression that would contrast that and be very soft and ethereal and environmental. And so we settled on this idea of an embossed linen finished stainless steel that really just is stunning in the way that it accepts light and reflects things in a very blurred, soft way. So it was kind of this idea of contrasting the sharpness. So lots of early prototypes for how we were going to be then cladding aluminum extrusions to create those window frames, taking it up in scale and testing actually different reflectance values of the embossed linen finish, because we didn't want to go so reflective that it would potentially create even other issues. And so we tested different reflections and did studies to make sure that reflections were going to be okay, and that we were still achieving the lightness and brightness and crispness that we were after. Testing different soffit materials as well. And then obviously testing the performance, a completely custom system, especially with that idea of the angled glass and plan, which required two different aluminum extrusions that were cut on a slight angle to allow that angled glass to happen. So we were really keen to test this as soon as possible, working with Permastelisa on this. It was a remarkably smooth process to test the air infiltration, water infiltration, dynamic water with the jet propeller was always a fun one. And then the coils of the stainless steel itself, because this is a raw material, there does come some intrinsic character to the metal itself. And so part of the process and actually acceptance criteria was looking at a sample of every single coil that was going to be used for the entirety of the project to ensure consistency, and there wasn't something intrinsic that would catch your eye. And so we had a sample of every single coil shipped out to the Bay Area to look at them in person, review them for consistency, like I said, just a really high emphasis on quality control. And then also being in the factory, there's just nothing that replaces the being there, seeing how things turn corners, things that you don't catch on shop drawings, right? Seeing the very first units off the line, setting the benchmark. It's just, I can't say enough how important that stuff is. We were also lucky enough that Permastelisa actually set up an assembly line locally out in Modesto, just 80 miles from the project site for this project. They have a warehouse out there that they use for storage, but to actually set up a dedicated assembly line for unit assembly so close to the project site was a really nice embodied carbon kind of efficiency story that we're happy about as well. So the units arrive on the floors, were then hoisted into place in a very straightforward, typical way. The challenges came, of course, at the corners, making sure everything lined up. This is a shot of the east side of the building in morning light, and so you can kind of see the varying expression of that linen finished stainless steel, where it really takes on highlights at certain areas where you get direct solar heat gain, And then, shade and shadow, where you get the angled glass contrasting it. I like these two images a lot as well because it just speaks to the fact that this is one material, but it has a very different reading depending on the time of day and the building orientation that you're looking at. In the morning, the linen finish stainless has this very kind of blue indigo-y look to it, and midday it's quite neutral, and then sunset is a particular treat where the material really takes on the character of the surrounding environment and the light. And so that was very much what we were after with in a way a very simple, repetitive design. We really wanted the material to sing and be something special. Looking up the highly textured facade, again, something that we're after from the sidewalk kind of building entry perspective. We're really happy with the quality of all those different shades and shadows and tones that were created. Thanks everybody for the interest, and enjoy the rest of the conference.
Thank you. Thank you, Chris. Thank you for sharing all those details through the process of the project. It must be really interesting to experience that space of the canyons from the workplace. So up next, we're going to be having one of our associate partners from Constantino, Western US. She's a regional facade manager, Diana Scare. She's going to be presenting sustainable facade design with ultra-compact stone. So welcome, Diana. Thank you.
Well, hello everyone. My name is Diana Esquer, Regional Facade Manager with Constantino. I would like to start introducing a little bit of who we are. Constantino is a global Spanish company with presence in more than 110 countries. We are the leaders in manufacturing and suppliers of ultra-compact surfacing stone panels, especially for facade projects, commercial and residential. To show you a little bit of our value proposition, Decton is our main brand for facade. It's a mixture of more than 20 inorganic materials. No organic minerals are included in these mixtures, which makes it, it doesn't fade, it doesn't degrade over time. It's special for facade applications. I have a short video to show you. If you can just play it. Oh, right here. So we can show you a little bit of how it is.
A facade is a blank canvas on which to draw ideas that excite. Each facade is unique, and so is each design. We approach each project as a tailor-made suit. Colors, textures, fittings, thicknesses, and finishes specifically created to bring each design to life, just as it was envisioned. Constantino offers comprehensive, customized, and sustainable solutions for timeless facades. We marry performance and strength with endless installation possibilities and ease of maintenance. Decton transforms buildings into functional works of art. Composed of a mineral blend, it's sintered, heated, and pressed to create an ultra-compact inorganic material that unites performance and beauty, creating a technically superior surface. Decton doesn't expand or degrade with UV rays. It's resistant to extreme weather conditions. Available in large formats and with great dimensional stability, Decton panels can cover every corner of the facade with minimal joints. Decton boasts never-before-seen technical properties. It's non-combustible, impermeable, and with minimal maintenance needs. It's also available in thin thicknesses, offering maximum lightness and performance. Decton is cradle-to-grave carbon neutral, a commitment to our planet and our value chain. Decton's sustainable production process and high energy efficiency contributes up to 15 LEED and 14 green credits for facade projects. A world-class product coupled with world-class service. Constantino, leader in architectural surfaces, offers a robust global distribution network, delivering materials in record time to every corner of the earth. Additionally, Constantino City showrooms, located in the heart of key cities, have become a meeting place for connection and collaboration with the architecture and design community. Constantino's team of experts accompany clients every step of the way, from specification to on-site execution and post-sale services. Decton has become the material of choice for renowned architects, including Ron Arad, Francois Payne, and Ville Arret. The material clad some of the world's most jaw-dropping buildings, such as Torre, Leonardo Tower, Cap West, and countless more. This is only the beginning.
So as the video says, Decton is special for facade application. It is high resistance to UV rays. It is graffiti proof. The color doesn't fade, doesn't degrade over time. It is easy to clean. No sealant is necessary. It comes with a 25-year warranty for facade application. And it's really strong. It's stronger than porcelain, stronger than marble, which makes it a really good product for exterior applications. It's high density, linear thermal, porosity of 0.1%. Sustainability is also big for us. It's actually the only product that has a carbon neutral certification. We recycle 99% of the water that we use, and we only use renewable energy. We use more than 38,000 solar panels to produce Decton. We have multiple certifications, the ICC approval being the most important, especially for the West, the BBA, EPD, earthquake. To partner with us is very simple. We basically only need your drawings. It can be 50% done. We can help you doing the takeoffs. This is, for example, an example of a facade study that we do. We study the area. We can check the wastage percentage, the panel size. We can help you to optimize that for your projects, panel complexity. Our panels come with Decton Protect, which is a reinforcing mesh, and it makes it a A-class fire-resistant product. Decton ID is another service that we offer. Our panels can be 100% customizable. It can be any base color, any texture, and all of this while maintaining all the advantages of Decton. As I said, many colors can be achieved. Orange, green, for example, this project in Vancouver, we customized the color for the architect using Decton ID. It is ideal for any kind of facade. It can be ventilated facade, curtain wall, bonded facade. We partner with different system providers to provide the attachment systems for Decton. It can be a combination of mechanical and chemical attachment systems. We have two different options: visible, using rivets, screws, and clamps, or invisible system, doing a chemical adhesive bonding, system rail, undercut anchors. Some of the options that we have for visible attachment systems is the DKR system, which is a rivet visible system. It can be used in slabs, 4mm, 8mm, full slab. Another one of our visible option is the visible clamp. We will supply the color matching clamps to attach the system. Our invisible option, using an anchor system, Kyle or Fisher, it can be used in a slab that it's 8mm thick, 12mm, 20. The staple system, another curved periodic stable system. It can be used in 12mm, 20mm slab. The DKGB is a combination of chemical and mechanical attachment system using Sika or Bostik, and our chemical adhesive system. It can also be used in curtain wall application. Our product can be used exactly the same as glass. It is glazed into the unitized system. ICAP is another system that we have. It's an insulated cladding architectural panel, and it can be used in residential and commercial applications. This is our typical prices. per square foot using Decton plus the system, the cheapest one being the direct adhere system, ICAP, then the rivet fixing system, and the chemical anchor system. Some of our example projects, case studies, is the Porch Boutique in Illinois. Here we use a rain screen facade system, one color, 12 millimeter thickness. Another one, a good option for a curtain wall facade project, is the Gap West in Munich, Germany. We worked with the Wheel Arets architects here. It was a 12 millimeter panel, big project, unitized system. Here's some of the examples of how we manufacture the panel with the undercut anchor system included in the panels. We pre-drill and deliver ready to install on site. Another one, a project in New York, 3 different colors, different thicknesses, 12 millimeter panel using undercut anchor system. Our biggest one is the Torre building in Tel Aviv. This was 6 different colors in the first six floors, the mechanical rooms, and the soffit as well. This bank in Chicago, Illinois, it's a rain screen facade, 12 millimeter thickness. This project in Austria, Danae and Zenith, 2 different colors were used, 12 millimeter thickness, rain screen facade. Curtain wall project, the 8X on the Parc in Vancouver, 12 millimeter thickness, Decton hollow color. This one in Brazil. We can achieve any kind of forms, any kind of corners. The Warner project, 12 millimeter facade, ventilated. The first bank in Greenville, South Carolina. For this one, we used a thicker slab, a 20 millimeter slab, ventilated facade. This one in Spain, ventilated facade, 8 millimeter thickness, 2 different colors, Domus and warm white. Office in Germany, 8 millimeter using a Danae color. It's kind of a white beige stone. That's it. Thank you so much.
Thank you, Diana. We're definitely good on time. Let's take it a little bit slower. So picking up a little bit from an earlier conversation we had from Karen Brandt from Heintges, where she dove into the importance of the quality in the facades for any carbon calculations within the building. I've had the privilege and the pleasure to work with Prateek and Atelier 10. I witnessed firsthand him work really hard on carbon tool within Atelier 10, and it's a pleasure to see how this has developed. So he will be diving deeper. We have Prateek Jain with Atelier 10 presenting, sorry, it's not updating on my background, but so Prateek Jain will be presenting Thinking Through Facade Choices as Carbon Investments. So please, a warm welcome to Prateek. Thank you.
Thank you so much, Edlyn, for that personal introduction. You're doing a great job, by the way, and I loved working with you too. Okay, so like many of the talks earlier today, mine is also focused on sustainability and does a little bit of a deep dive into embodied carbon. And as I was listening to the talks earlier today, I feel like this is going to be almost like a sequel to Karen's talk in the first session. So without further ado, I'll dive right into it. Okay, so we're a small community here. Most of us know each other. But just a quick slide about Atelier 10. We're sustainability consultants within the built environment, and we work with architects and owners to make buildings more sustainable, healthy, and comfortable for occupants. Personally, I work a lot on third-party certification systems, sustainability of materials, building codes, but my favorite is really whole building life cycle analysis and embodied carbon. So that's what I'm talking about today, and that's a rapidly evolving field, as all of us know. And there's been a lot of new developments, so I'm going to try to capture some of that in the first piece of my presentation today, and then talk about how facades contribute to embodied carbon, and then some educational content about how we compare embodied carbon of materials as well as assemblies, and then finally try to answer some of the provocations that Karen had about carbon paybacks and the relationship between embodied carbon and operational carbon and lifespan and all of that. Okay, so what's new with embodied carbon? The first piece I would say is just awareness, right? So how many of you have considered embodied carbon on your projects or products? Show of hands. Quite a few. I'm seeing around half of you, so that's pretty good. Yeah, so I would, if I were to point to a single event here in the Bay Area, that would be the Climate Smart Building Day that happened in San Francisco in 2018, where this EC3 tool was launched and the Carbon Smart Materials Palette was launched by Architecture 2030. And personally, I felt like a big momentum shift there in terms of how building design projects have started to consider embodied carbon from that point on. There's been an explosion of resources. There was a shout out to the Carbon Leadership Forum earlier today. I'll give them a shout out as well. The AIA has a bunch of resources around how to do LCAs and how to think about embodied carbon, how to incorporate it into your design thinking. The benchmarking systems have followed if they weren't already taking the lead. So for instance, LEED already had the LCA credit, but the ILFI has come up with the zero carbon certification system, and other certification systems have also started to make embodied carbon a highlight of their credits and scoring systems. Regulations, an exciting one. Again, we had a shout out to the Buy Clean California Act earlier today, which regulates global warming potential for materials for a state-managed project in California. That is not just in California, it's in the Pacific Northwest, it's being adopted in the Northeast, Canada is doing a lot with it, Europe is a few ways ahead of us in terms of regulating GWP of construction materials, and just in terms of transparency, at the federal level, the Inflation Reduction Act has earmarked a lot of funds for this. So for manufacturers specifically, there's a $250 million fund for the EPA to create a program to provide assistance for manufacturers to develop EPDs. So we're going to see a lot more EPDs spurred by that. And then in California specifically, concrete is conspicuously excluded from the Buy Clean California Act at the moment, but there's another bill which is seeking to decarbonize the cement sector. And as was mentioned again earlier today by Karen, there's a mid-cycle code update coming to Cal Green, which will require whole building LCAs above a certain threshold. And then cities have taken up this at their own local scale. So the Marin County low carbon concrete code kind of set the precedent for regulating concrete, and then Palo Alto also picked it up, and Berkeley also picked it up. So these three jurisdictions have requirements around reducing embodied carbon of concrete specifically. Emeryville gives you a bonus if you're building with mass timber. So local codes are picking this up. And regulations definitely proceeding faster than I kind of expected in terms of recognizing embodied carbon. The private sector obviously is again not far behind. So a lot of trade coalitions have taken this up, and industry coalitions. So the MEP 2040 Challenge is a coalition of MEP designers who've committed to eliminating embodied carbon of MEP systems by 2040. Structural engineers have taken this up, and then ESG frameworks have started to recognize it. So the Science Based Targets Institute, which is used by a lot of multinationals for reporting their carbon emissions, is going to be featuring embodied carbon, and is going to have targets for individual buildings pretty soon. That is based on the amount of carbon budgets we have remaining at the global level, and then broken down by sector and by country, and what that means for individual building projects. So that's coming soon. And for developers, GRESB started to recognize embodied carbon. So all of that is a whole bunch of development which has happened very quickly in the last few years. In terms of how we as building designers look at embodied carbon, there's a whole suite of tools out there. The early stage or system level tools are typically the easiest to use. I want to give a shout out to several of our partners, many of whom are present here today. EHDD had a major update to the EPIC tool. You should check that out if you haven't already. That's a very user-friendly tool, high-level embodied carbon, whole life carbon information, as a matter of fact. Beacon by Thornton Tomasetti for structures. One of my favorites is Kaleidoscope. That is probably the most relevant to us as facade designers, which looks at facade assemblies and provides comparisons of different facade assemblies from an embodied carbon standpoint. There's also Pathfinder for landscapes. So a whole suite of easy-to-use early stage tools. And then you start getting into the more involved tools which do whole building LCAs. So Athena, the open source, not open source, but free tool that's been around for a while. One-click LCA, that's used by a lot of us practitioners for doing whole building LCA. Tally's integrated into Revit, so that's, again, one of the easier tools to use for whole building LCA. Shout out to Eckersley O'Callaghan here for their own tool. And then on the side and for material selection at a more granular level, EC3 by Building Transparency has a whole database of thousands of EPDs. I think they're getting close to 100,000 pretty soon. So it provides great statistical analysis of EPD data and enables comparison and choice making on that basis. So a lot of talk about tools, but how much do facades contribute to embodied carbon of buildings? A high-level view. This, as Karen said earlier, varies by typology, so I've captured a few typologies here. For concrete, mid-rise commercial offices, when you're also considering interiors, it is about 20 to 25% of the embodied carbon is in the enclosure. The big categories are the metal, the glazing, and the insulation. And metal is typically the highest, and then it can kind of change on the basis of the project. When you're building with timber, the embodied carbon of the structure is reduced, so the enclosure takes on a bigger chunk. It can be up to 30%, and once you start to factor in sequestration of carbon inside the wood, it goes up even higher. And if you're doing renovation projects or reuse projects, again, the proportion of structure is reduced. So enclosure takes on a much larger chunk, assuming you're reskinning or replacing the windows. So this is an example from a campus project we did in San Diego, and there it was almost 40% of the total embodied carbon in the enclosure. So bottom line, right now, the best guess is around 20 to 40% of the building's embodied carbon is in the enclosure, and that's pretty significant. And I have felt in all of our projects and in our analyses that it's a tougher nut to crack compared to structures where there's a lot of work that's been done in terms of how to optimize your concrete mix designs and where to get your steel and where to get your rebar and timber, but not quite as much in facades. So there's still a bunch of work being done, but definitely ways to go. So the first thing to look at is just comparing materials and assemblies for embodied carbon. And the best data point we have, as flawed as they are right now, are environmental product declarations, right? And the analogy that is used most often is a nutrition label. I like to think of them more as a list of side effects on medications, because that's really what EPDs are telling you. They're kind of depressing documents. They tell you like 6 to 10 different ways in which your product is messing with the environment, and then you're using EPDs really to make a comparison of what's less bad. So ideologically, I have a little bit of an issue with EPDs, but yes, they are the best data source we have right now as industry practitioners to compare materials. That said, you need to use them responsibly. So there's a lot of caveats around how you use EPDs. Where you're comparing exact products that you know, if they have published EPDs, use the product-specific EPDs, and don't try to cross borders when it comes to functionally equivalent materials, because that can give funky results. When you don't have that, industry-wide EPDs are your next best bet, but you can use this as an opportunity to push manufacturers to produce product-specific EPDs. And again, comparing functionally equivalent products in units. So an example that we take in structure is concrete and steel, right? So at a per unit mass level, concrete is way less carbon intensive than steel, but obviously they're used in very different ways. There's much lesser mass of steel that's used than concrete. And so at a whole building level, they can come out to be even. Similar analogy for facade materials can be aluminum and terracotta. So aluminum is very carbon intensive, as we know, on a per unit mass basis. But you need to look at how much of it you're using to cover your facade. So if you're using, say, an ACM panel or a terracotta cladding, you need to look at really the per square meter facade area and compare on that basis, accounting for the different thicknesses, and then further expanding that comparison to include the entire assembly, because you need, the support systems can be as carbon intensive or even more carbon intensive than the cladding material itself. And when you're just looking at EPDs, that's again something to remember, to check whether EPDs include a substructure or they don't, and if they don't, then accounting for that in your comparison. That said, for insulation, this is one of the easier places where you can use EPDs to make more direct comparisons, where there's a lot of other considerations when switching out materiality, but here it's easier to have a one-to-one comparison for materiality, and this also keeps changing over time. So mineral wool, for instance, here is a pretty carbon-intensive alternate. It used to be XPS, traditional XPS with a lot of HFCs. Now with the HFO products and reduced HFC new generation products, it's come down the line. But in general, more plant-based, more bio-based insulation that you can go for, the better. And then coming to assemblies, as I was mentioning, if you see the graph at the bottom here, you'll see that if you just look at cladding materials, that's the green bar. But when you start to look at assemblies, the comparisons can look different. So for instance, fiber cement has a low embodied carbon just for the cladding piece, but the support structure holding it up bumps it way higher. Obviously, you can't have assembly details at the early stage always. The example on the right is when we did have material quantities for the assembly. The example on the left is using data from the Kaleidoscope tool, which has predefined assemblies with assumptions about what quantity of support structure goes into holding up these different types of opaque assemblies. Coming to glazed assemblies, they're a whole different beast. I do want to give a shout out to Arab, who've done a phenomenal study with Saint-Gobain using their EPD, and they've compared 16 typologies, run 18,000 simulations to compare embodied carbon and operational carbon. And there's no clear answer because it's so different on every project. But one of the things that stuck with me is that coatings in particular, and that's shown on the graph at the top left. Coatings are pretty good when it comes to looking at them as carbon investments. They have relatively low embodied carbon, but offer great operational carbon benefits. But yeah, this comparison shows just the impact of processes, so coating, tempering, lamination, double glazing, triple glazing, how that impacts. So when you don't want to go through EPDs, you can reference literature like this, like the Arab paper, or the recent study published by the Carbon Leadership Forum. It was an update to their study of baseline materials. So again, not sifting. They have done all the sifting through the EPDs and imparted all uncertainty calculations to it for you to make more scientifically informed comparisons. And yes, again, once you've done those assembly comparisons, again, important to zoom back out, look at the whole building level, see what you're doing. In this graph, they were considering traditional XPS, which was very carbon intensive, switched that out to EPS, led to a major reduction at the whole building level. But I want to spend a few minutes just talking about carbon paybacks. And a quick anecdote that comes to mind is a designer once mentioned that when we told them to consider embodied carbon, they said, I'm a painter, I'm an artist, you can't just take away a color from my palette and ask me to design like that. And her response was like, you really need to think of yourself more as a juggler because there's so many things that you're trying to strike a balance with, right? There's a whole list I've put here. I'm not going to read it, but form factor is one which I find particularly challenging because we love increasing the form factor. It means higher daylight, higher views, higher natural ventilation potential, but it means more material and more embodied carbon. So this is always a difficult question. How do we start to address it? And the best ways we found is to quantify as many drivers as you can. Well, first of all, prioritize your drivers, but that is a subjective exercise. So to bring some objectivity to it, quantify whatever you can. In this case, on the bottom left graphic, we quantified the number of hours that 633 Folsom here could keep their blinds open depending on which shading configuration they chose. And then once you've quantified things, lay them out together on a table, on a spreadsheet, and then you start to see things like movement in one metric. So this one on the right is a good one that I want to talk about. Double glazing versus triple glazing. Triple glazing had a big embodied carbon penalty, and it wasn't really saving as much in terms of operational carbon later on. So on that particular project, 58-story building in New York, we decided to stay with double glazing because the whole life carbon made more sense from a double glazing standpoint. Exterior shading, Felix talked about this a little bit in the first presentation. Exterior shading, when done well performatively, when done well on south and west facades, it can save energy, which can be an operational carbon savings. So this was a Bay Area project, academic building. We had shading on the south and west facades, which was optimized to be performative. And its embodied carbon investment was paid off by savings in less than 5 years. I skipped over my previous one, but this was a renovation building in CSU LA where we reskinned the building and redid the mechanical systems, and again, like, it was a pretty quick payback for operational carbon savings. Running out of time here, but I do want to mention that there's a lot more in this sphere that needs to be studied. Electrochromic glass versus static glass, I think that's a recognized issue these days, that electrochromic glass is great for energy, but at the moment, because the facilities are not being utilized to their whole level, the embodied carbon of electrochromic glass is much higher than static glass, multiples of static glass at the moment. So that's a consideration we need to make. And when we talk about lifespan, again, most of the focus has been on upfront carbon because that's how the conversation is framed at the policy level, right? That we have global carbon budgets. We need to stay under them before 2050, before we go over global climate tipping points, and then we are in irreversible territory. So yes, lifespan is important, durability is important, but probably more important at this point is reducing upfront carbon emissions so that we can stay under those tipping points and then figure out those solutions later. So all of that is just, I guess, adding more complexity, but that's why all of us are in this together. So just some food for thought. Thank you so much.
So to keep on the topic of glass, we have Eduardo Rosa, which is the manager for Interpane AGC. He's also an architect. I think he also has a lot of experience with curved glass, all in one. So
correct.
you can keep at it.
Thank
Welcome,
you.
Eduardo.
Thank you. Hi, good afternoon. I'm just showing this picture. Is there an echo? Okay. I'm just showing this picture in order to remind this is the Arctic zone where the ice is melting. So we have to be conscious that this thing is impacting us, even if it is far away from what it's our comfort environment. AGC Glass Europe environmental journey has been, I think, a front runner on whatever it is related to environment and sustainability. In 1989, AGC already created an environmental team in order to bring study, in order to make processes far more sustainable, more easy, more energy efficient, and developed through all over the different years a path to different steps in order to get into a final steps where, for example, AGC was the first cradle-to-cradle certificate glass company. We have a lot of primary sites with ISO 14 certified. We have now a creation of an APD tool, which in future, the idea is that it will be launched on websites, so it can be used for to anybody. The other topic is that, which is a pretty recent, and it's not mentioned here, there is an agreement between AGC and Saint-Gobain in order to team up workforce to find new ways to run a flow tank with a different type of energies, trying to remove the gas and bring more hydrogen and electricity. The main idea for work AGC is we have to address the greenhouse emissions, and we have to avoid to create more greenhouse emissions that are concerning to the greenhouse. So the idea is that we are trying to get into the net zero trajectory for the carbon footprint in 3 different steps, where we do have the direct emissions, we do have scope 2, which are the indirect emissions from electricity, and the indirect emissions for scope 3 for the upstream and downstream activities. So the main idea is that all these are the work that AGC has to be done in order to make the carbon footprint less impactable to the environment. From another point of view, also, AGC had put themselves some thresholds, some goals to get into greater sustainability in order to reach the 2030 values for carbon footprint. And the idea is to reduce by 30% the specific emissions of greenhouses, reduce specifically the energy consumption, reduce water consumption, try not to throw it into the landfill waste material, but try to reuse or recycle as much as possible, and produce sustainability new products which will improve far much better the products itself. That is the climate actions that we have to take into account. So trying to reduce the climate target not to increase more than 1.5% by 2030 and maximum 2 degrees by 2050. The idea is that for the moment, we have got a couple of awards that we are on the way to get into the 2030 target. the sustainability in the environment is not just only on products, but it's a whole cycle which is covered either from a framework, so the climate change, politics, businesses, to the products where you have EPDs, life cycle analysis, cradle to cradle, recycling or reusing, the urban environment, so the green certification and the embodied carbon, and the organizations that certify that we are fulfilling and going onto the right path for the sustainability topics. The main emissions which are related to the buildings and construction are primarily energy and emissions, where you see here that everyone has his own impact on it. The building construction industry, as you see, is 6% on energy and 10% on emissions. The sustainability, in fact, we are just going into three main pillars, which is social, ecological, and economy. So the environment sustainability covers impact on the natural environment, such as climate and resource. This dimension leads toward optimization of resources through reuse and recycling, as well as lowering of environmental impact throughout the building life cycle. So through this, we can get into a whole element which makes that sustainability is not just only restricted to the buildings and to the product, but also to whatever it is, employees working for the company, environment on the company, and all the other systems which are just social and economy. The other point related to the economy is lots of companies see that being sustainability falls into losses of the company. That should not be understood like that. So even if you are sustainability, you can get profits out of it. So which for a company is important as a concept of the economy. These are the inputs and outputs of how the glass is made. So the raw materials, where we can get from the mining, the energy and water, which we are using quite extensively for the float tanks, and then all the emissions and solid waste which you're getting out of it. The embodied carbon, which comes from all the four elements, which are the materials extractions, manufacturing, transport, and the building construction, the using buildings with the operating carbon, and the carbon offsets, which is the renewable energy production and the carbon embodied. The way that there is actions that have to be taken, and in one of the speeches by Karen this morning it mentioned, which is a different type of steps, but I think it's not just to follow, but to make understand what are the impacts that those actions do have. So building nothing means that you have no carbon footprint, which at the end of the day is not 100% true, but it's an idea to do. Either you can build less or build thinner, so you get better products. For example, you have vacuum insulated glass, which is thinner, has less weight, has much better performance. You can use a much clever ideas, either using photovoltaic, either using more extra daylight into the buildings, or use, for example, anti-corrosive glasses, which you will not have the problems that in 20 years' time you have to throw it, but maybe you are able to reuse them. Building efficient, so using all the tools that the glass industry is capable to give to the building industry and to the facades and construction. So having coatings and having performances on the products itself. Minimize waste, so trying to use and reuse and recycle the maximum amount of material that we are able to. And at the end, produce glass which has a low carbon content on it and reduces the emissions towards the environment. This is a pretty new piece, which is how you can go from recycling to reusing already units which are on old buildings. Until now, when you reclad a building, you just remove the unit and you just make a cullet, recycle it, or maybe it goes to the landfill because you're not able to recycle because it has several additional elements which are not able. Hegla and AGC, Hegla is one of the biggest manufacturers of machinery in the glass industry. Together with AGC, they are on the way to work on a machinery, which the idea is that you could get the IGU out and from the facade, bring it down, and then you open the IGU, and you could reuse either one of the two panes, if it is in proper condition. Might be the other one can go either to be used or reused, for example, as a painted back glass, or might be, if it is not into bad condition, you even can do it acid etch processed, or it goes directly into the cullet to go to the recycling. Whatever is the element for the spacer and the silicones, this has to go to the landfill. But I think this is an important piece because nowadays we are just bringing down a lot of facades and the glass is lost. We, as Interpane, did many years ago a recladding in Frankfurt for an iconic building. It converted the facade into a triple glazed versus a double glazed, and all the double glazed that was brought down theoretically was requested to be recycled, but at that time, 15 years ago, there was far much more complex, and it did not happen. Nowadays, with this system, which even if you foresee it, you could have it at the bottom of the building that you're recladding, and you can separate the lights, you just spare a lot of transport afterwards. We are also on the life cycle assessment, so we are on the cradle to cradle. As mentioned before, we were the first ones to have the cradle to cradle certification, and we have been very, very strong on putting on that. We also consider the cradle to gate or the cradle to grave assessment. We do have quantified and standardized evaluation for the ISO, and we have a general method that can be used for many purposes, like eco-design, policies, ongoing development for EU. We do EPDs, where I think AGC is pretty strong about it. It has been one of the front runners on that. We do it internally, but all the EPDs are third-party verified. They do have 5 years warranty, and it covers the full cycle of the product from the raw material to the end of life, or alternatively, not the end of life, but to the recycle or the reuse itself. We are covered by the LEED and BREEAMs, and we do have information required to assess sustainability at buildings levels. We can do now the EP on demand. I think this is an important topic because nowadays the EPDs that the glass industry is giving is just for standard products. There is no specificity for the product itself or for the final product that it's been requested. The EPDs, as you can see, covers the whole majority of the production that we do have, from hard coatings, magnetron insulating units, or whatever it is, surface treatment, with the primarily part of the products are covered by an EPD. The only ones that are not yet covered is the enamel, pattern, and security glass, but they are on the process to be done. We have done the cradle-to-cradle certification. We started in 1995, where the gentleman on the picture wrote this cradle-to-cradle book, and then in the AGC followed the cradle-to-cradle certificate up. They got the first one at the end of 2010 with the assessment of William McDonald. We do have, it's a voluntary certification, so cradle to cradle is not a obligatory and mandatory. You can have multidisciplinary certifications at different levels. You have from the basic up to the platinum, and we do have independent bodies that control ourselves for that. The 10 certificates that we have actually today, which are covering from bronze to silver, and that's it. Thank you.
Muchas gracias, Eduardo. So to continue on the last portion of the session, still within glass, just diving a little bit deeper, we have Brian White, who's a technical manager on American Insulating Glass with one of our associate partners, H.B. Fuller. So please welcome Brian. Thank you.
All right. So many great talks today, and a lot talking about the embodied carbon, the operational carbon of facades. And, it's interesting because I love coming to these events because I learned so much about the building facade. I learned from the architects, I learned from everybody here, and I'm just a sealant supplier. So I'm a sealant and spacer supplier, I should say. So I'm really, we're tied in pretty tightly with the IG manufacturers. But what I want to do is provide a little insight to this crowd about how, specifying or looking down at the spacer level of an insulating glass unit can have some pretty big impacts when it comes to the carbon performance of a building. So a term you guys are probably all familiar with is the carbon payback period, which is defined as the amount of time it takes for increased operational carbon performance to balance the increased burden on embodied carbon. And specifically, we'll look at a few levers that can affect the embodied carbon in this carbon payback period, and talk about how some of these design decisions, especially when it comes to the edge seal, can minimize the whole life carbon of a facade. So we all know that insulating glass has done a really, really good job at minimizing operational carbon. We've started with single pane glass and have moved to dual pane, to coated glass, to argon fill, krypton fill, xenon fill, all sorts of crazy gas fills, to triples, and so on and so forth. So we keep getting more and more complex in our insulating glass units, and we're getting that concomitant improvement in U factor and that drop, or that increase in operational carbon performance, but we're pretty much doing it in an environment that is sort of ignoring embodied carbon. So, the more complex we make our insulating glass units, the higher the burden on the embodied carbon of that particular insulating glass unit. Now, when we look at, at this embodied carbon, we see that one of the levers we have to pull when it comes to the embodied carbon or the total carbon footprint of that particular IG unit is the service life of that insulating glass unit. And we'll talk a little bit about how we think we can improve that over time here. So a real quick, probably very easy math to do is to say, look, if you can double the service life of an IG unit, and we heard earlier today that an IG unit is supposed to be about a 25-year thing, right? Like we're supposed to replace them every 25 years. Well, what if you could double that? What if you could make it a 50-year unit or longer? Well, what you're going to do then is cut in half the amount of embodied carbon that's associated with the insulating glass in that building facade. So fairly simple math. But what do we mean when we talk about the service life of an insulating glass unit? And really, in our view, the service life of an insulating glass unit is dictated or predicated upon its ability to maintain the operational carbon drivers, or the operational carbon piece of the IG unit that it was built for. So a couple of those drivers would be the low E coating, so that's going to drive a lot of the operational carbon performance of the unit, followed by the insulating gas fill, so that's about another 20% or so. And the edge seal itself, if warm edge or aluminum box spacer is chosen, that's going to have an effect as well. But we think far more important to the edge seal is that edge seal's ability to retain that argon gas and keep that low E coating from getting damaged over the life of the unit. That's going to drive longer service life and lower embodied carbon for the IG unit. One way that we found to do that is to use a thermoplastic spacer system in the edge. So some of you may be familiar with TPS, some of you may not be, but TPS is a material that actually replaces the traditional rigid box spacer, the desiccant, and the primary seal, the butyl or PIB primary seal in an insulating glass unit. It doesn't replace a secondary seal, that's typically still going to be silicone. But what it does in this particular product is a reactive TPS, and I'll explain a little bit about that in a second here. So what this does is make it easier to make IG units. It's going to cross-link, so it's reactive as I mentioned. It's going to cross-link to build strength within itself. That's going to yield a higher heat resistance for the edge seal than a traditional PIB-based system. It's going to chemically bond to glass and silicone, which results in a permanently fixed but flexible edge seal system. It's applied robotically, so one of the interesting things about this is since it's applied robotically, it can be applied very precisely, and that makes it very amenable to shaped IG units, makes it very amenable to cold bent units, and we'll talk a little bit about a good cold bent project in a minute, and also jumbo units. So we know that the market keeps demanding larger and larger IG units, and if you try to hand place, or if you ever go to a fabricator or work with a fabricator and they're trying to hand place box spacer on a big unit, it's very difficult to do precisely. So how, you might ask, does this affect the embodied carbon and the service life of the unit? So this is some external lab testing that we've done historically, and what we did is we subjected IG units made using Cuddy Space 4SG to European industry standard testing, which is EN 1279. So 1279 would be like the analog to ASTM E2190 or CGSB 12.8, kind of the standards for IG unit performance stateside. This is 4 weeks of temperature cycling followed by 7 weeks of high heat and humidity. So this is accelerated weathering, is supposed to simulate about 10 years in the field. Now we know there's no real perfect correlation between the field and the lab, but that's what it's supposed to simulate. We ran this through these units through 5 successive cycles of this testing and noted that there was still low dew points, so we weren't getting any moisture ingress into the unit, or at least moisture accumulation within the unit. We retained over 95% of the initial argon fill over all these 5 cycles, so again, maintaining that gas content. And we also looked at a measure that they do in Europe called moisture penetration index. And this is something that differs from North America, and it's kind of interesting that it does, and we're actually making progress within ASTM about adopting this. But what moisture penetration index measures is the amount of desiccant capacity that's been used up in that unit. So the desiccant capacity, and so it's important because the desiccant capacity in a unit, given a stable seal, is what drives the lifetime of the unit. Because once that desiccant is saturated, moisture will continue to work its way in and eventually corrode and destroy the coating. So we noted after these 5 cycles is that only 12% of the desiccant capacity had been used up. So that means, again, that with a stable edge seal, 88% of this unit's lifetime is still present. So we're looking at decades upon decades of IG performance. So we thought, well, that's pretty compelling. Let's look at this internally and compare it to the standard that's out there right now. So we took typical rigid spacer systems and some of the commercial foam systems that are out there, subjected them to the same type of accelerated weathering testing, and noted that they made it through typically 2 to 5 rounds of this accelerated weathering, which is good, right? I mean, that means that the units that are out there are passing kind of the industry standard, and some are passing it a couple of times in a row, so that's great. But what we found with TPS units is that they can actually last up to twice as long, if not longer, than those 5 cycles that the industry standard currently puts out. So again, if we go back to that IG unit being a 25-year lifespan or having a 25-year lifespan, now we're looking at 50 years plus based on the accelerated weathering testing. So looking at that, we say, wow, that's pretty cool. What is it about this spacer that does it? What is it about thermoplastic spacer? And it all boils down to stress and strain. So from an engineering standpoint, stress results in deformation or strain within an IG unit. The daily temperature swings, pressure swings, all that kind of stuff forces an IG unit to move around and has an effect on that IG unit. With a rigid spacer system, the stress is compensated for by glass deflection and glass movement. With an elastic spacer system, that can actually take some of that strain out of the system so it can elastically deform, which allows for less glass deflection and less glass movement. And really, at the crux of it is by improving that strain distribution, you minimize the chance of failure, you minimize all that movement in the unit, and that leads to a longer lifetime for the IG. We studied this doing some FEA analysis, so this was done on a particular project where we looked at cold bent IG, so we took an IG unit and bent one corner out of plane. what we found was that the strain was not only tenfold less in the TPS system or the 4SG system, but it was also very well spread throughout the system. So actually, let me see if I can grab this highlight. Is that the highlighter? Nope, that's not it. What's that? Top one? Oh, there we go. Perfect. So what we can see is that the strain is actually well distributed throughout the system, as opposed to the rigid spacer system, where that strain is focused right on the primary seal. And if we remember our basics about IG, the primary seal is what's keeping the gas in and the moisture out. So putting a whole lot of strain on that primary seal is not exactly where you want it. We also took a unit and subjected it to a cold soak. What we found out is that the panes of glass deflected inwards, which is exactly what you would expect by taking a sealed cavity and exposing it to cold. But just by switching out the spacer system to an elastic spacer rather than a rigid spacer, you got 60% less glass deflection. And we think that has some pretty cool implications when it comes to, you know, larger glass units and the amount of airspace that's called for to avoid the glass touching in the center of the unit. We also did some lab experiments, and we found out that when you take a little coupon of, for example, a rigid spacer system, so we've got our box spacer, on the edge we've got our primary seal or our butyl primary sealant, and then our silicone. Here we've got a simple 4SG spacer with the silicone behind it. We take that and we pull it 2 millimeters out of plane, and then we image the strain resulting in the system using a camera and computer, that kind of thing. What we find out is that in this particular system, or in the rigid system, you can't see the strain in the primary seal because it's been destroyed, but all the strain is focused in that secondary sealant with a pretty big hotspot right at the edge here. What we see in the 4SG system is that, again, that strain is well distributed throughout the entire edge, and you actually don't have any hotspots of strain in that system. So again, the overall deformation is less, leading to a more stable edge seal in general. So with that, you know, I kind of want to go into some of the projects that this particular material has been used in, and it's been used worldwide, but some particularly cool projects in my view are the Rufus 2 building in Seattle. So this is a 4SG, this building is incorporating insulating glass units using 4SG. The CIBC Square in Toronto, so these two buildings in the center here with the diamond pattern on them, these are units that these are insulating glass units utilizing thermoplastic spacer by actually Viracon, who's here right now. But then what I think is one of the most compelling pictures is the Chadstone Shopping Center in Melbourne, Australia. So this entire glass roof is cold bent, oh, is that good in there? There we go. This entire glass roof is cold bent glass made using insulating glass utilizing 4SG. And so that was what some of that FEA modeling was done for, but that is about I think it was about 2,000 square meters of insulating glass that was installed and bent into place using thermoplastic spacer. And I just like that picture because it really showcases, in my view, the capability of the thermoplastic spacer system to not only make, you know, beautiful and architecturally interesting IG units, but make them durably and keep them, keep its insulating value over the life of the unit, so over the life of the facade. So to kind of wrap that up, we think that Coty Space 4SG makes some pretty carbon efficient facades by utilizing the service life lever that we have to pull when it comes to embodied carbon. Its gas retention is state of the art, and its mechanical stability and its elasticity allows it to deal with the weathering and the pumping that it sees in the environment on a day-to-day basis, and therefore, you know, create a longer service life. As I mentioned, the fact that it's robotically applied allows us to make all sorts of innovative shapes. We can make bent insulated glass, large insulated glass, shapes, triples, all that kind of stuff. The precise application of that spacer, again, makes really nicely aligned long legs, nicely aligned corners, looks very good from just an installation perspective. And I didn't talk too much about it today, but you know, it's also, we're working with a lot of the companies out there that are doing the thermochromic, electrochromic, the PV coatings, things like that, because a lot of those are extremely sensitive to moisture. They're extremely sensitive to they're extremely sensitive to anything getting inside that IG. And one of the things that one of the things that we want to do is make sure that when we make an IG that's multifunctional, that's going to last as long as possible, because this is getting incredibly complex and expensive. So by ensuring that airspace stays dry, keeps the gas in it, we get a really good lifetime for those units. So, yeah, so thank you very much for your attention.
Thank you, Brian. All right, there's like a couple of announcements. Of course, speakers stay. We want to take a photo from this session. And most importantly, before going on a break, you do not want to miss out on the last session. If you really want to find out on the fresh out of the oven, the new project that's coming up in the center of San Francisco, Hayes Point. Joseph King is going to be presenting from SCB, as well as a very interesting panel about affordable housing in San Francisco. So I think it's definitely worth to come back and don't miss it out. I will look forward to having you. Please take a break, mingle, stretch, coffee, and I will see you back here. Thank you, everyone. Are we good on munchies, on cookies? These are delicious, soft cookies. Seriously. All right. For the last session, we're going to be having this first topic focused on the new Jain that's coming up in the center of San Francisco. It's in the famous corner of 30 Van Ness and Market, right? And Joseph King, Associate Principal of SCB. He's also faculty at UC Berkeley. We've collaborated actually in this project for a few years now. It's ups and downs, and happy to see it start getting up, or at least tested. We're going to do the PMU test in a few weeks. So, but all in all, he's going to be presenting more in depth. This is the first presentation on this project, so it's hot off the press, like I said. So please welcome Joseph King.
Thanks, Edlyn. Hi, everyone, and I want to start off by congratulating you all for making it to the 1605th hour of the day in this lecture, so kudos to everyone here. As Edlyn mentioned, my name is Joseph King. I'm with SCB Architects, and we're going to walk through the design of a new building that's under construction right up the street on Market in Van Ness called Hayes Point, and the title of this talk, Context-Driven Design, will become apparent as we go through the presentation. So just a little bit of background. Hayes Point is a mixed-use office and residential tower, 834,000 total square feet, 540 feet tall with 47 total floors, and 9-level podium, 8 of which are office floors, at 234,000 total square feet with its own amenity floor on level 2, and then a 38-story residential condominium tower above that totaling 333 units, of which 25% are below market rate. And the project is slated to be completed in 2026. So that's kind of a diagrammatic section of the tower, which shows the mix of uses and how they are dispersed. The building is targeting LEED Platinum, as well as WELL Core Silver and Wired Score Gold. It was decided early on in this project, 3 years before the city mandated it to be a all-electric building, so no gas is going into this building, and that was the decision from the client, Lend-Lease, early on, in terms of trying to keep it targeted towards a net zero carbon footprint. So the ground floor, you can see the corner of Van Ness and Market Street comes to kind of an acute angle, and the office has its own separate entrance and address off of Market, and the residential has a separate entrance off of Van Ness. They share entry to the bike parking and loading docks in the back. Sandwiched between the two on the corner of, on the corner of Market and Van Ness is a community lobby, and we envision that as kind of a community meeting space. It'll be open to the general public. You can come in off the street, hang out there, visit one of the micro retailers or the food and beverage vendor in the corner, and just kind of take in the sights. It becomes a little bit of a community living room. And we worked with Gensler on the interiors for this as well as the office space. So want to give a shout out to them for all of their support and help in putting this together. And then the office floors, which are 3 through 8, are average 32,000 square feet per floor, 14.5-foot floor-to-floor heights with abundant natural light coming from all 4 sides of the footprint, including the side which is on the inside property line. We bought the air rights over the building, which is 2 stories high adjacent to it to allow that to happen. And then 2 expansive terrace spaces on each floor, and you can see the way they kind of dance back and forth from floor to floor to allow a little bit more light penetration into those spaces, as well as a little more sunlight to come through. And then the tower levels really are a mixture of 13 units per floor on the lower levels, market rate and below market rate combined, and then down to 2 units on the top floors where the building tapers back, which we'll look at the massing in a second. So 25% below market rate again, and the podium level, which is level 10, includes the amenities, 9,000 square feet of interior space, 13,000 exterior amenity space solely for the residential use. So again, what is context-driven design in our case? The notion begins with understanding of the location of this site and an understanding of the history and trajectory of city growth, which informed the design process and ultimately led to the form-making, massing, and facade choices that came together for this project. So to our west is Hayes Valley, which is a lower scale residential community neighborhood type of feel, mixture of older Victorian buildings with newer modern buildings, very residential with neighborhood retail, a lot of open plazas, a lot of vibrancy, and kind of that neighborliness that you feel in a really urban neighborhood. And then to the south of the site, and then stringing out towards the east, is Market Street, or in this case, Mid-Market, which, as you can see through these slides, have really gone through an evolution over the decades, was the entertainment hub of downtown back in the 50s, and then the Muni and BART underground tunnels were dug in underneath Market, which really changed the trajectory of that area. Most recently, it's been a little bit of a tech boom location with Twitter and Uber, but we've all heard some things about those names in the news, so we'll see what comes next. The evolution continues. And then along Van Ness and towards the north is the Civic Center, which is a series of government and cultural institutions, including City Hall, Davies Symphony Hall, War Memorial Opera House, the San Francisco Conservatory of Music. So a lot more of a larger proportion scaled, a lot more staid expression of architecture, a lot more organized facades. And then we're kind of right in the crux of all that. So that is Hayes Valley, a block over. There's Mid-Market going across, and then that is the Civic Center with City Hall right there. That's the City Hall dome. And then as part of this, we've been working closely with city planning as they look at redistricting the zone as the hub, as it's being called, to allow more residential density and a little bit more height than what was previously allowed in this area. And recognizing this is a new urban residential targeted area that could take on more housing. So really, we wanted to find a way for the facade and the building to start to coalesce all 3 of those different neighborhoods together into a singular building. We'll look at that through massing, through facade, and really the idea of how do we take a smaller scale residential neighborhood like Hayes Valley and blend that or coalesce that with the larger moves of Civic Center and the buildings that we see along Mid-Market. And we're looking at doing that through a mix of programmatic uses as well as facades, where the Civic Center in the middle is really expressed in the podium, which is the same height as a lot of the buildings moving towards the north on Van Ness. The street level activity, we want to bring some of the energy and vitality of Hayes Valley into that space. And then for the tower, we want that kind of smaller scaled residential liveliness and trying to puncture that back down to reconnect with the ground floor Hayes Valley feel as well. So from the beginning, we looked at those elements as being something that's going to be reflected in the facade. The facade is going to take on different scales or different proportions to react to those different impetus that we just talked about. And really, how do we create that different level of scale, but still have complementary uses within the facade and complementary relationships, as opposed to creating a homogeneous feel to it. So this is the final version of the design as it's under construction right now. And you can see the podium has a much larger, kind of more regulated facade, whereas there's a little bit more play, a little bit more of a smaller scaled aperture to the tower. And then the, oops, wrong button. The line of all glazing going down to the terraces down at the office level forms that connective element that brings it down to the ground floor. So I think this quote is really apropos to what we've been trying to do with this building is I think constraints are very important. They're positive because they allow you to work off of something. And we do have a lot of constraints on this site. So as mentioned before, we have the BART zone of influence, which has forced the bulk of the weight of the structure, meaning the tower, away from Market Street. So we don't have it right on the corner of the site as an anchor point. We have 100 Van Ness, the tower in the inset image there to the north. So to maintain the 115-foot tower separation, we've brought the tower away from the other corner. And then due to the fairly high wind criteria along Van Ness, we've pushed the tower back 12 feet from Van Ness. So the tower placement was kind of something that was dictated by a lot of these different elements that are coming into play. So our goal was to try to create an opportunity out of these challenges. And this is a case in point for that is the wind tunnel testing, which you see here in Guelph with RWDI, showed that we had to maintain a certain amount of pedestrian sidewalk wind safety mitigation in order to meet planning criteria. The version that we're looking at here is test number 55 out of 56. So it is the one that we ended up going with. But part of that was that we needed to provide a fairly sizable canopy at the corner of Van Ness Market, 20 feet above the ground, 40% porosity, about 15 to 20 feet cantilevering away to catch downdraft winds. So taking that notion as an opportunity, we created a wind canopy that also met the art budget criteria. And that was something that we worked hand in hand with the ownership group and Future Forms, Jason Kelly Johnson and his group locally, to create a canopy that could both be an artistic entry welcome point off of the privately owned public open space and community lobby, as well as be that wind mitigating element that really starts to play an effective role in keeping those spaces underneath as safe and comfortable as possible. So you can see some of the initial mock-up samples in the top right corner. And it also becomes an element which lights up at night in different ways, and that's something that's currently still under exploration. Another opportunity we took from a potential constraint was looking at the shadow plane, and in our case, we are a few blocks away from City Hall and Civic Center Plaza, which is in that little inset, and the building had to be sculpted at the crown the way it's shown with that green plane moving up in order to keep the majority of that crown from casting any net new shadows on Civic Center Plaza. So we are creating a little bit of a discrepancy right there, like a couple of hours in 1 or 2 days out of the year, which the city was okay with. It was 0.002% more shadow, so they let that slide. And what we were able to do with that is there are 4 floors of penthouse units at the very top floor. Each of those has its very own private outdoor terrace space. On the clear day of the year that we get in San Francisco, they have views of Golden Gate Bridge. So let's get a little bit deeper dive into the facade design. I'm going to talk about the podium, and then we'll work our way up into the tower. And they are very two discrete facade elements, as I mentioned earlier about some of the reasoning behind that. So this was one of the early studies taken from a Wall Street Journal article during our COVID hibernation, if you will, of some of the elements in the building that were already there, but have also made its way in as kind of features that the future of building or the future of office are taking into account. I think some of the main ones to take away is a mechanical system, MERV 15 filters with the capability of having 100% outside air on a floor-by-floor basis for control on the office floors. Touchless access from the moment you enter the lobby to the moment you get to your your office space. So that includes the destination dispatch elevators, security badging, and the like. And the goal is really to achieve a best-in-class design based on amenities, health and wellness benefits, and technology. So some of that is also greater level finishes in the common stairs to address the use of those instead of elevators for a little bit of exercise on your lunch break, breaking down the amenity spaces into smaller compartmentalized areas so that they could be used by more people discreetly, and of course the large outdoor space access that's on every floor. So this is a view of one of the upper office floors with a nanowall system opening out onto the expansive terrace balcony. You can see the balcony above is pulled back so that a little bit more light penetration gets into every space. And then this is view on the left of the separate lobby, 1450 Market, and then separated there is the community lobby space. There will be a wall that can open up to connect them or create separation between them as needed. And in this case, we did go with an electrochromic glass on all of the office floors. And the benefit of that wasn't really from an energy savings perspective, given the mild climate we're in, but really from a user wellness connection to the outdoors and the ability to have people be able to control as much of their environment, bring in as much daylighting as they wanted at any given time through that flexibility of operability. And then this is a view of the 21,000 square foot second floor tenant amenity suite with another protected outdoor space off on the right side there. So the design intent to achieve a facade that could bring all this together really was to achieve a grander monolithic scale in the podium itself, in tune with Civic Center adjacencies, with a strong organizational grid that mimicked the buildings that are next door to it, while instilling a sense of modernity and depth within that rigid system. So we explored ways to create subtle bends and twists within that facade to create a little bit more of a dynamic flow and rhythm within that grid system. So part of that was creating that double floor expression, which you can see in the mock-up models over here, to really start to pick up on some of the proportions of the Civic Center and other buildings towards the north. So this is one of the early studies we put together. This is designed as a system that has a little bit more of a heavy, solid materiality to it. So in this case, we've gone with a unitized GFRC facade system on a steel subframe with dual-face sealed joints to accommodate movement. Within those within the GFRC subframe is a punched window system that's installed into the GFC subframe off-site, and it's by the same manufacturer as the window wall system in the tower above. So these are some of our working drawings showing that patterning. So the pattern itself is very rigid, but given those twists, there is some subtlety to it, and really we wanted to regularize that pattern as much as possible for repeatable unitized elements for the GFRC manufacturer. So even though our system, from a design standpoint, is vertically oriented, the panels themselves are horizontal in nature. So that would be one facade panel, horizontal. The pink would be another one. And the reasons for that are to aid in the ease of transport, because they are loaded on the back of a truck horizontally. And then if we do them horizontally, we don't have to then go to the extra step of tilting them up to bringing them into place with the crane on site. The other is it's better for racking and shear mitigation in that horizontal orientation. So these are some of the details we've been working through with the geometry. And then to create that metal frame around to express the double height space, it's really a metal cover piece that's placed right on top of the GFRC to create that sense of a separate layer of materiality. And these are some of the shop drawings from Willis Construction. And this is the formwork for the PMU system that is currently underway. You can see we've translated our geometry to them. Their geometry from their shop drawings are put into the formwork. In the middle image is the 1.5 to 2 inches of glass fiber reinforced concrete being sprayed onto the formwork. And then to the right is the subframe, which is then attached to the backside of that. And what we get is this frame, this image is the front side. These little tabs of gray are what will accept the metal panels which go in between them. And then the subframe is seen on the backside behind. The image to the right is another building, but it is by Willis Construction as well. It's also a GFRC system that's actually made by Lend-Lease, or installed by Lend-Lease Construction, who is our client and GC. If you want to see that building, it's just right outside the window over there. And that is the system loaded onto the side of a truck, ready to be shipped down to the PMU testing yard. And that's the final product for the podium. So for the tower design, we wanted something that was a little bit more of a smaller module to reflect the difference in use and the difference in proportion and scale on the tower versus the podium. So again, this was to reflect some of the scale that we see a couple blocks away at Hayes Valley, but we still wanted to keep an overall modularity of it to create that kind of a smaller layer of organization. So Myers Plus is in the audience here, and they've kind of coached me up on this one, but I'm going to read directly from Adam Kyle. This is a ventilated envelope, so intake and exhaust for kitchens and toilets and intake air for the HVAC system are all coming horizontally out of the skin. And by ventilating the residential units horizontally through the facade, instead of vertically through centralized shafts, the airflows are right-sized for precisely what's needed, and fan power needed to push and pull air through the building is reduced. This avoids unintentionally over-ventilating the space, saving significant fan, heating, and cooling energy on an annual basis. In terms of energy usage intensity, or EUI, the savings amount to about 2 kB2 per square foot per year, which in our case equates to about 7% energy savings overall for the building. The images on the right are two details that we created for this. You can see the stacked joint for ventilation is there. It's tied into the ductwork, in our case in soffits underneath the slab. And then the difference between these two details is we wanted the ability to do both a flush curtain wall look, as you see on the right, as well as an extruded metal slab edge panel in the middle that allows us to create a little more depth. Then the photo on the left shows a stack joint in a project that we have under construction in Oakland, and you can see compared to the operable window, the joint is fairly indistinct. So we can get a pretty clean look while still incorporating the horizontal ventilation through that wall. And for this project, we are using Reflections Window Walls 9500 system. It's a 4-side silicone glazed unitized curtain wall look, but it is a hybrid window wall system. As you see, it attaches top and bottom to the slab. And it can achieve up to 7 inches of depth on the exterior to create that grid that we were looking for. And at the bottom there is their detail for the stack joint for horizontal ventilation. So this is an early days mock-up, still out in the yard overseas. And it shows some of the stack joint, or not the stack joint, but the depth we get in the white panels coming out, and that's meant to reflect the same coloration of an off-white linen for the GFRC down on the podium level. One thing to mention here is this glass to us was a little too green, so we've been experimenting with different glazing types, working within the performance parameters that we've set up through early testing, but trying to get that right balance, because with electrochromic glass, there's a little less flexibility and leeway in changes in tonality and look. So we wanted to try to find something that wouldn't create a clash with the podium glass. This is a standard IGU in terms of not being electrochromic. So we wanted to create something that had more of a neutral tone, a little bit more reflective, so that it would be complementary to the podium in that respect. And then this is a view from one of the upper middle tier units looking out towards the bay. And I think the only people left probably touched this project at one point or another, but a thank you to everyone who's been involved in this project, including Edlyn, and several other people in the audience and Myers Plus as well. So it's, this is what we have right now. It's currently, shoring is up, the basement is being dug out, and moving forward. Thank you very much.
Thank you. All right, maybe I should talk in front and not on the stage while, oops, again, while we get this uploaded. Thank you, Joseph. Definitely looking forward to that, that construction process. Happy to see it through. Now we will be getting it together. We have the last panel that will be discussing good buildings that do good, elevating affordable housing. And it will be with our moderator, Alison McHugh, Senior Vice President of Project Planning of WebCore. So thank you for staying till the last session. And while we set up, if there's any questions for the people on here, anybody? We good? Okay. Then without further ado, I'll leave it to the new panel and the moderator come forward. Thank you.
Good afternoon, everyone. Hope everyone is doing well. You're one panel and one closing note away from happy hour, so I can tell you're all excited. We have a fun-filled panel discussion for today. I'm Alison McHugh. I'm Senior Vice President and Head of Planning for WebCore Builders. For those of you who don't know WebCore, we're a self-performing general contractor based in San Francisco. So, with that said, we're going to dive right into our panel. I'm going to introduce everyone here. So we have Jeanette Walton, Principal and Design Leader at DLR Group. We have Pedram Farashbandi, Principal at David Baker Architects. And Ashley Welton, Project Manager of Development at IQHQ. So we're going to dive right into the discussion here. So we kind of want to set the stage a little bit for affordable housing. And I'm going to ask each of you kind of the same question, which is, when you're looking at a project around affordable housing, what are kind of some of the goals and themes you have for that project? And Pedram, we're going to start with you. So what are your thoughts?
Yeah, well, thank you very much, and thanks for Zak Facade for having us with such a high caliber panel. You know, I think what you see here are some of our 9 ways that we look at when we start a project. I think we started with 900 ways, and then we distilled it to 9. So I think 2 of them are very relevant to this discussion. One of them is make big moves. And what it means is really when you value engineer a project and take all the good stuff, the project can still make a statement. So for instance, in this project, it's Tahana. It's essentially in front of a jail. And then we're thinking, if these people only have one window, is that really what they want to look at? So we turn all the windows, and now they're looking at San Francisco's downtown view. I mean, we were lucky we were able to afford all those curtain facade, but if you take that also away, it still can make a statement. Next one here, it's 2 of our projects, framing San Francisco City Hall, this beautiful building with a concave and convex curve. So that's still, that becomes a statement, and if you take the good material, it's still, the design bones are still there. This is another example where this was in a historic context. It's in Tenderloin. It's actually a couple blocks from here. And what we realized, a lot of the neighboring buildings were horizontally layered. But our building, at best, it was a square, so we shift the facade and the orientation by breaking these boxes. And then some of these slots line up with the neighboring buildings. And, of course, the material can match the neighboring building. The other way is little goes a long way. I think it's something that a lot of us are familiar with. It's the fact that acknowledging the fact that we're building housing and affordable housing, and a lot of it is there to serve its function. And it's about keeping the simple things simple and focus our effort, energy, and money in where people can see and where people are. Like this is an example, like this corner was the very important corner. It's in front of a park. And it's this nicely detailed corten facade. The rest of the building is pretty simple, but I think that's what people see when they see the project. Another example is like put warm material. I think with modern architecture, we tend to get a little bit cold sometimes. So it's bringing warmth to where people are and highlighting entries. The other way is disperse the good and premium materials throughout. As opposed to concentrate it. So like this is an example where we have the zinc facades where we're dispersing throughout the project.
Thank you for going through that.
Yeah.
Those are some really great examples. I definitely think there's a lot of opportunity to do more with less, I think was kind of what you were talking about, is really picking those places. And I think I can't remember if you brought up value engineering or changing things, and as the contractor in the room, I'm apologizing in advance, because usually those ideas are partially coming from us. But I will say, if the contractor ever says, hey, this is gonna look so much better, just don't believe us, okay? But Jeanette, what about you? What are your thoughts on, what are your goals and themes when you start looking at an affordable housing project?
Yeah, so when I was thinking about that question, one of the things that came up is that the approach that we typically have to affordable housing, it's not actually that different from most of the other projects that we have. The outcome can be very different based on the budget that's there, but the way that we approach it tends to be the same. And really what we're thinking about is how can we anticipate those early decisions that are going to help the design maintain its integrity through the process. And so, there's a couple of themes that come up pretty regularly for us. One is really starting at the very beginning, sometimes before we even really have the project, when we're helping our clients to investigate sites and the yield that's available, really understanding, what is the value that's available within a project and how can we help identify that for the client so that we can really afford the design at the tail end. So really thinking of ourselves as a partner there. That's one approach. Coupled with that, of course, as designers, we're trying to set the project up for success as best we can. And so in these early decisions with massing and yield, there's a lot of decisions that we make about the breakdown of scale, whether there's some relief in the facade. So we're trying to identify those things early and maybe tackle a lot of it on the massing level so that the actual facade has to do less work. And if we do that successfully, then there's a lot more flexibility in terms of when we're actually skinning this mass that already has a nice proportion and already is responding to the scale of the neighborhood. And so that gives us a little bit more flexibility. So we try to go into those early decisions with that in mind. We're also looking and trying to have the reality of VE be present from the beginning and understanding that not all facades are created equal. There is a ranking system that makes sense. Where do we really want to spend the dollars? Where does it make sense to save the dollars? If we have those discussions early and can get on the same page early enough, then that's baked into the first pass of design as opposed to it really needing to be an exercise of VE later on. Internally in our studio, we also talk a lot about resilient design, and I know that word can have different connotations in different contexts. The way that we're talking about it in terms of facade design is, there are things that are essential to clad the building, the must-haves, and then there's the things that are nice to have, different moves that we're making, things that in an ideal world we think are important as designers, but what happens when those go away? And so part of our design process is we'll go through the design exercise of where do we want this to be, and then we'll strip things out and see if the design holds. And if we really get to a place where something that could be VE'd out, when it does get taken out, if that breaks the design, we need to keep looking for the right solution. The last thing that I'll say that's been very successful for us, not just in affordable projects, but market rate projects, all of it, is getting the entire team to the table early. We've done a lot of our projects as design assist, and having, this is an example, this is not an affordable project, but it's at the corner of Pine and Franklin here in San Francisco, the Rockwell. And for this project, we had the general contractor, the client, and the architect all at the same table really before we even started. And so having this be a precast building was something that was direction that came from the general contractor. And we were able to bring in Clark Pacific, who did the precast for us early on, really at the end of schematic design. And so as we were developing the design of this building, we were getting their input and feedback. We were essentially looking at shop drawings, in DD, and working through the details with them, understanding how we could get to a place so that once we were finally on site, erection was actually very quick. And that translates into dollars. So a lot of those things really have to do with our early decision-making process, getting the right people to the table, having those early conversations, and it tends to benefit the project in the long run.
Yeah, I definitely love the nod towards the production, because that is totally where my brain goes with this last picture, which I got very excited about. But that's definitely where my brain goes when I think of ways to be efficient and things like that. Okay, but I'm going to kind of put you on the spot for a second. And this could be a question for anyone on the panel. But what do you think stops us from all getting to the table at the same time that maybe we could all fix or work on together? Like if you had an idea. I'm kind of putting you all on the spot.
I think, some of our clients, I feel like they're just not there yet, I think that part of what benefited these projects was this was a series where we had worked with the same team over and over again, and we had that synergy already developed. And I think that there are efficiencies that can benefit the project having that already in place. So part of it is just understanding that it brings value early on and making it a priority. I don't know if you guys see that.
Well, sometimes I feel like we're a little bit scared of each other. Like I'm thinking, if I present this to a contractor, they're not going to go for it. So, I think for the benefit of the project, I agree that it's really important to engage everybody, all the stakeholders at the beginning.
Ashley, to put you on the spot as our developer representative here.
I think they hit the nail on the head. Like, honestly, it's really about being comfortable with that early engagement and bringing these people to the table and being able to have those continued discussions and really wring out all the details in the project. It's not just about the system, it's about the details too.
So then going back to our original question, so when you're looking at a project, what kind of things are you looking for, and specifically around facades, but also just the project in general?
Yeah, I think so. As an owner-developer, whose main intent is to build core and shell developments from the ground up and maintain them for the long term, we typically look at it in two specific variables beyond what Pedram and Jeanette have said, and that's really like, is it durable and is it efficient? So in the terms of efficiency, you might think, we look to designers effectively to say, hey, I want you guys to design a facade that helps me run my building, maintain my building with a lower amount of energy, and that lower amount of energy will directly input, or output, I should say, a reduced amount of cost that we experience as owner-operators over the long run. And then also in terms of efficiency, I think one of the former presenters had hit on it, is just like, do I need all this material in the design? Are my are my column size too large? Are my mullions too large, et cetera? Like really finding that efficiency in the design, because that again is going to translate to cost savings and reduced schedule, et cetera, and that's going to be a better return on investment for an owner. In respect to durability, this one is a little bit more near and dear to my heart, being a former waterproofing consultant. I see with durability that there's a need to connect the contractor, the designer, as well as the manufacturer in the detailing and installation process. Because if you look at a design, if you don't use the right material in the right setting, what good is the material? If you don't install it right, what good is the material? And if you don't follow the manufacturer's recommendations, it's probably not going to work. So just marrying those three people in that process, I think, is extraordinarily important. And I actually think about that in the sense of like a personal example I've had in my own life, and that's when my boyfriend and I, we bought a condo, and we ended up looking at the windows one day, and I was like, oh my God, I think we have polyisobutyl migration on the window. You guys actually know what I'm talking about.
What?
My boyfriend looked at me like I had 3 heads, because he's like, what in the world are you talking about? And I was like, oh, I'm sorry, that is a material incompatibility. I was like, what that means is someone in the process of building my condo forgot a detail. And that detail, what that resulted in was a lot of time, a lot of attorney fees, and a $30,000 bill for us to replace our glazing units. And that was one unit. And there's 230 units in the place that I live in. And if you think about that in terms of affordable housing, if you take that tiny, minuscule thing that doesn't seem that important and you extrapolate it across 230 units, it quickly becomes unaffordable. And then looking at it in the terms of affordable housing, or even if you're just me and you can't afford a $30,000 bill, it oftentimes turns into deferred maintenance. And if you have deferred maintenance, that tiny little drip of a leak could quickly turn into a little bit of mold in your wall cavity, or that could then quickly turn into a little bit of deterioration on your facade, or even worse, like a structural compromise. So I think at the end of the day, that really like hones in on the theme of, you want your facade to be as durable as it possibly can, because that's the thing that's going to be seeing the greatest amount of weather. And then the last little thing I want to hit on before I pass back to you, Allison, is, you could take these top line products that the industry says, like, this is the grade A product. And again, if you don't detail it right, it doesn't matter. But you could also take like the second rate product, and if you have thoughtful detailing in it, for example, like the VE, you're like, I want to do something a little cheaper. If you have thoughtful detailing and good coordination, you could make that same product have a long life, and it's going to be a great return on investment.
You just have to pay the architect a little bit more.
I did a little bit.
Well, that was going to be my next kind of question, is like, so to go into this a little bit, and I, as the contractor and me, of continuously trying to improve, because clearly it was an installation problem. I've gathered that.
Fabrication.
But so what would help kind of drive that? It's like additional detailing, but where do you think that should live in the life cycle of the process? Like, and who could help? Like, how could this group help in some capacity with that? I'm going to put you all on the spot for that one.
I think as a former waterproofing consultant, they brought me in so late. Oftentimes they'd help me, or they would bring me in the early concept and help specify the systems. It wasn't always, hey, I'm going to be frank with you, I want something a little cheaper. They don't normally say that. They just say, hey, tell me what I should do, and you write a memo and you say, okay, here's the best products, that's what you should do, et cetera. And then you go away for a long time, and then you come back when you're somewhere near early on CDs. And if they had involved, let's say, the waterproofing consultant earlier on in every step of the way and really communicating the project goals, especially on cost, and educating people on how expensive these things are, I think that could really help the industry.
I heard pay architects more. Don't worry, we all wrote that down.
That's always good.
No, I think that there's a gap there of when it's handed off to like the contractor, and I'm going to totally put myself on the spot here. Because there's things that end up GC to coordinate, and we're like, we're not qualified to coordinate that. Like, don't let us pick colors either. But I think that's an area that we could all definitely improve, because it does take something that could be affordable and make it very, very costly in the end. So, okay, we're gonna pivot really quick and talk about, now you have a magical wand, and you get to change some part of the process of the design, or the things that you see on the projects that you've worked on around facades and affordable housing. So you have the magic wand. Jeanette, you're gonna have the wand first. What would you change?
So again, a tough question to pick just one thing. So I've had a recent experience here in San Francisco working on a project called Freedom West. I'm not sure if people are familiar with it. But basically it's a redevelopment project in the Fillmore Western Addition part of San Francisco. It's essentially working with a co-op, the Freedom West Co-op. It was a co-op that was started in the late 60s. And they have, very low density housing. And so this project is really about condensing their 382 units into 2 buildings on the site. And then the rest of the 4 city blocks will be redeveloped with a bunch of new program, including over 2,000 new housing units. And so one of the things that was really interesting about this project that I really enjoyed, that doesn't happen a lot in housing, it'll happen in other types of buildings, is that we got to really interact with the residents that were going to live there, as opposed to just with our client. And so the phrase that we used a lot to talk about these residents really getting to represent their own design ideas was they had design agency in the process, and it changed the way that we designed the building. And so in terms of the way that it affected the facade, just sort of an overview, the image on the left is the low density housing. The image on the right is the new development. So you can kind of see there's definitely an increase in density. There's 2 buildings that are for the co-op residents that are between Golden Gate and McAllister, and they're kind of either side of what we're calling the Octavia Green. Octavia doesn't actually go through this block as a street, but it's going to be a pedestrian area. And so as we were engaging with the community about what they wanted to have for their new homes, there were a lot of things that came out of it. They wanted it to be colorful. They wanted it to really celebrate community and open space. They wanted it to be vibrant and bold. They definitely had a different sensibility than I think we might have come if we were left to our own devices to design for them instead of with them. And so, as we started to get into the details of how are we going to approach the facade design, we were looking at the character of the different facades for the building. And, Golden Gate tends to be, it's across from Parc, it's a little bit calmer, a little bit quieter. McAllister is a major transportation thoroughfare, so, the scale of it is a little bit bigger. It has a little bit more elegance, I would say, to the facade. But really what the community thought was the most important were these 2 facades that were flanking the Octavia Green, which, for me is a little bit different than how I think I might have approached it without their input. Usually we tend to value the street-facing facades more than the inward-looking facades. And so, with those 2 facades that are flanking the Octavia Green, they really wanted it to be exciting. They wanted it to be playful. They wanted it to be something that really represented them as a community. And so one of the concepts that we talked a lot about was how do these facades both celebrate them as a co-op within this larger development. They didn't want to lose their sense of identity by becoming part of this larger development as a co-op as a whole, but then also for each individual resident, they wanted to be able to, to have their unit be identifiable in some way. And so as we got into developing that Octavia Street facade, we looked at color, we looked at having the ability that if you're in this community space, which was really important to them, you can point up to the underside of your balcony, which might have a color, and have that be something that's identifiable and unique. And so that was a real driver for the facade design. So this is an image of, you know, one of the two buildings. So basically this facade would be flanking either side. It's very colorful, it's very bright. There is that sense of identity within the development as a whole. I'm sure there's not going to be a lot of other things that look like this within that development, but also, you know, having the color be unique and identifiable. People can say, you know, that's my unit, I'm the yellow balcony on the 3rd floor, and there is that sense of ownership and presence for the green. So having the ability to work with the community that's going to live there, having them have agency over the design that's going to be implemented, it changes things. It changes the way that we think about it. It changes the way that that even the conversations with our developer partners have gone, because we have, it's not just the architect you know, defending design. There's the people that are going to live there that say this is something that we really value and needs to be important for everybody on the team.
So I have to ask, how long was that process to kind of get through it, and who facilitated that process?
So it's been ongoing, and it's going to continue to be a long process. We actually met with the community to share with them sort of the outcome of the design, and they're ready for it right now. And they're asking, you know, so when do we get to move in? And well, you know, we're just starting discussions with the city. This is going to be a long process. McFarland Partners is the developer that is kind of working with the co-op, so it's that partnership, and then we're the design team. And so we started with them, it was a master planning exercise, so that was kind of the level that we started, really just the planning, and now we're starting to get into some of the architecture, and I think that the way the rest of the development is going to be parceled out to other architects and other partners. We'll do some of the other buildings as well, but it's going to be a process for many years to come.
Okay, one more thing. Other than their feedback on, I think you said the Octavia Street, what was one other thing that you kind of surprised you that they had an opinion on that you were like, oh, I didn't know that? If you had to pick one other thing.
I think, so especially when we're at the master planning scale, we're thinking very big picture, and the questions are very, very granular. And so I think, you know, they're wanting to get into what is my kitchen going to look like, or what's my, you know, where's my window, what's my view going to be. And so I think, you know, for us it was a real education in figuring out how to kind of help them zoom out a little bit for the big picture, and also still be able to answer some of those questions that we're not there yet, but this is how we anticipate that process to move forward. So, okay. Yeah,
cool.
It was fun.
All right, Ashley, moving on to you. You have the magic wand now. What would you change or do differently? And you can pick more than one thing if you really want to. Sorry, Jeanette, I didn't give you that option.
I would say, like, I would do differently in the sense of, like, I would ask the industry to think about adopting construction technology a little bit more, because you know, you look at other industries, particularly, let's say, manufacturing, and they've had like an enormous amount of productivity gain over the past, I don't know, few decades. Meanwhile, building construction, I think we've actually seen diminished productivity. Not to pick on you.
No, it's okay. I'll take it. I'll take it today.
And, you know, with that diminished productivity, I think a lot of it, you know, we're improving worker safety, et cetera. There's some valid reasons to that. But I think with construction technology, if we actually adopt it, we have a huge opportunity to really get that ROI. You could increase, or decrease, I should say, decrease cost. You can increase productivity via reducing your schedule. And oftentimes with construction tech, at least what I've seen, is that you have an opportunity to have that lovely marrying of like reducing your carbon footprint too. What I've seen is like some of those examples that the industry's had, and I actually commend the facade industry the most, is like in modular specifically. So if you think about it, we're crushing the game already. We're doing GFRC, precast, unitized curtain wall. We've thought about it. We're implementing it. Let the rest of the construction guys catch up with us. But you know, like just in modular, for example, if you look at ESG initiatives, they tend to recommend modular because it reduces on waste, it reduces on transportation costs, and you could actually install modular a whole lot quicker than you can, a conventional stick built or something like that. Then there's like other types of construction tech that are out there that, I'm pretty sure you guys are aware of and you guys are researching, you're interested in it, et cetera, but it's, let's say it's like a multi-use type of facade component. Think about an energy-producing facade, or integrating your EV panels with, your curtain wall fins, things like that. You could harness a lot of energy there, make it multifunctional and beautiful at the same time. I leave it up to them too. And that's an example. You could also do alternative product selection, right? There are alternatives to concrete. Or, for example, I know of one company who's 3D printing like these beautiful, intricate facades, and you could hang it as rain screen. Granted, like it's a challenge, and a lot of you out there are engineers or architects who have a lot of liability on your hands. I get that. So it's hard to adopt it. It's hard to be the guinea pig. But I think if we advance the industry that way, we have a lot of opportunity to gain.
Okay. We're going to pass the wand now to Pedram.
Yeah.
What are your thoughts? What would you change and do differently?
Yeah, I'm going to build up on what Ashley was mentioning, is the willingness of trying new things. It's very interesting that you mentioned modular. I think we did 10 different modular projects, but they were for 10 different clients. Basically, once they do it, they get PTSD, and then they're like, that's it, we're not going to try it anymore for at least some time. But I think walking through the process with the whole construction team and the client, with some of the advantages of trying new things, it also doesn't need to be scary. For instance, on Tahanan project, where I was showing it earlier, it's essentially in the Filipino cultural district of San Francisco. And then similar to Janet, we had community meetings, and they wanted to have something within the project that relates back to that cultural district. So we identify some elements, and we're like, okay, how do we use that? How do we integrate that into the project? Is it like a mural on the side of the building? But then we realized that, we can use some of these items as a form liner for concrete. It doesn't have to be board form always. So in our workshop, we tried some of the items, see how it sticks to the concrete. Some of them, it never gonna work, but some do. And then, it creates this beautiful texture concrete. And that's what we did. And once the construction team saw this, they got really into it. They built this one-to-one mock-up. The concrete superintendent drove to Southern California one day and then came back the same day to bring the bamboos that were the right height. So they got really into it. And the result was really, was very interesting. And I think people don't tag this. So that's like anti-graffiti texture, we call it. So that's one example of trying something new that comes from the community that doesn't necessarily need to be costing more. But at the same time, I want to acknowledge that some of the new things are going to fail because it hasn't been tested. The other item is, we had this perf pattern, and then we related it back to these rice patties, and then we use it as the perf pattern, and then, that's what you see on the side of the building that became the staircase of the building. The perf, the cost of doing the perf, it's essentially the same regardless of the pattern you use. So those are some of the examples we used as trying new things.
So following that thread down the trying new things, what, as the facade experts that we have here in the room, what's one question you feel like the next time they're meeting with a client or with an architect, what's one question that they should be able to answer, maybe about their new product that you feel like hasn't really been answered before, if we're trying something new? Sit around. What do you think? Ashley, you're kind of already nodding. What do you think? What's one question you would ask that this group sitting across from us would need to answer?
I would ask, what torture tests
have you sent your product through? Like, I want to know every little gamut that you sent this thing through and what was the performance on it. And like, who have you had look at your product outside of your immediate team? So for example, like in the construction tech industry, I've had some folks reach out to me and say like, Ashley, do you think this will work? And I'm like, no, that's a terrible, terrible idea. And or I'll say, I think you're onto something. I think you should maybe tweak these little things here. But my ultimate recommendation is always like, figure out if there's an ASTM test for that or something like that to send your product through the torture chamber and see what the end result is to see if you even meet ASTM standards on various items.
Do you want to torch everything? Is that where we're at? Okay.
I think what I always love when people are really into something is asking them what's getting them excited about whatever it is. And I think that there's usually opportunities there. So I feel like asking that question, what is it about your product that's getting you excited? And then trying to figure out how to marry that with whatever it is that I'm doing that's getting me excited. I feel like that's where creativity and synergy really comes together. So I love hearing what people are passionate about.
Yeah, I think cost also is very important. If I can tell clients that it's going to cost less than a stucco or fiber cement panel, they're probably going to go for it. So I think that's also what happened. The stucco became really expensive. And then that's when we were able to afford brick, corten, and other great things on the facade.
No, I definitely agree. I think that, can I have the wand for a minute?
Yeah.
I know as a moderator, I'm like, should I answer the questions? But I think that's ultimately what we look when we start approaching an affordable housing, project, and specifically, I mean, the facade is a huge part of that. And I apologize. But really like the efficiency side, and I really hope that we start looking at newer products, to your point, and part of that risk discussion is going to have to happen with people like me, right? You're going to have to bring me to the table and figure out how I'm going to be okay with that risk and all the general contractors of the world. And so I think that's a big point that collectively I think we'll have to do as an industry together, is to really figure out how to manage risk as a group. And risk is okay. Like, we can take risks on things as long as we know, what we think our outcomes are going to be, and kind of we weigh all our options together. So I really look forward to all of us someday working together on something like that. But I think Jeanette, in one of our prep sessions, you had mentioned that the problems that live in the affordable housing space, the problems are the same, but the solutions are different, I think. So if you all could leave this group with one inspiring thing to think about and go forward with, what would it be?
Well, I think for me, the challenge with affordable projects is to not have them obviously affordable projects. So maybe it's a no-brainer, but yeah, so how can we approach these projects and make them so that they don't have a stigma, they're still very design forward, they're taking advantage of creativity and innovation. All of the opportunities of a project are available within affordable housing projects. We probably just need to be a little bit more creative and proactive about it.
Okay, Pedram, what about you?
Yeah, I think if someone asked me what's the worst part of my job, I would say when we're value engineering not to a target, just for the sake of value engineering, which tend to happen more on market rate projects because it's constant, it happens during construction, versus the affordable housing projects, the way the financing work, once they get funded, they have to spend that money, so that value engineering has a goal, that once that goal is reached, you're there. It's a little bit better in a way that you think of the whole project as a whole, and you say, okay, this is the target, and this is where I'm going to spend my money and energy, versus with the marketer, you say, okay, great, you saved that much money there, can you save that also in this great part too? So I think when we talk about value engineering, especially with owners, I think it's very important to set a goal and try to stay within that goal.
Great. Ashley, what about you?
I would
Unfortunately, my perspective is a little bit more different, just being an owner. One thing that we're seeing in the industry ultimately is that affordable housing is now being pushed more onto private developers. Previously, we would have to just commit money to a fund, and then that would be our fee, and then we get to build our ultra-dense project. And now I think the solution is becoming different. It's something that's more imposed by cities, jurisdictions, et cetera, where the developer is going to be the one that is in charge of building the affordable housing. And so, you know, it's a way to approach affordable housing in a different way, and it's almost being imposed on us, but you know, that may not be for the bad. Maybe it's for the best.
Yeah, I think if I were to pile on, I would add to bring all those new and exciting things to the table for all of us to learn about, and know that you will have to teach us, because you all are the experts in facades, and there are new and exciting products out there. And I think if we can figure out a way collectively for affordable housing to leverage those new technologies and new things and manage the risk and make it beautiful, I think all of these kind of affordable projects will be better and will be built faster and with more confidence, and I think that is ultimately what all of our cities across the United States really need. So I think that is a big thing I would challenge this group to come to the table with, is all of the crazy ideas, and no idea is too crazy. So we say that in general contracting as well. Just kidding. But anyway, I know we're a little bit over on time, but if anyone has any last minute questions before you all head out for the evening. Otherwise, that was the end of our illustrious panel here. So thank you for sticking with it.
Thank you.
All right, thank you for everyone who stayed till the end. Really amazing panel. Creativity should not be limited by price. But go ahead, please. Thank you, everyone, for coming. And I hope you all have a great, long Memorial weekend. Have fun. And for those of you who will stick around, that'd be great to see you. All right, thank you. I think, go ahead.
Mic's on? Yeah. So thank you all for attending today's event. As I mentioned in the morning, we've recorded today's event. We'll share the YouTube link with you at by next week. I'd like to thank our event host, Edlyn. I think she did a great job. A round of applause for her. She was fabulous. Thank you all for taking time out. I hope you enjoyed today's event. Until we meet next time. We'll quickly have a photo opportunity with the panelists. Can I request Susan to come on stage? And we'll wrap this event up. Thank you all. Thanks for attending once.